Data binding is a concept often used in higher level languages. You can talk about Python or JavaScript for linking UI elements to data sources in a way that updates automatically. Now, C is a lower level language and it doesn't have built-in support for such abstractions. However, we can simulate data binding through a careful use of pointers and function pointers to achieve similar functionality. In this video, we will simulate a module view controller pattern, normally called MVC. This diagram presents a typical MVC pattern. We have the model which holds the data of whatever entity we are talking about. It could be anything that we want to store data about. The view displays the data to the user, and on top of that we have the controller which serves as a middle ground between both the model and the view. So when there is new data, the controller takes it and updates the model, and automatically it will notify the view so that the view will display the newly acquired data. Now go ahead and create a simple C file. First we include stdio. We also include stdlib. We need time because we'll be using sleep function, and we will also include unistd header file. After we have included the header file, we will go ahead and declare a few constants. Then we will start with the function declaration. So first, in this project we are basically going to simulate measurement of temperature using the MVC model. So let us declare a constant for the number of sensors that we'll be using. We can do sensor count, let's say 3 sensors, and also we will declare a log file where we will log all the temperature values. Then we can just give it a name, temperature.txt. Now because of the name we've given it, this file will be created right in the current directory. Once we have the constants, let us forward declare the functions that we will use in this project. First, the model, we can write a comment holds the temperature data and the thresholds. Now this will be a data type, so we will just call it struct model. Now for our view, as we said, the view will display the temperatures data and logs it. We can add a comment, which means that we need to declare a function that will update the view. So in this we will use a function pointer here. So we can say view update function, and as parameter it will take array of temperatures and also the number of sensors. We can do this float array and int. Because we are forward declaring it, we don't have to give them names. Now we can also add a function that will display the temperature. We can do display temperatures, and also this will take float of temperatures. Once again, we don't need to bring the name, but we can just bring it so that we know there is no difference. Then we can add the last function to log the temperatures, and once again float temperatures as parameters and the number of sensors, that is int count. These are all the functions that we need for the view part. Now the controller, as we said, it sits between the model and the view, and it updates the model and also notifies the view that there's a new data. We will have a struct for that, a struct controller. We will define the struct later in the video. Now we can forward declare a function that will check the threshold so that we know that the temperature that we have recorded is either higher or lower than the threshold. We can do check thresholds. We will pass a pointer to the controller as a parameter. Okay, we can create the next function that will actually update the temperature. This function will update the model with the new values, and we will pass controller to it and also the new temperatures that we want to be updated. We also need to declare some utility function. Because this project is about simulation, we need to write a utility function that will simulate a temperature sensor, and also we write a function that will allow the user to set the threshold. That will be for the user interface. Utility function read temperature sensors, and we will pass float temperatures to it. And this function, let's say user interface, it will allow the user to set the threshold, void set thresholds, and within here we will pass a pointer to the model. Very simple. These are all the functions that we will be defining in this project. We can go ahead and define all the functions. We start with the first one. Let us define the structs for the model. Let's make a type div with the struct model and an instance called model. As we said, this is going to hold the data, so it will have have a float for temperatures, which will be an array, and the size of the array will be the sensor count that we declared above. The next attribute of this struct will be the upper and lower threshold. The purpose of this threshold is to help compare the temperatures that we will measure. We define the next function. We will copy this forward declaration, paste it here, and we give it a body. This display temperature is part of the view. It will print the current temperatures to the user. We can do printf current temperatures. We can loop through the temperatures that we have recorded and print them to the user. We declare a for int like that, e++. Then we call the printf function. Because the temperatures are float values, we can print float values with 2 decimal places. We can add Celsius. Then we call I. Once we are done, we can print a new line. The next function is the log temperature. We do the same thing. The peculiar thing about the log temperature function is that the temperatures that we will measure from our sensor device, or in this case our simulated temperatures, we will write them to the file that we created above right here. We will create a pointer to the file. We call the inbuilt fopen function. We can pass the file and we want to append. Now if you scroll to the top of our pages here, we have already declared a file name here and we called it log file. That is what we are passing to this function. Make sure you spell it right. Capital file. Once we have the file, we can check if indeed the file was open by comparing it to null. It means that if the file is equal to null, we were not able to open it. We got an error, then we need to return. If this if statement is not called, it means that the file was successfully opened, so we can create a for loop here and we write all the temperatures into the file. E less than count, e++. We call the fprintf function. First we pass the object that we want to write the file to and temperature A. It will loop through the temperature and write everything into it. Once we are done, we can write a new line. And after writing a file, make sure that you close the file. And that is it for the log temperatures. We are done with the view here. The next function will be the check thresholds and update temperatures. Copy them, come here and give them bodies just like that. We will pass a pointer to the controller struct. The controller struct has already been forward declared here. Before doing this, just as we did for the model, we can also define the structure for the controller. Let us do it right beneath this. Type def struct controller and an instance called controller. Now I want us to take a look at the MVC model. We said that the controller updates the model when new data comes in and also it notifies the view, which means that the structure of the controller should contain a variable to the model and also it should contain that function that will notify the view, right? The view update. So inside the controller, we can add a pointer to the model and also the function pointer that we declared here, this function pointer. We will create an instance of this view update. Once we are done with it, we can complete the check thresholds. We will loop through the temperatures that we've already recorded and compare them to upper threshold and lower threshold. Start with a for loop, int equals to 0, int less than sensor count, e++. If controller, now the controller is a pointer, so we need to do this model.temperatures. If this value is greater than controller.model.upper threshold. If this is the case, then it means that the recorded temperature is higher than the threshold. You can do printf alarm, then we pass in the temperature, controller.model the temperature. We can also check for the lower threshold. This time we can say that temperature is lower than lower threshold. Let us write the function for the updating temperatures. Now this function, we passed a pointer to the controller and also a float of the temperatures. We shouldn't forget this should be an array. Make sure you update it because we are passing all the recorded temperatures to it. This is an array of temperatures. Now if we are going to update temperature, let us take all the temperatures that has been passed and assign them to the controller. We can do a for loop once again, controller model temperature E, then we assign it to temperatures E. To notify the view, we need to check that if controller view update not null. You can do controller view update. We can do controller model temperatures. We can pass the array to it and the sensor count. The sensor count is a global variable, so we can call it anyway. Now, after notifying the view, then we can go ahead and log the temperatures. Very easy. We just call the log temperature function. We pass in the temperatures and the count. Controller model temperatures, then once again the sensor count. That is it. Then we can also check thresholds and we pass the controller to it. After updating temperatures, we still have the utility functions to define. Just copy both functions. Let's give them bodies. Because we are not using an actual sensor, we are going to simulate the readings of a sensor, let's say thermometer. We are going to use a random value. That is why we included the time.h header file. So we can do a for loop. Now, how many temperatures are we going to read? It depends on the number of sensors that we have. For int is equal to 0, int less than sensor count, a++. Then here we call this temperature, which is empty. Now we are going to fill it with simulated sensor values. We call the rand. We divide the rand by rand mass, which is inbuilt function. Then we can multiply it by 50 and subtract 10 from it. And don't forget, this is supposed to be an array. Go to the top and correct that. The read temperatures function here. This is an array. Okay. We call the read function and it will fill this with simulated values. After doing that, we can set the threshold. Now the threshold that we set, it will be a user interface and it will give the user an opportunity to set upper and lower threshold to whatever he wants. Here we can tell the user enter upper threshold. We can use the scanf to get the value that the user is entering. Once we have the float, we set that to the upper threshold. Then we will tell the user to enter the lower threshold. Now with this, we have completed the entire function. The next thing to do is to write the main function from which the program execution will begin. So we do int main return 0. We will start by initializing a random C. We will then initialize the model. After initializing the model, we can also initialize the controller. And then we allow the user to set thresholds and finally simulate the temperature monitoring. Alright, with the first one, we can call the srand, which is an inbuilt function, and we pass time with 0. With the model, we create an instance of the struct model, then we will assign values to the various parameters. Now, since the temperature is an array, we can quickly loop through the temperatures and set all of them to 0 initially. Then we can do model.temperatures is equal to 0.0 f. After doing this, we can set the upper and lower threshold as well. So giving them initial values, we can do model upper threshold. We can set the upper to, let's say, 30.0 and the lower threshold to 0. The next thing is to define an instance of the controller struct, just as we've done for the model. Controller.model, and since we've already defined an instance of the model, we can just set it to model. The view update function, so we can set that to the display temperature function. After setting up the controller, now we can allow the user to set the thresholds, and this should be very simple since we've already defined the set threshold function right here. We will call it and pass a pointer to the model to it as an argument. We call the function, and inside we can pass a pointer to the model that we have created. And the last thing to do is to simulate the temperature monitoring. This simulation is very simple. The number of times we want this whole program to run, we will do a for loop here. Let's say we want to measure for about 10 times. We create an array for temperatures, sensor count. Then we will call the read temperature function that we declared. It takes temperature as an argument. After reading the temperature, then we need to update it. So we call the update temperature function, and the update temperature function takes a pointer to the controller and also the new temperatures that we've read. So we can pass a pointer to the controller and also the temperatures that we have just read right here. Now we can call sleep. Let's say sleep 1, just a delay, right, to simulate real-time monitoring. And that is it for this program. Now, once we are done with defining the flow of the program, you can go to where your C file is located and compile it. So I'll go to my terminal. I'll do ls. You can see that is my main.c file. So I'll do gcc main.c. Okay, great. Now we are getting some errors. Let's see. Saying main20 must use struct tag to refer to type controller. Here must use struct tag to refer to controller, struct tag to refer to the model. And also we are calling a printf and passing a float here, expecting a value, but we didn't give it any value to replace that placeholder. So go back to the code and let's fix this. Now when we go to the forward declaration of the functions, the controller is a struct, but it says we cannot do it like that. I'm not so sure, but we can fix that. Put struct in front of this, and also we can put struct right here. This should fix the problem. And the last one, where we are printing a float but not passing any value for the placeholder, right here, alarm temperature is below lower threshold, so we need to give it the value, which is controller.model temperature, and because it's an array, we get that specific value. Okay, having done that, let's go back and run it again. Let's clear it. gcc main.c. okay, the program compiled successfully. We have been given the executable file, so we just run it. And the first thing is asking you to enter upper threshold, so I'll say 60. Enter lower threshold, I'll say 20. Now when I click enter, it will loop through the number of times that we call inside the main function, which was 10, and it will compare the temperatures that it will get. This brings us to the end of this tutorial about data binding in C, how we can automatically update view when we get new values for the model. Oh, we have a game. Game 1. Enter. This game will cost me 10 credits to play. Pick a number between 1 and 20. I pick 10. Enter. Oh, I didn't win. Would I like to play again? Of course, I want to get my credit. Now I pick 5. Sorry, you didn't win. Do I want to play again? No. Game 2. Enter. This game will generate 16 random numbers. If there are no matches, I win. Okay, I want to gamble 10 of my credits. Enter. There's a match between 72 and 72. I lost. Do I want to play again? Of course, yes. I want to redeem myself. Enter. How many? This time I want to gamble 30 of my credits. Enter. Oh, I lost. I don't want to play again. N. Game 3. So this is a card game, and after choosing a card, the queen will be revealed, and I also get a chance to choose again. How many credits? 10 of my credits I want to wager or gamble. Enter. I should choose one card out of 3. Interesting. I pick card 1. Enter. Would I like to increase or change my card? Maybe I want to change. See, I have won. Now I have 50 credits, and it's pointing to the card I changed to. Do I like to play again? No. The flowchart of this program is intuitive. Immediately the program starts, it tries to retrieve the player's data. If it is not able to find the data, it assumes that it's a new user and register this new user and gives it all the default values. So after registering, it gets the data. Now it's able to go ahead and show the menu options. This game comes with 7 menu options. Option 1, 2, 3 are the games that you can play. Option 4 right here allows you to see the highest recorded score so far. Option 5 gives you the opportunity to change the username, and 6 allows you to reset the account to default. Now if you want to quit the game, you can go ahead and select option 7 and the program will end. Now one peculiar thing is, after playing each game, that is 1, 2, 3, you can play again by selecting yes, but if you choose no, the program will take you back to the menu options where you'll be presented with these 7 options, and it starts all over again. The only time that you get out of this game loop is either you choose not to play again by selecting 7. Even when your credit is finished, you can select option 6 to reset your account, get new values and proceed with the game. Okay, go ahead and open your favorite IDE, create any directory. I've created a directory and I've called it Game of Chance. You can name it whatever you like. So inside here, I will create a file and name it main.c. And also, I want you to create another file and call it hacking.h. Alright, we come back to that soon. But go into your main.c file and let's include some inbuilt function. Let's include the header file that we created because it is in our working space. Let us also include the stdlib. Once we have that, we can write our main and return 0. Okay, with this game we'll be writing and reading from file, so we will create the data file. So we can define data file, or maybe sometimes you can call it data path, and we want to put it in the tmp directory, and we can call this chance.data. This will be the path where we will read and write. Now we will need to store the information of every player or user on this game, right? So we will, let's write a comment, define structure for player / user. So let's write struct and call it user, and inside of this struct we will make way for the user identification. We will also store the credit. You know, when you play games you tend to have credit or money in some sense. We will create a variable to store his score. We need to save the name of whoever is playing. We can make this a character of 100 bytes. Now let us also create a function pointer, and this function pointer at any point will store the current game the user wants to play. So after playing a particular game, you want to change to a different game, it will assign this function pointer to the game you want to play. And we just write current game, and as we define function pointers, we do this. Every player in this game is going to have these attributes. We can decide to add extra attributes like the level, right? Don't forget to bring your semicolon. Alright, now after defining a structure for a user, we go ahead and define all the function prototypes, which we call forward declaration. First, we will start by getting player data as we stated in the flowchart. Immediately the program starts, it tries to retrieve the data. Another function that we need is we register a new player in case we are not able to retrieve the data. Now the next function will be to show high score. Okay, the next will be jackpot. This jackpot function will be called when the user wins a particular game. A function to get the user's name. This function particularly will be called during user registration, right? A function to print our cards. So whenever you want to print a card, you give the message to it and you give a pointer to the cards that you want to print, and also we provide it with an integer. After the print cards function, we need to create this function take wager. Now this wager is interesting. It will be used in multiple games. So for example, if you are playing a game that you need to use some of your credit, we call this function. Let's say that you are playing Find the Ace game and you want to wager about 10 of your credits, right? So it goes to this function, and this function makes sure that the total number of credits that you want to wager or deal or gamble with is less than the credit that you have. You cannot have a total credit of, let's say, 20 and you want to wager 50 credits. We will define this function, play the game. Now let us define dealer no match game. We will define find the ace game here, and we will also call this function whenever an error occurs, right? We can pass it to this function, and actually we will define this function in the hacking.h header file. After this, we can just show all users. This function is more for an administrator, but I've put it in here in order to show you how you can read all the users inside the file and you print it to the console. We also need to put a function to update player data, right? Yeah, I think it's important. You are playing a game and you win, we need to update your records. We also have the pick the number game. We need to write it here. Pick number game. Okay, take wager, play the game, dealer no match, pick the number game, find ace, fatal for printing any error that we face, and show all users. Finally, what we can do is, because we've already defined a structure for a player, we can come down here and define a global variable, right? We call it player. So we can come here, struct user player, so that wherever you are in the code, you'll be able to access this player. We can go ahead and dive into the application logic, but before that, I want to say that if you are liking these videos, go ahead and subscribe to my channel and like the videos. My goal this year is to get about 1,000 subscribers, so let's do this. Now, this is what we are going to do. We are going to use random numbers, so because of that, we need to call the seed function and pass time into it, right? But first of all, I want us to create a variable called choice. This is a game of chances, so we have some choices, and also we will create a variable to hold last game. And the reason is, after playing a game and we want to play again, right, we wouldn't go to the options. After every game, we save it to the last game, so if you want to play, we just go ahead and play it. We can go ahead and call the srand and pass the time into it to seed our randomizer. Now, if we look at our flowchart, the program starts and it tries to retrieve the player data, right? Okay, so let me go back to my IDE, write a comment like retrieve player data. And if it's not able to retrieve the player data, it registers it because it assumes it's a new user, right? So we'll call this, we'll try to get the player data, right? Let's make an if statement, get the player data. Now, if it returns -1, it means it didn't get the user who logged in. So now we need to register the new player. We write register new player. This part will ensure that either we get the user's data or we register new user. All right, once we are done with this part, we can go ahead and show the options just as we have in our flowchart. Okay, once we are done with this part, we go to the menu, and because this is C program, we are just going to do some printf. Let us do a while loop, and in this while loop, we are going to make sure our choice is not equal to 7. And why is that? The reason is, when we look at our flowchart, we said that if you want to create the program, you click 7. Yeah, so as long as the choice is not 7, we can go ahead and play. The game start, we either retrieve the user data or we register this new user. After doing that, we present him with these options. Then the next logical thing is that we will have to scan whatever the user will choose. Now we get the choice right here. Once we have the choice, it means we can use some if statement to define what the user wants to do. We can do if statement, and let's go back to the flowchart. You can see, according to the flowchart, 1, 2, 3 are games. We can just make an if statement within this range that obviously if the user chooses 0, then 0 is out of this, right? So if the choice is less than 0 or the choice is greater than 7, okay, then it's out of this game. We are not going to handle it. We can say if choice is less than 1. I know some people try to choose 0, or choice is greater than 7. You can show him the number is an invalid option number. Okay, else if the user chooses 1, 2, 3, then he's going to play a game, right? Depending on the choice that he gets, we will set this current game that we created, we will set it to the game that the user wants to play. We can also check something to make sure that the choice the user made is not equal to the last game, this last game, right? If it is equal, we don't have to come through the if statement. We can just go ahead and play it again. Okay, so if number is not equal to last game, then we can now see if choice, let's say, is equal to 1, right? Now if it's equal to 1, you can set the function pointer, right? This one. So we call player dot current game, right? And you can set it to pick the number, right? How did we define it? Pick the number. Okay, let's make it pick a number. It sounds better. Else, if the choice is equal to 2, then the user wants to play the second game. We set the current game to no match game. So we can say else, then we just assign player.current game, and now the last game that we have is find the ace, right? If the choice is not equal to last game, we always need to keep a tab of the last game being set. So last game is equal to the choice. Now we come out of this loop and we will just call play the game. Okay, so these are the game options that the user has, 1, 2 and 3. So after choosing a particular game, we set the last game to the choice that he made so that we remember next time. Then we will play the game. This else if statement was if the choice is less than 4. So we can also write here else if choice is equal to 4, and according to our flow diagram, 4 is to view current high score, right? So here we can show the high score. Else if choice is equal to 5 is equal to, sorry, make sure you correct that to equals. Yeah, correct this to equals. Okay, else if choice is equal to 5, and with 5 we are changing the username, input name. Let's put this in a curly bracket and yeah, bring this inside. Let us print change username, right? That would be cool. Your name has been changed. Yeah, that looks better. Choice 6 is to reset the account, right? Else if choice is equal to 6, you can say as your account has been reset, right, by credits. Reset the user's credit by 100, right? Now if you don't know this credit, we already created a structure for every player. This is the structure, and one of the variables or one of the parameters that it contains is the credit, right? It contains this credit. Okay, so now we've defined a global player here. So every player has all these characteristics, right? And this is a method. So every player has these characteristics. So when we come here, we are just resetting the credit. For example, if the user played and all his credits is finished and he wants to still play again, he can do that. Okay, so now we come here and we reset the credit, and basically this should be all for our application logic. The next step is for us to write and define all the functions that we have, all the functions over here. So I would like to start with, go to the hacking.h file that you created. We will create the function to print any error, a function to display error message. Basically that is what it's supposed to do. Now we have already, if you go to the main.c, you can see we call the filter here. That is the function. You can copy it and go back and paste it. That should be fine. And let's give it a body. Okay, so inside this we'll create an error message of 100 bytes, and we can use the string copy function. We need to give the parameter a name. Let's call this message error message. A fatal error occurred, right? Once we've added that to this array, then we can also go ahead and we use the string cut to join the error message and the message that we passed to that function. We assign the next 83 bytes to the incoming message. We concatenate it to the string. After that, we will call the inbuilt to print the error, and we have our error message. And last but not least, because it's a fatal error, we would like to exit. Basically, that is all that we have in the hacking.h header file. Let's go back to our main.c. The first function we have here is the get player data. The get player is going to read the file. How is it going to read the file? We already created a data path right here, data file. So we are going to create a file descriptor and use the file descriptor to open the data file and give it some privileges. We have our application logic set up. We will go ahead and create the first function, and the first function is going to be get the player. This function, if it doesn't find the player we are looking for, it returns -1 and goes ahead and register the new player. If it finds it, then great, it retrieves the player's data and set it to the global variable right here, player. Now I want you to scroll down to the bottom. Outside the main loop, we don't put any function inside the main loop. Okay, so now outside here, go back again and look at the function prototypes, get player, and how we defined it. Okay, so get player, it was defined as int get player data. You can go ahead and copy it. Of course, I'll copy it. You can copy it or you can write it. Now scroll to the bottom, make space for yourself, and we paste it, and we give this function a body. Now before we define it, why don't we leave some comment? Okay, maybe you can say for the current UID. And what does it do? It returns -1. It returns -1 if not found. That is what this function does. Now we are going to read from a file. So first, let us create a function descriptor, and also let's create a variable to hold the UID, that is user identification, and the last variable will be the number of bytes that we want to read from the file. Now the number of bytes we will compare with the structure. Scroll to the top of your program, and as we define the structure, every player is going to have these parameters and also this method. Now to know the number of bytes we are going to read is just adding these. Okay, so we have 4 bytes for UID, 4 for credit, 4 bytes for high score, 4 for level, 100 bytes for name, and most of the time function pointers, they have size of 8. So the total size of this structure will be 100 plus 16 plus 8, that is 124. Scroll back, let's define some things. Let us get the user identification, and this is inbuilt function. So we can say get users unique. Any person who logs in, because this is a console program, will get a unique identification. Once we have the unique identification, we can go ahead and open the file. So function descriptor is equal to open, and we pass the data path or the data file. We call it data file, and if you don't know the data file, we define it on top of our program. Scroll to the top of your program, and right here we define the data file, and this is where we want to put the names of the players. You can choose any directory you want to. Just declare a macro on top here and set it to the directory you want. Go back, we pass in the data file, and we are only going to read So read only. We are only going to open the file. Now, if you know something little about reading and writing of files in C program, when the program is unsuccessful, it returns -1. Okay, we can use an if statement to check. If the FD is -1, it means it was unsuccessful, so we return -1. In our case, -1 means that the user doesn't exist. If the user does not exist, then we create a new user for him, right? If it doesn't, then the program continues. Then we can go ahead and read the number of bytes that we want. So this time we will call the inbuilt read function and we will pass the function descriptor. Now you shouldn't forget, now the function descriptor will now point to this file, and it also has the privilege, the read only privilege. We pass in the function descriptor, which is a pointer to our file. Then we also give it the destination, okay, where we want to read the file into, more like a source template. Okay, so what we can do is that right under this, let us create an instance of our structure user and call it entry. Okay, now we pass the size of the entry. What this means is that we go into a file and we are telling it that we want to read this size of entry. What it means is that the read bytes, after reading this total size, we can compare with the read bytes. If the read bytes we get is less than the size of the entry. Now, how do we know the size of the entry? We just figured it out. We combine all the parameters inside the user structure and we can make the comparison, right? A quick look is this, okay, 4 byte, 4 byte, 4 byte, 108 bytes. That is the size. So now we will read the first entry, but because we want a specific user with a specific ID, we need to look through the entire file so that when we get a match, we can say that this is the player that we are looking for. We can just make a while loop here and we will say that while entry.UA is not equal to the UA that we are looking for, or the UA that is logged in, and read byte is greater than 0. Now when you are reading a file, this read byte function, as long as it is able to read this size, it means that the read bytes will be greater than 0. If read bytes is greater than 0, it means we are reading something. If read bytes is less than 0, it means that probably we are at the end of the file. So while this is true, we want to keep on reading. Just read bytes, we call the read function again, we pass the entry, size of entry. Okay, we can put a comment here and say loop until user is found or the ID is found, right? This will make sure that it keeps on looping until the UID matches. Now when it's done looping, we can close the file. After closing the file, we can also check if we've come to the end of it. We can do an if statement and look at the number of bytes that we have. If the read bytes, let's say the read bytes is less than the size of entry. If this is the case, as I said, it means probably we are at the end of the file, right? And we couldn't find what we are looking for. So we will return -1. We only have one statement in there. So let us remove the curly bracket. Else in the sense that if read bytes is equal to the size of entry, then we found the user we are looking for. If we found the user that we are looking for, then we can set our global variable to the entry, right? Hooray, we found what we are looking for. And we can also print some statements onto the console. We can print a lot of stuff as well. We can even show his credit, player.credit. Then we can return 1 or 0, because according to our program, it's only when we return -1 that it sees that it wasn't successful. Now if you look at this, okay, if it's called -1, then it will register a new player. So we can return 1, which means it's successful. Yeah, we are done with the get player data function, and the next function that we are going to create will be register new player. That is in the case where this function returns -1. And which cases will it return -1? Case 1 is when the file descriptor is not able to open this data path, and also when we get to the end of the file and the read bytes is less than the size of the entry. It means we got to the end and no data was found. Let's go to the next function. Function to register a new player will be simple. So first of all, let us scroll to the top and see how we forward declared it. This is the function. It's a void register new player. Once again, you can copy and you paste it right here. Void register new player. It takes no parameters. But before we do anything, as usual, maybe we can leave some comment. Now, because we are also going to access files, we can go ahead and declare the function descriptor variable. At this point, this is a new person, so we can maybe give him a warm welcome. New player registration. We will tell him to enter his name, right? Please enter your name. Then we call the input name function. We have not defined that function yet, but that is okay. We will define it right after the register new player. Now, after getting the player's name, the rest of the parameters, we give them default values. So we can set the player.uid. We can set the high score to be the same as the credits, right? Let's give it 100. And also the level. Now, what I was thinking when I added the level is every time a player wins a game, his level increases, right? So if you win 3 games, then probably you go to level 3. You start at level 0. Once we have given these default parameters, the next thing is to save it into our file. We go open. The first will be our data file. Now this time, because we are going to write, we need to pass more privileges to this function. So first we will pass this RW. We are going to read or create or append, and also let's add these privileges. The user be able to write, read, and also execute. If FD returns -1, it means there was a problem. We can use if statement to check. If FD is equal to -1, at this point a fatal error occurred. We are going to call fatal. Now this fatal function is what we define in the hacking header. When the message is passed into the fatal function, it creates, let's say, a private variable here, and it adds fatal error to it. Then it adds your message, which means that if, let's say, you pass an error message of something happened, it comes here and output will be fatal error plus something happened. Very simple. Let's come here and we will pass in a message. If no error occurs, then we can write all the data that we have given to the user. We create the player data and we go and save it to the file. FD, a pointer to our source where we are reading it from, right? And the size that we want to read, size of struct user. Okay, then we can go ahead and close our file. When we get to this point, it looks like we are successful. Then we can welcome the user to the game of chance. By the way, credit to this game goes to the book title, The Art of Exploitation. If you guys have time, you can take a look. It really goes deep behind the scenes of C programming. And maybe we can tell him some of the things you have. Yeah, I think this is good enough. Now, the function we need to create next is input name. Yeah, right here, input name. So come here and void input name. What this function will do is that it will just allow the user to enter his or her name, save the name to the player object. The player is a global variable, so it can be accessed anywhere. Let us add a comment here. What we can do is we can just create a pointer to a name, right? We can say a name pointer, and also we can create an input character. Initially we set it to line break like this. We will say, wow, this input character is equal to the line break. We are going to read the input of the user. We do scanf here because this is a character, and we will pass our input character. We are going to point the name pointer to the address of the player's name. This is the global variable, but basically this name is what we are talking about. Convert that into a character pointer and we get the address of player.name. Maybe we can leave a comment. Now once name pointer is pointing to the address, it means whatever we do to this will take effect right there. We do a while loop, and this time while the input character is not equal to this, the reference name pointer, and we will set it to the first character that was read. Then we need to read the other characters. The user's name might be long, right? Read the character, put it input character, and we will just increase name pointer ++. So So every time we go through the loop, we are setting the name pointer to the character that is read. After we've done that, you read the next character. At the end of this, the player's name will be set to whatever the user types in. Once we are done with this, we can set it to 0, which is we are just terminating it. Basically, this will be the end of the input name function. Now that the input name function is completed, let us create the function to update the player's data. Now scroll to the top and we already forward declared it here, update player data. So let us give it a body, void update player data. So when you win or lose, we call this particular function to update the info. Now because we will be accessing file, let's go ahead and create the file descriptor, and also we are interested in the read UID, that is the UID that we will be looking for. Now when we are updating file of a particular user, we are interested in the identification of that user. So we go through the file and we only search for the identification. If we scroll to the top of our program to the definition of a user struct, it starts with UID. So what we can do is that we go into the file, then we read the UID. Now the UID is an int, so it's 4 bytes. Okay, so we have our player's UID, then we read that UID and compare. If that is what we are looking for, we found it. The rest of the data we are not really interested in. We loop through quickly, then we get to the next UID, then we will read. Let's put it in code. Go back to the function. Let us create this bend byte. We will use this variable to loop through the other data that we don't need. We are only interested in finding the user identification that matches, but the rest of the file we will just walk through just like that. So now we can call our function descriptor, open, and we pass the data file. We want to read and also write, so let's pass the RDWR to it to give us that privilege, and we know that if the file descriptor returns -1, an error occurred, so we call the fatal function. Now we define the fatal function inside the hacking header file right here. We define it here. Maybe we tell it where the error occurred. Now if the file descriptor returns a positive integer, that is if it is not equal to -1, then probably it was able to open the file. So in that case, then we can read the first UID. The first 4 byte will also be the UID. Once we've read this, we will try and compare this UID to the player's UID. If it is the same, then we found what we are looking for. If it is not the same, then we keep on looping. While this read UID is not equal to player.UID, it means we've not found what we are looking for. Then we can go through the rest of the parameters. We don't need them. But this time, don't forget that we have already read the first parameter of the struct, which is the UID. So we need to subtract 4 from this. Then we will do E++. We will pass the file descriptor, and this time we will use the bend byte. Should be the address instead. By the end of looping through the rest of the struct, we can read again the UID of the next struct. I hope this makes sense. What we are doing is that we are going to the file, and the file contains users, and each user has these parameters. Right now we want to update a particular user. We go into the file, we read the UID. Now the UID is 4 bytes. So after reading the UID, we are not interested in the rest. So what we do is that we will just loop through without saving anything. Once we come to the end of this, it will be also the beginning of the next user. All right, scroll down. So that is exactly what we are doing here. Right here, we read the first UID inside the file. Once it's not what we are looking for, then we go ahead and we will bend through the others parameter of that struct. We don't need it. At the end, we are starting a new user. We read that one too until we find the user we are looking for. By the time we come here, we are sure we already have what we are looking for. We can use the write inbuilt function, and we use the function descriptor as usual. Name is 100 characters, so 100 bytes. Close the file. Let's leave a comment here. This will be all for updating the player data. So the next function that we can write, showing high score. Void show high score. As usual, let us leave a comment. This function will show the highest score available. All right. I guess this function can also show the name, the player who got it. Okay. Now, since we will be reading file, we can go ahead and create our file descriptor, and let's create a variable to store the top score. make sure it's unsigned int because this cannot be negative. And we can also create a variable to store the name, right? Top name. And this also be maybe a character of 100 bytes, just the same as the property of the user struct. Then we will create a user template here called entry. We can use this to loop through the file. Let's create an introductory message. We welcome the user with this, and we can go ahead and open our file. We pass in the data file, and at this point we just want to go in there and read something. We don't really want to do anything else, so we can do read only. If we wanted to update, we could use the RDWR. If LD returns -1, it means there was an error. We call the filter function and we pass in. The error occurred in show iScore when opening file. At this point, if an error doesn't occur, we can go ahead and do the while loop. We want to read throughout the file and see the player that has the highest score. We can call the read function. From here, we pass in the file descriptor and we can give it the entry that we created, and we want to read the size of the host struct user. We want to read everything, and we know that whenever you read, it returns the total bytes that was read. Then let's get something from here. Now we can check the top score, that is the high score, if it is greater than our top score. If this statement is true, we set the top score to entry.highscore. Then we can also set the name. Let's use string copy, the inbuilt function. Let's copy the user's name into the top name, so we can do entry.name. Why don't we initially set the top score to 0? We've gotten the top score and also the name of the person who scored it. We can close the file, right? And at this point, we can make a simple comparison to see if the current user is the top score. If that is the case, we will tell him that you are the top score with this. If not, then somebody else is the top scorer. If the top score that we have recorded, if this is greater than player.highscore, then clearly our current user is not the top scorer. You can say somebody has the top score. Else, top score is less than the player high score. It means our player has the highest score. We will do player.highscore. Now once we get here, we are done with everything, so maybe we can do something to show the end. Alright, now as we can see, this function will go inside our file and look for the top scorer, save his name and the top score. If the current user is the top scorer, it will tell him that you are the top scorer. If not, then it will give us the person who is the top scorer and the score that he is using to lead. Let's dive into the next function. So we go to the top and see, after the showing high score, the next function is the jackpot. Why don't we just copy this? We paste it. The implementation of the jackpot function is really simple. All that it will do is that once a user wins a game that involves a jackpot, we call the jackpot function, and it will just increase the user's credit. That is it for the jackpot function. The next function is input name, but I've already defined the input name here. The next function that we have is print cards. Now the print cards will be used for find the ace game. 3 cards will be presented to a user, and the player is supposed to pick one that he thinks is the ace, right? One is ace and the other 2 are queens. Let's copy this, make space for it. Now because we are defining it here, cannot be like that. This is going to be the message. This function pointer is going to be the cards, and this will be user pick, right? Let us give a comment for this function. It will print the 3 cards. Now when this card is called without any user pick, then the user pick, we can pass -1 into it. In that case, this function will print the card. So it could print like XSX, and it will ask you to choose one card. We can define an index to use for looping. Let's print the message that the user input. After that, we can just make a little design, maybe with tabs. We just want this to align with the number of cards that we have. Then the last printf, we can go ahead and print the contents of the card. Card 0, cards 1, and cards 2. Now at this point we can assess what the user picked. Now if the user pick is -1, it means he has not picked anything yet. We just want to print the content of the card. We can do something like maybe tell the user to choose 1, 2, 3. Else, if the user picks something out of the 3 options, show what the user picked. We want to do a for loop and show the contents of the card, and we show which cards among them the user picked. We can do for loop as long as it's not what the user picked. We can print tab. Then here we can use this sign to indicate what the user picked. Let's put this in bracket. They are all under the else. That will be all for the print cards function. The next function that we need to complete before we go and define our games is the take wager function. So we go to the function prototypes and we declare the take wager as this, but actually we need to pass some parameters in there. First of all, we need to pass the available credit and also previous wager. And the reason is that this function allows you to gamble some of your credits. Let's say that you are playing the find the ace game or match the dealer game and you want to gamble some of your credit. You want to gamble 20. Okay, if that is the case, you pass the 20 to this function and the 20 will make sure the total number of credits you want to wager should be less than your available credits. Other than that, you will not be able to play that game. So it makes sense that we pass some parameters. So scroll down and let's copy it and let's give the function a body. We paste it here. Let's give some comment. First, let's declare a variable for the wager and also a variable for total wager. We can ask him how many of your credits do you want to wager, and we can show the available credits. Once we are asking the user, we are expecting an input. We can do a scanf here. We give it the address of the wager. You can wager only positive numbers. Return -1. So -1 means that what he entered in wasn't right. Now if the wager is greater than 1, then we can go ahead and find or calculate the total wager, which should be the wager the user entered plus the previous wager that we passed to the function, right? Okay, perfect. So once we find the total wager, we can do an if statement to make sure that the number of credits the user is trying to gamble, if it is greater than available credit, it means he cannot play the game. Other than that, he can play the game. We return the wager. That will be all for the take wager function. Let us see what else. So now we are left with defining our games. And actually these are the interesting parts. Okay, so we start with this. It will kind of provide a loop and allows us to play the current game over and over again. So for example, if we take a look at our flowchart, in the flowchart we said that the 3 games, pick a number game, no match dealer, and the find ace. At the end we have the opportunity to either play again or not play again. So if we say yes, then we play our current game or the last game again. If we say no, then we are presented with the main menu options. Okay, now this function will give us that opportunity to do that. So let's give it a body here, and the comment will be this function allows us to play the current game again, and also it will update the player data. It will give us a loop and we can keep on playing the game over and over again. So when we come here, we can create the variable and call it play again, and maybe we can just set it to 1. Now we will also create 100 characters, that is an array, and this array will be used for keeping the user's preference. If the user say yes or no, or if he says Y or N instead of yes or no, we will keep that in this character. So probably 100 is too much, right? Let's make it 50. But you don't know, maybe somebody might write, yes, I want to play the game. We are just getting ready for all circumstances. Then let's create our loop. While play again is 1. I want you to scroll to the top of the program, and when we define the struct of a user, we said that there is a variable that holds the current game. This variable is important. We can always print the pointer to this game. But the current game that we are playing is always set to this address. When we come here, we can say, maybe for debugging purposes, pointer of current game, player.current game. We need to check if the current game didn't return -1. Once again, take a look at the flowchart. How do we know that a game is over? Now, after each game is ended, there is a return value. Whenever an error occurs, a -1 will be returned from these games. So as long as the return value is not -1, then we know that the game was played without any error. If player.current game, so the game will be called, you can play the game and it will return. So if the return is not equal to -1, it means the game played successfully. After playing each game, probably you lost a credit, or let's say you won a credit. This is the place where we can choose to update the high score. We can check the player.credit and we will see if it is greater than the high score that he has. If that is the case, we do player.highscore equals player.credit. After doing that, maybe we can tell the player the credit that he has and we will update the player. Just as we have updated the high score, you now have this credit, right? After showing him his credit, we can call update player data, which we have already defined. If you don't know, we scroll up here. Right here, we have defined update player data. So come here and let's call that function to update player data. We call it here. After doing that, then we can give the user option to play again. Like maybe, would you like to play again? There's a question. At this point, we are asking the user if he wants to play again or not. Let's get his input. We can do select. We can set the first character to end line. Then we can do a while loop. While select is equal to this, then we will get the user's input. Select. Okay, so now we have the user's input. So we are going to check the input whether it's a yes or a no. If the user say yes, it means that play again is still 1 because play again is already 1. Right, so we will not even check whether it's yes, but we are interested whether the user said no. Show him what he chose. Then we will do this select. All right. We do a simple if statement. If the user chose no, if the first character is n, it means the user doesn't want to play again, right? So we will set play again to 0. Immediately we set play again to 0, it means this loop will not run when it comes to the end. But now let us look at this whole if statement. We can say that if current game doesn't return -1, it means the game played with no error. Other than that, there was an error. Okay, so we have to set play again to 0. Okay, so two situations where we will not play the game again. The first situation is if the user decides not to play again and he enters no here, or if an error occurred during the game, then we will not be able to play the game again. The play the game function is done. So at this point, let's look at what else we need to define. All right, we are done with the play the game. So now we will go ahead and define the 3 games. You guys should brace yourself because we are going to the interesting part. And I want to remind you guys that if you are liking this video, subscribe to this channel. And once again, credit to this game goes to the book called The Art of Exploitation. If you really want to dig behind the C programming language to know what is behind the hood, you can take a look at it. Like and subscribe. Let's do this. Okay, now that we are done with the play the game loop, that will allow us to play our current game over and over again, we will define our first game. Let's scroll to the top and see the games that we have. We have 3 games. We have dealer no match, pick a number and find the ace. Let us start with this. Pick a number, copy it and move to the bottom. Let's give it a body. Before we write anything, let us add some comments. Now the way this game works is very simple. You will pick a number. Inside this function, we will get a random number and save it as the winning number. So if the number that you pick is the same as the random number, then you win. Now to play this game, you will lose 10 credits. But if you win the jackpot, and the jackpot is worth 100 credits. Very easy. We can define your pick and also winning number. Now let us welcome the user to this our game, and we will explain to the user how he's supposed to play. Just pick a random number between 1 and 20, and if the number you pick is equal to the winning number, you win the jackpot. So when we come here, we can set the winning number So we want a random number between 1 and 20, right? We are telling the user that it will cost him 10 credits to play, which means that we need to check if he has that available credits, right? If he doesn't have, then we will tell him that sorry, you cannot play this game. So we will say if player.credit is less than 10, then he cannot play. You need at least 10 to play. This is the credit that you have. You cannot play. We return -1. He cannot play. If he has more than this credit, we subtract 10 from his credit. We can tell him we have subtracted this number of credit. Then we can also tell him to pick his number between 1 and 20, right? Then here we can do the scanf, and whatever he picks, we save it to the address of pick. So now we've deducted his credits, that is 10 of it, and we are giving him the chance to pick a number. So once the player has picked the number, we will check if the number is the winning number. If this is the case, then he has won the jackpot, right? So we call the jackpot. Else he didn't win, right? Then we can tell him sorry, you didn't win. Okay, and we return 0. Don't forget, we only return -1 if, for example, he didn't have enough credit to play. But when we get to this point, it means that he was able to play successfully. He just either won or lost, okay? So we return 0, and that is the end of the pick a number game. Okay, once we are done with the pick a number game, the next game that we will write will be the dealer no match, right? We'll copy this as usual. Let's give it a body and let's write some comment for this game. So as we are starting, let us define some variables that we will need. We will need some indices to get the random numbers, and also to search through the random numbers if there are matches. Now we also need an array to store. We will store 16 random numbers. Now this variable will hold the value the user wants to wager or gamble, and the last variable is to determine whether there is a match in the random numbers. Okay, now the idea of this game is simple. It is going to generate 16 random numbers. If there are any match among the numbers, then the dealer wins and you lose. If there are no match among the numbers, then the player wins. When the player wins, the amount that he is wagering or the amount that he is gambling will be added to his total credit, and if he loses, it will be subtracted from his credit. So let us welcome the user to the game, no match dealer game. We can also give the user some information about this game. The dealer will deal 16 random numbers, right, between 0 and 99. If there are no matches, you win. To play this game, you shouldn't have 0 credit. So let us check if the player has 0 credit. If he has, then we will return the game. Okay, sorry, you don't have enough credit to play, then we return -1. If he has enough credit to play, then we can go ahead and ask him the total number of his credit he wants to gamble. We can do while wager is equal to -1. We've already set the wager to 1. Okay, let's make it -1. Then we can call the take wager function that we already defined above, and when we call the take wager function, it requires us to pass in the available credit and the previous wager. So we will pass the user's credit, and it's our first time calling it. There are no previous wagers, so we will pass in 0. Once we've done that, it's time for us to get 16 random numbers and put them inside this array. We can print something to the console and say that dealing 16 random numbers. Now we can use a simple for loop. A is equal to 0, e less than 16, e plus plus, right? Now at this point, we are going to generate some random numbers between 0 and 99 and put them inside the numbers array. Numbers to bracket a equal to rand modulus 100. Once we get the numbers, we can go ahead and print them straight away, just for the user to see the numbers. So we can do, after 8 numbers, we print the other numbers on a new line. If e modulus 8 is equal to 7, then we can print a new line. After getting the random numbers, we will search through the random numbers and see if any of the numbers match. Once again, we can use a for loop. Now we can use the j variable that we created, and we will set j to e+1. We compare one number to the number right next to it. While j is less than 16, then we will try and see if we get any matches. So let's say if numbers into bracket e is equal to numbers into bracket j, right? If this is true, then we have a match. We can set the match variable to the numbers that are matching. Alright, and we increase j. By the time we are done with this for loop, the match will be equal to the last number that are matching. So definitely match will no longer be equal to -1 here. So when we come here and we check the value of match and it is not equal to -1, it means there was a match. If there was a match, then the dealer wins. If match is not equal to -1, it means match has been set to a value, then the dealer wins. The dealer match the number, we can show the match. The dealer won and the player lost. You lose that credit, and the credit you lose will be the credit that you wagered, the wager. We subtract the wager from your credit. Now if match is still equal to -1, it means that none of the numbers matched, so you win. There were no matches, and this will be your wager, and we will add it to your credit. Now at this point we've come to the end of the game, then we'll return 0. And just like that, that is all for the dealer no match game. The final game that we will write is the find the ace game. Let's do it. Find the ace game is quite simple. This is the whole concept. A player will be presented with 3 cards. One of the cards is ace and the other 2 are queens. After the player has made his choice, one of the queens will be shown to the player, and the player will be given 2 options. Either he doubled down on his first choice, that is, he is sure of his first choice that he will gamble more of his credit, or he decides to continue and finish the game. Let us scroll to the top of the program where we forward declared the function. It's right here, find the ace, and we can decide to copy it. Come back to the bottom, make space, and let's give this function a body. Now before we write anything, let us leave some comment. First, we will declare an integer that we will use for looping. Now this should be for the ace. This variable will store the value of our ace, and we will get them randomly. Also, we can declare our total wager, because as I said, you have the chance to gamble twice. Let us declare a variable and call it invalid choice. Now this variable will also hold the value of whatever card the player will pick. Now let us define wager 1 and also wager 2. No, we set it to -1 instead, which means that the total wager will be wager 1 plus wager 2, and wager means the number of credits you want to gamble. Now we come here and we also define choice 2. So first the user will make a pick, and if he decides to, let's say, change it, he can have a second choice. Let us create an array of length 3, and this will just contain these placeholders to be SSX. So initially when we print this card to the user, nothing will be revealed, only XSX. So beneath this XSS will be 2 queens and 1 ace. We will use the random number generator to get our ace. So randomly we get the ace value and we store it right here. Now at this point we can print some information to the user as to how this game works. Alright, we give the user instruction. You'll be presented with 3 cards. 1 is ace, 2 are queens. Now you make your choice. After making your choice, one of the queens will be reviewed. At this point, you can either select a different card, or you can just increase the wager. That is, you double down and you are sure that your first pick was right. Now, as usual, if your credit is less than 0, you cannot play, right? I say, sorry, you don't have enough credit to play. Once again, we return -1. Now, if this statement doesn't run, it means the user has enough credit to play the game. Alright, so the first thing that we will do is we ask him the number of credits that he wants to gamble, just as we did for the other game. So we can do a while loop here, and we will say while the first wager is equal to -1, we can say wager 1 is equal to take wager, and inside the take wager we will pass the credit. And because this is wager 1, there are no previous wager or gambling credit. Okay, so we pass player.credit and 0. Now after this point we can print the card right to the user. Let us look at our print card function again. We pass a message and also a pointer to the card and the card we are picking. But as you can see, if the user pick is -1, it means the user has not made any choice, right? Then we will give the user instruction to pick 1, 2 or 3, telling him that there are 3 cards available, so pick 1. Okay, so we come here and the instruction will be dealing cards, right? The pointer to the card, so we will point the card to this. This is the array that we have created for the card. So because it's array, it will default to a pointer, so we will do this. Or you can also do this if you want to give it the address of the first element, right? It's more or less the same, but let's delete it, make it simpler, and we will get it -1, so we are not making any pick. After printing the cards, then we can go ahead and set pick to -1. Now we have to tell the user to pick something. Now there are only 3 cards available, and the user can either pick 1, 2 or 3, which means that any value below or beyond that is out of bounds, right? While pick is less than 1 or greater than 3, we will keep on asking the user to input a new number. You can say select a card, right? 1, 2 or 3. Whatever the user will put in, we will assign it to the address of pick, just like that. Now at this point we need to adjust the value the user picked. We have 3 cards, 1, 2, 3, but because it is in an array and an array is addressed from 0, we have 0, 1, 2. Okay, so we need to adjust this to make it work with the array. We can initialize the variable that we created. Okay, we want to use it now. Now in the game we said that after the user has made his pick, we will show him one of the queens. Okay, so let us do a while loop. We have to make sure we are only showing him one of the queen, right? While E is equal to ace, and we don't want to show him what he picked previously. Then after doing that, then we can go ahead and get the cards, and we set that character to kill. Immediately after setting this to queen, we can print the cards. So here the message will be revealing a queen, and we pass a pointer to our cards to it. And what is the user pick? Now this time the user has a pick, so we give it the user pick. Now we are at the point that we will give the user the opportunity to either double down on his first choice or change to a different card. So he will make a second wager here, or gamble twice. We can call the invalid choice and we set it to 1, right? And we'll loop it while invalid choice. We can tell the user, if you want to change your option, this is the time. Would you like to increase your wager or change your pick? You can say select either E or C. Alright. Once we give him this information, then we can scan for the value that he picks. So we can start by setting the choice to line break, and inside the while loop we can do while choice 2 is equal to this. We will scan for the user's choice. We can do scanf. Choice 2 is a character. Choice 2. Shouldn't forget, this is supposed to be an address. After getting the user's choice, we can go ahead and check whether he wants to either continue or he wants to gamble more of his credit. If choice 2 is equal to E, it means that he wants to wager more of his credit. We will set the invalid choice to 0. Yeah, because after this we don't want to loop again. After setting the invalid choice to 0, we can do while the wager 2 is equal to -1. We will call the wager function. This time we will pass the available credit and also the previous wager. So we will do wager 2 is equal to take wager, and we pass player.credit, and the previous wager this time will be wager 1. Okay, once we have this done, the next thing that we will do is we can also check if the user chooses to continue. That is when choice 2 is equal to C, when he decides to change to a different card. So in the same case, we will set invalid choice to 0 because we don't want this to run again. And after that, although he's changing his choice, we have to make sure it's neither what he picked before or the queen that we showed him. I mean, it could be true that what he picked before was the ace, but he doesn't know at this point. He's changing his mind. So we can do while a is equal to pick, that is his first choice, or we showed him a queen while index of e inside the card is equal to, and we have to make sure that his second choice is none of these. So we will do a plus plus. Okay, after we found it, then we can now set his pick to the other card, right? So now we loop and we make sure that his second choice, he's changing it, right? But now because he's changing it, he doesn't have the power to say he wants 2 or 1, but rather we are looping through and making sure that his second choice is not the same as his first choice here, and also is not the same as the queen that we show. So we set it to the last card that is found because we only have 3 cards. Then we can print a message and tell him that your card pick has been changed to. Now because in indexing we use 0, so we have to add this to this. Okay, basically at this point we can show him the cards and let him know whether he won or he didn't win. Come outside the while loop and write a comment, review cards. And let's do a simple for loop. We use the index that we created up, and this is less than 3, then e plus plus, right? We will do if the ace, and we already randomly selected the ace. If the ace is equal to e, then we want to set that index in the card to, we want to set it to a, right? Else set it to queen. Very simple logic. So loop through the 3 cards, and whatever index equals the ace, make it this, set that character to a, and the rest should be q, representing queen. After doing this, we can print the cards again for him to see. We can say revealing cards, right? We give it the cards pointer and the user's pick, just like that. So after this point, we are going to handle whether the user won or lost. We know the user won if the pick equals the randomly set ace. You have won dash credit from your first wager 1. Then we can add wager 1 to his credit. If wager 2 is not equal to -1, we also have to add wager 2 to his credit. He won twice. We can put this in curly braces, and before that we can print a message, let's say an additional credit from your second wager, right? Wager 2. Now if he didn't win, else make sure you correct this. If pick is equal to ace, double. Now if pick is not equal to ace, then he lost. We can tell him that you have lost this number of credits, right, from your first wager 1. Then we subtract it from his credit. We can say if wager 2 is not equal to -1, then he use it. Then we can tell him that additional lost credits from wager 2, and we subtract from his credit. So by the time we come here, we are done with the game and we return 0. Now bear with me, find the ace game is probably the complex among the 3 games. Now that we have completed the find the ace function, we can go ahead and compile our program and start debugging. Open the terminal and go to the directory where I created my C file. So that is it, and I'll compile it. So these are the warnings that we got. We'll go through and fix each one of them. The first one is giving this error and is saying get the player is invalid. Okay, so we are calling a function get the player and it's invalid. So let's find the problem. Let's scroll to the top of our program and see the function prototypes. So these are our function prototypes. It seems there is no get the player, but we are calling get the player function here. Instead of calling the function get player data, we are calling get the player. Okay, so this is the function get player data. So let's correct it. We clear this, get player data. The next error, what is it saying? Main C line 62 int pointer, but argument has type int. Okay, so let's go to main file line 62. Right about here, we are calling scanf, and with scanf you pass a pointer. Let's add this. So we corrected that. Let's see the next one. The next one is saying expression results on use. Play the game. Okay, it means play the game. We are returning something. First, let's check the function prototype. Play the game, we are returning an int. So if we are returning an int, then we need to use it. Let's go to how we defined it. Yeah, so obviously this function is not supposed to return anything. It's supposed to be void. So let us remove the int and put void. Now when you do this, make sure you go back to the function prototype, and also let's correct this. It's supposed to be void, not int. The next error is saying main.c line 152 scan. Okay, so we shouldn't forget, always when you call the scan, you need to pass a pointer, that is to the address. So let's go to 152. Yeah, right here we are calling the scan input character. We need to pass the pointer to the address. Then obviously here too we need to fix this. Let's check the next error. Now this error is interesting. It's saying comparison between pointer and integer, character pointer and int, while select is equal to this. Line 278. Let's go to 278. Okay, this is 278 and we are using this while loop while this is equal to new line. But as we can see, select is an array of characters of length 50. This array is for storing the user's input. Alright, now because this is an array, we are saying select is equal to this. So obviously we need to only get the first element in the array. Alright. So if the user, for example, types yes, we are only getting the first character. While the first character is a new line, it means the user hasn't entered anything. So we'll be waiting for his input, right? Let's see the next error. Let's run it again. So go to the command line and I have typed gcc and main.c. Okay, now what are we getting? Expression result on use. Play the game. Line 76, that is main line 76. Okay, this is the line. Now you see the mistake. We are calling a function, so we need to bring this. Okay, let's run it again. gcc main.c. Alright, now the program runs. So we will run it like this. Oh, our program is here. So now we've been provided with the options. Hello everybody. A microcontroller is a tiny computer. Typically it has a CPU, a RAM, flash, and a bunch of pins that stick out, as you can see in this diagram. The RAM, which translates random access memory, is a volatile memory that is used for temporary storage. We say it is volatile because immediately you cut power to the microcontroller, you lose the data that the RAM stores. When the program is running, the RAM stores things like the variables and the stacks. ROM, on the other hand, read-only memory, is a non-volatile memory that can be used to store firmware or data that doesn't change frequently. Traditionally, ROM is rarely used in modern microcontroller units, but the concept includes storage mechanisms that retain data even when power is cut off. So when power is cut off, the ROM retains its data. The flash memory is a specific type of non-volatile memory, which means that when the power is cut off, all the data that is saved in the flash is retained. Now, the flash is often used in MCUs to store the firmware. For example, when you are booting your MCU, it first needs to read certain instructions, and all those code are stored in the flash. Sometimes it is also used to store constant data. Now, flash retains its content even when the power is off. Now, depending on the microcontroller that you use, you see a lot of pins. Some may have 64, some might have even over 100 pins. Some of the pins are used for power, specifically the ground and the VCC pins. Now, the other pins are mostly used to communicate with peripherals. When I say peripherals in this instance, I'm talking about external devices like a temperature sensor, pressure sensor, motion sensor, whatever sensor that you have. An LED is one of the simple electrical devices that you can connect to a microcontroller, right? So you connect one side to ground. Normally we connect the shorter leg to ground, and you connect the longer leg to a different pin, a signal pin on the microcontroller. So what happens is you write a firmware on the microcontroller, and the microcontroller sends high or low voltage to the signal pin. If it sends high voltage to the pin, the LED turns on, and if it sends low voltage, that is 0 volts, then the LED is going to turn off, right? There is no power. The interesting thing about a microcontroller is not all these cool pins that are sticking out, or the design or the circuit board. The fascinating thing about the microcontroller is on the inside. Now, when we cut open a microcontroller, not like we are going to cut it open, but when we do, a microcontroller contains different types of peripherals. Inside the microcontroller, we have a CPU, we have ROM, flash, RAM, RCC is clock. We have GPIO and a lot of other peripherals like the UART and the SPI and I2C. A lot of them, okay? We cannot represent everything here. Now, all these peripherals that you see occupy a specific place inside the microcontroller. The same way your house is located at a specific place inside the microcontroller, every peripheral, including the core peripherals, the CPU, the ROM, the flash, the RAM, they are a specific address. Now, if you want to communicate with a particular peripheral, you go and you get the address of that peripheral. Now, let's assume that the first peripheral inside this microcontroller is the CPU, and because it is first, we are going to give it an address of 0. Okay, so now we have 8 zeros, and this number is in hex. If that is the case, and let's assume that each peripheral that you see here is 1 kilobyte in size. Now 1 kilobyte is 1024 2 raised to the power 10. We can say that the first address starts at 000, which means that the second peripheral, here is the ROM, will have an address of 0x0000400. Now 400 is in hex, and when you convert it to decimal, you get 1024. The third peripheral here, that is the flash, will contain an address of what? I think you can guess now. The address are going to increment by 1 kilobyte, 1024. So the first one start at 0, the next one start at what? 1024. Then the third one is going to start at 2048. Now 2048 in hex is 800, right? So the address of the flash will be 0x0000800, and the others follow suit. The address for the RAM will be C00, the address for the RCC will be 1000, and the address of the GPIO will be 1400. Of course, I'm not saying the 4 zeros, but they are part of the address. This is how easy it is to get the address of all the peripherals inside the microcontroller. So now, if we scroll up a little, you see all these pins, right? We call them GPIO pins, and the GPIO pins are part of the GPIO peripheral. If I want to connect an LED to this pin, it means that I need to go inside the microcontroller, get the address of the GPIO. When I get the address of the GPIO, then I can take it from there. There are different types of microcontroller unit architectures. We have 8-bit microcontrollers, we have 16-bit, 32-bit architecture. A microcontroller with a 32-bit architecture can address a memory space of 2 raised to the power 32, and that will give us 4 gigabytes of space. So in a 32-bit microcontroller architecture, the size of the registers will be 32-bit. In normal sense, a register maybe is used for keeping stuff. You use a register to keep names of people or probably names of items. It is the same in microcontrollers. Now, a microcontroller has peripherals, right? We have RAM, we have RCC, we have GPI. Now, when you pick one peripheral, inside that peripheral, we have registers. Different peripherals have different registers. So, for example, the RCC peripheral will have different number of registers compared to the GPIO. Just see registers as a space inside the peripheral, but actually it's a circuit that makes that peripheral act in a certain way. If you want one pin of the microcontroller to power an LED, you have to go to the register that is specific for doing that. For example, outputting data, and you write to that register or you read from that register. Let's scroll down here. Now, before we talk a little bit about registers, the inside of the microcontroller, when we lay microcontroller on a flat plane, if this is supposed to be the space inside the microcontroller, the first address starts here and the flash will be located somewhere there, and the RAM and the peripherals. When you pick one peripheral, the GPIO peripheral, it has a couple of registers. Let's say we have register 0, register 1, register 2, register 3. When you pick UART peripheral, it has a couple of registers. As I said, different peripherals have different number of registers for different purposes. I want us to take a look at some of the microcontrollers currently on the market and see what is going on inside. Okay, go to your browser. I use Google, but feel free to use whatever, and let's search for STM32G0B1RE datasheet right there. Click on the datasheet and yeah, there we go. Go ahead and download the datasheet. We also need something we call reference manual. By the way, in programming a microcontroller the bare metal way, the few things that you really need to embrace and learn to read are the datasheet and reference manual. They contain everything that you need to know about the address of peripherals, the address of registers, and how you can interact with specific registers. Let's search for STM32G0B1. This time we want the reference manual. Okay, so right here, download it. That is the reference manual. Okay, once you are done, I already have it. We will look at something. I'll start with the data sheet. Okay, this is our data sheet. I want you to search for block diagram. Block diagram. Yes. Now, this is the block diagram of the specific microcontroller that we are dealing with. It contains STM MCU. From the block diagram, you can see peripherals everywhere, okay? But I promise you, it is not confusing at all. At the center of this microcontroller unit is the clock source, that is the RCC. Now, when we go here, you can see GPIO, general purpose input and output. Inside the GPIO, we have specific port A, port B, port C, up to port F. Now, each port has a certain number of pins. So now when we go back to this microcontroller, you can see it has pins, right? So probably this might be 16, let's say 64 pins. It could be that all the pins here belongs to one port A. It could be all these pins belong to port B, port C. But don't forget the same peripheral, and the peripheral is GPIO. So GPIO, it has instances. It has port A, port B, port C, port D, port E, port F, and they are all GPIO. They are all pins that you can use for different purposes. I want you to come back to the center, that is the RCC. You can see some lines that are connecting peripherals to this central clock. Okay, look at this line here, like a pipe, and they've written AHB. Now, all the pipes that you see here, we call them bus. Okay, so this is a bus, and this bus is written APB. This is another bus, it's also APB. Let's see, this is another bus, is AHB. You can see there's one bus here that goes and connects to bus matrix, so this is also a bus. On the left side, this is DAC. DAC is also a peripheral, digital analog converter. It means that if you have a digital signal, let's say a high or low, and you want to convert it to analog. So analog signal, it means that it fluctuates. So the analog signal that will be generated will fluctuate between 0 and 5 volts. ADC is another peripheral, analog digital converter. So the DAC and the ADC, they work in the opposite way. Now the ADC, we use that to measure analog signals and convert them to digital. Let's say that you want to measure voltage. Okay, you have specific voltage and you want to use the microcontroller to read it. Then you have to connect that voltage source to the ADC of the microcontroller, and this peripheral will convert it from analog to digital. Now beneath it we have SPI, SPI2, SPI3. Okay, so the same peripheral, different instances. SPI is also another peripheral that is used for communication. Earlier on I said that some of the pins of the microcontroller unit are used to communicate with sensors. Different sensors also use different forms of communication protocols. So SPI is one of the communication protocol. UART is also one of the communication protocols. Now when you come here, you can see we have USB. I'm sure that you are familiar with USB, the USB that you use in charging your phone phones and other stuff. Yes, actually USB is a peripheral inside the microcontroller. If you have a PC in your home and there are USB ports, it means that the USB port is being connected to the microprocessor in your PC. So it is a peripheral inside there. The port that you see is just an extension to enable you to connect whatever you have to the peripheral. All right. Now on the right, you can see we have USART, which is also UART. All right. Now besides these, we have the timer peripheral. Let's say that you are doing something and you need to time stuff. We have the power control. We have some watchdogs. Okay. An event happens and you want to trigger something. Different peripherals inside the microcontrollers are used for different activities. Enough of the data sheet. Close it and let us take a look at the reference manual. Let's see what we got. You downloaded it, so go ahead and open it. Inside this reference manual, I want you to search for memory map. You scroll down a little bit. This is what we are looking for. This is the memory map of the MCU dev kit that I'm using. In a glimpse, you can see this memory map presents the address of all the peripherals and the components inside a microcontroller unit. Now, as I presented in the first page right here, every peripheral inside the microcontroller has specific address, right? So now, this microcontroller, this is how it looks like. The flash memory occupies this address. You can see main, flash memory, system memory, and RAM. There is a part of the memory that is painted gray. It is reserved. You can't use that part. So we have flash memory, this part reserved. Here we have system memory. When you look at the left, RAM peripherals, okay, all the UART, all the SPI, all the I2C, all the timers, they are part of the peripheral. On the right, the peripheral is extended into buses. Now, when we opened the data sheet, you could see that all the peripherals were connected to specific bus, right? I hope you've not forgotten. Take a look again. This is the block diagram. You can see all the peripherals are connected to a specific bus and the bus connects to the RCC. This point is where the AHB bus is connected to the APB bus, right? For now, don't worry about the name of the acronym. Just know that AHB, APB, they are buses. So they are channels through which the peripherals are connected to a clock source. Every peripheral requires the clock source to run accordingly. All right, now pull the data sheet aside and let's look at the reference manual. The APB bus, it starts at this address 0x4000000. That was difficult to say. And it ends at this address 0x4000A7FF. Now, if you are wondering why we still write address in hex and not in decimal, copy this address and let's convert it. Go to your browser and type hex to decimal. Paste this, make sure there is no space, right? Convert. Is it easier to say 1,073,784,831, or is easier to just say 0x4000A7FF? Enough of that. Now go back to your memory map. There's a second APB bus that starts from this address and ends here. Now there's a gray area, which means it's reserved mostly. This bus, it starts from here and ends here. The IO port starts from here and ends here. Now, these bus are important. The reason is that every peripheral is connected to a bus. The GPIO is connected to the IO port, which means that if we want to get to a particular GPIO peripheral, we can find that within the IO port address range. In the same way, the other peripherals like the SPI is connected to the APB. Therefore, if we want to find the address of the SPI, we need to look at the range of the APB bus. To prove that, let us scroll down. If you look at this table, SRAM, which means that it's a special type of RAM. It has a starting address here. Now this is the flash memory, and the starting address of the flash memory is this, just as we saw in the memory map. All right, look, flash memory starts here. Let's find some of our known peripherals like the GPIO. On the bus side, we look for IO port, right? The boundary address 0x5000000 to this is occupied by this peripheral, GPIO-A. The next range of memory, which has a size of 1 kilobyte, is occupied by GPIO-B and GPIO-C, D up to F. Flash is connected to the AHB bus, and the address range of the flash is 0x4002 2000 up to this, and is 1 kilobyte in size. Enough of the STM32 MCU. Let us take a look at other MCU. One of the popular MCUs is the Atmega, right? Because of the Arduino platform. Let us search for Atmega 2560 datasheet. Download the datasheet. Open it here. On the first page, it gives you some characteristics of the MCU that you are going to deal with. There's JTAG. We are interested in something that has to do with memory. So let's search memory map. This is address map with external memory. What about block diagram? This is the inside of the Atmega 2560 microcontroller unit, mostly called the Arduino Atmega. Alright, so at the center is CPU. Now right here we have flash, we have RAM here, different types of RAM. Let's see what we got. We have a bunch of peripherals. We have the SPI, TWI is here. We have the AEP ROM. Now on this side, you can see port A, port G, port C, and definitely these are the GPIO ports. On this side, we have the USART3, USART1, USART0. Commercially available microcontroller units. They come with multiple instances of the same peripheral. Okay, so the USART peripheral has few instances, like we have USART3, USART1, USART0, the GPIO likewise, and the others too. Let us check on the registers and see. So here the AVR CPU general purpose working registers. The registers are laid out here. So register 0 up to 31. Each register has a definite purpose. Open the reference manual again. I want you to set the GPIO register. Every instance of a GPIO, so whether it's GPIO port A, GPIO port B, each instance has mode register. It has the output speed, the pull up, pull down register, the input data register, output data register. Now, one of the things that make embedded system very interesting, especially doing bare metal programming, is some of the registers. Their names are very self-explanatory. Okay, this is what I mean. Look at all the registers here. Literally, they are telling you what they do, which means that if you want to communicate with a particular GPIO peripheral and you want to read the input from that peripheral, then clearly you are going to deal with the input data register. In the same way, if you want to output something or write something to the register, then you can see right here, output data register. Now click on the mode register and the first register of the GPIO peripheral. You can see right here, it has written GPIO X mode R. The X just means that the peripheral has multiple instances. We have GPIO A, GPIO B, GPIO C. Okay, so if you are dealing with GPIO A, then this register will be GPIO A mode R. If you are dealing with GPIO C, then the mode register of that instance of the GPIO peripheral, that is C, is going to be GPIO C mode R. The microcontroller we are dealing with right now is a 32-bit architecture, which means that the registers are 32 bits long, starting from 0, 1, 2, 3, up to 31. It allows you to define how you want to use a particular GPIO pin. In case you want to use a particular GPIO pin as input, then you need to set the part that corresponds to that pin to 00. Now, how do you know? Take a careful look. We have mode 0, mode 1 up to mode 15. Now, each mode has 2 bits under it. What it means is that in regards to this microcontroller unit, that is the STM32 J0B1, inside this microcontroller unit, each GPIO peripheral has 16 pins. So from mode 0 to mode 15. Alright, now if I want to connect an LED to this particular pin 0, what I need to do is that I look at the mode that corresponds to pin 0. If I want that pin to put on or off an LED, it means that pin is going to act as output pin. I need to write this to bit 0 and bit 1 So I come here. This is general purpose output mode. The pin is going to act as output. Why? Because it will send volt to the LED. Bit 0 here to 1 and bit 1 here, I need to set it to 0. What if I want to connect the LED to, let's say, pin 7? Okay, easy. Pin 7 corresponds to mode 7. This is mode 7. What are the bits under mode 7? 14 and 15 right here. It means that I need to set pin 7 as output mode. So what do? The first bit is bit 14. I set it to 1. The next bit I set it to 0. That is bit 15. In the same way, if I want to connect a button to the microcontroller unit, and when I press the button, I want the microcontroller to do something, I need to set that pin as input pin. So that when I press the button, let's say that the state will be high, and when I leave it, it will be low. If I want to connect the button to pin 8, then pin 8 corresponds to mode 8, right? Then I need to set this mode as what? As input. So I'll set bit 16 to 0 and bit 17 to 0. When we scroll down, we can see the other registers that we have. The data register, you can see, is read only. If I want to read a value from, let's say, pin 11, it means that I come to pin 11 right here and read whatever value is there. This is the output data register. And the output data register, you can write or read. These bits corresponds to the number of pins. Now from 16 to 31 they are reserved. This is a general overview. In the next video we are going to implement writing and reading from specific registers. Let's assume that this is GPIO and we want to write to pin 2. Go back to the reference manual and search for the memory map again. We know that the GPIOs are connected to the IO port. So scroll down. On this side we have the bus. So we will look for the IO port. And this IO port, starting from the base address, that is GPIO, and they are laid down consecutively for GPIO to B to C to D, and they are 1 kilobytes apart. We are going to start with GPIO, but before that, just create a directory wherever you want it and create a file. I called it main.c. So you can include this. We want to set GPIO, let's say pin 3 as output. This is what we want to do, and also after that we want to set GPIO pin 5 as analog. Alright, we are going to do this. Go back to the reference manual and we will copy the base address of GPIO. Now before you paste it, whenever we are addressing memory, we use the volatile keyword, and as we said, we are working on 32-bit architecture. We cast the address to 32, and inside here we just paste it, and we need to add something to it. Before that, make sure you close the gap here. As we explained earlier from our diagram, a peripheral contains a couple of registers. Go back to the reference manual and search for GPIO registers. These are GPIO registers. We have a couple of them. Click on the first one. Now we want to set pin 3 GPIO as output. According to this, to set a pin as output, you need to set the first bit to 1 and the next bit to 0. Okay, we are dealing with pin 5. Pin 5 means that is 16 pins. Set mode 5 as output, so you set bit 10 to 1 and bit 11 to 0. Before we set that, just look on top here. Registers are arranged inside peripherals, one after the other. If this is our first register, it means that it has an offset of 0. It's the first register inside the peripheral. Okay, so it has the same address as the peripheral. Now the next register is the GPIO OTYPER. Because this is 32 bits, that is 4 bytes. Okay, so the second register will start at this offset and it just goes on. The third will be 0x08 and the next one will be 0x0C, just increasing by 4 bytes. I want you to remember that. Go back to the VS Code, and here we add the offset. Because we are dealing with mode R register and it is the first register, the offset is just 0. All right, so we do this as the offset, and Now to set specific bit inside the register, first you have to make sure that it is cleared, right? So to do that, we have to end it with the number of bits we want to deal with. Each mode deals with 2 bits. So if we want to set 2 bits in here, then we have to look for a number that has, let's say, 2 ones in there that we can manipulate, and that number is 3, right? If each mode had 3 bits here, then when we come here, we actually look for a number that has, let's say, 3 consecutive ones, and that will be 7, all right? But now we only need a number that has 2 consecutive ones, and we can use 3 to do that. So we take our 3 and we are interested in pin 3, okay? Now pin 3 starts at bit 6 and bit 7. So come here and we are dealing with pin 3. 3 times 2 is 6, okay? So we are going to shift 3, 6 to the left. All right, so when we do this, and that is it, we have cleared a bit, clear bit 6 and 7. Now after clearing it, then we will set it to the particular mode that we want. I'll copy and paste it here. Instead of end, we will have to do all here, and we remove this. And because we only need to set bit 6 to 1, we can't use 3, right? Because if we use 3 here, it will set both bit 6 and 7 to 1, but we don't want that. We can use 1 like that, and this is going to set it. So by doing this, we have set pin 3 of GPIO A as output, right? Now the next one, we want to set pin 5 of GPIO B as analog. So the first thing we want to do is to go to the reference manual, get the address of GPIO B. Let's do that. So we come here, we search for the memory map, we will go to the IO port, this IO port, GPIO B, and the starting address is here. So just copy this, go to your VS Code, and we will do the same. We are pointing to address, right? So we have to cast it to volatile, and we are dealing with 32-bit. So we cast whatever address to uint32, paste the address that we copied, and now once we have this, we will go to GPIO B and get the registers. But don't forget that GPIO A, B, C, they are just instances of the same peripheral, okay? Go back again to the GPIO registers, you get the mode R register right here. Yeah, so it's 1 1, okay? Pin 5 corresponds to mode 5, and with mode 5, 5 times 2 will give us 10. So we start from bit 10 and bit 11. We will set bit 10 to 1 and bit 11 to 1. Now mode R register is at an offset of 0x00. It's the same for different instances of the same peripheral, okay? So the offset will be 0x00 here. Make sure you remove the space. First, you need to clear bit 10 and bit 11, okay? We need 2 bits to do that, and 3 will help us. So we use 3, we move it to bit 10, clear bit 10 and 11. After clearing it, now we will set both bit 10 and 11 to 1. So I'll copy and paste this, and we will use all. This time, because we need both bit 10 and 11 as 1, we are going to maintain 3, alright? If we wanted to set GPIO B pin 5 to output, we'll use 1 here, alright? We just use 1 over here. Yeah, that is it. Very simple. You get the address of the peripheral, you get the offset of the register you are dealing with, then you go ahead and you set your bit, alright? Now go back to the GPIO registers. What if we want to write something to a GPIO? Okay, let's say we want to write high or low to a particular pin of the GPIO. What are we going to do? Let's try that. Let's look for the data output register. This is the data output register. It means that whatever we write here will be written to the pin. If we write 0 here, then it means low, right? If you write any number here, it will be interpreted as high. So we just write 1 and it will be interpreted as high. So what if we want to write high to pin 9 of GPIOC? Okay, let's write it here. Let's see. I think you guys can take a few minutes and work it out, but we will do it just as we did for the others. Okay, we'll go to our reference manual, we go and get the address of GPIO C. But if you watch closely, we said that the GPIO peripherals, that is ABC, they are at an offset of what? 400. So A is 000 and B is 0400. Okay? So you can see that C is going to be 0800. That is very easy, but not to confuse you, go back here and let us search for the memory map. Okay, once we have the memory map, we go to the IO port bus, and this is GPIO-C, right? So go ahead and copy this. You write the same thing, nothing different, volatile. We cast it to UIN32 inside here plus offset, right? So we write it here plus the offset of the register we want to deal with. This time we are going to write to the output data register. Okay, so we'll go back and get the offset of the output data register. Search for GPIO registers. Okay, so the registers are here. The output data register is this. We can see that the offset of the output data register is 0x400. all right, so you can copy that. When you come here, you add that. So write 0s14, and we just want to write high to this register, but not only this register, to a specific pin, that is pin 9, right? So we need to go back here. This is pin 9, and pin 9 is exactly at bit 9. Okay, so bit 0, bit 1 up to pin 9. Okay, so we are going to write high to pin 9. So go here, and this time we can just use all, right? And because we are writing high to pin 9, we can just shift this, right? And once we do this, basically we shift it to the left 9. So if we compile this program and we flash it to our STM32 board, whatever is connected to pin 9 is going to receive voltage. So if we have LED, then LED is going to set high. But I'm just curious, why don't you try write low to GPIO-C pin 9? What do you think is going to be? We want to write low to GPIO pin 9. Don't forget, GPIO-C pin 9 is already high. So if you want to write low to it, what do you think? Are you going to do this? If you do this, obviously 1 is shifted to the left 9 and we invert it, so we get 0. But since pin 9 is already 1, if you do 1 or 0, it will still be 1. Okay, so to do that, you have to use AND. So when we AND 1 with 0, then we are going to get 0. Let's move on. We create a struct to represent the peripheral, and inside the struct we represent the registers with a 32-bit type integer. First, go to your reference manual, search for GPIO registers. These are all the registers of the GPIO peripheral. We are going to represent all these registers inside the struct. Create the struct here. We call it GPIO. We are going to reference memory, so always you shouldn't forget to bring your volatile keyword. We use the 32-bit int. Then you need to be careful here. Now all these registers, they are 4 bytes apart, that is 32-bit. So starting from mode R, then you go to the OTYPER, then you go to this, you go to that. You need to write them accordingly. If you, let's say you start with the mode R, and instead of writing this, you write this, then later if you want to address this register, it will be at the wrong offset. You are not going to get the correct results that you want. So place your reference manual close by and write them. So let's do that. The first register that we have, the first register is the mode R. The next one is the OTYPER, OSPDR. We go to the IDR, ODR, PSRR. Just come to the next line. LCKR, AFRL, AFRH. Then we have the BRR. Okay, so look here, the registers are 11. Okay, this is not a register, it's just GPIO register map. What is there? Okay, so when you go there, it actually gives you all the registers starting from the first, the mode, and their offset. Yeah, so we have 11 registers. That is it. Now after creating the struct, then we can just define our GPIO A. Then we will do as we did for here. So we need to get the address of GPIO A, then we will cast it to this struct. Write your define properly. We have our struct we will cast it to point to this GPIO register and we will get the address. Now this is the address for GPIO A. We just copy it here. Once you have this, I think you can just create the struct for the others. Now don't forget this is a struct, so we have to bring the semicolon so that the red thing here goes. What do you think if we want to represent GPIO B peripheral? Obviously this is B and this is easy. You look at the B and the A and the difference is this, right? That is the offset. So what you can do is you can just add 0s400, right? But I prefer to put this into bracket like this. Once you get the concept, the rest is just easy, and that is 8. To make it consistent, then let's make GPIO A as 0. Now this is how you create a structure for a peripheral of whatever you want to deal with. When we looked at the GPIO peripheral, we saw the input modes, right? We can create an enumerator and we represent all these. Input is 00, which is 0. Output is 01, which is 1. Alternate function is 10. This is 2. Analog mode is 11, and 11 represent 3. So we do enum here, and the first 00 is input, right? So we can do GPIO input mode, GPIO output mode, GPIO alternate function mode, and the last one will be GPIO analog mode. We have represented the modes for GPIO. The next thing that we can do is we can write a function that will clear the bit for us, and also it will set the bit that we are interested in. We can create a static inline function and call it GPIO set mode. If we want to, let's say we want to set pin 2 of GPIO A, we want to set it to analog, we call that function and we pass it into that. So come here and let's create a function. Let's make this static inline. It will not return anything. Let's call it GPIO set mode. So here we will give it a pointer to our GPIO structure. We will give it pin number. So we can just say pin, and also we will pass the mode that we want to set. Okay, this should be, let me close this. This should be a very easy function. We are just going to replicate this. Okay. First, we need to clear the particular part of the register that we are interested in. But to be able to know where to clear, we need to find the shifting value. Now, the shifting value depends on the pin number. So if we want to clear pin 5, when we look at the mode R register, each mode has 2 bits. So pin 5, we are going to start at bit 10 because we multiply by 2. Okay, so when we come here, we will use that mindset to do that. So instead of putting an arbitrary number here, we are going to put the pin and we multiply by 2. So whatever pin that we pass, we multiply by 2, and the 3 will remain. That should be fine. We will. Now we have passed a pointer to the peripheral, that is the GPIO pointer, and we need the mode R register, right? So we get the mode R register, we end it. We have 3. Now we just add U to make it unsigned value, right? Now we are going to shift this 3 depending on the pin that we have. And since, as I explained, each mode corresponds to 2 bits, we will get the pin and we will multiply by 2. You can leave a comment. Once you have cleared a bit, then you can set it. Okay, to set it, we call the mode R, and setting we use the or instead of the end. Now there's something that we need to do here. When you look at how we were setting each bit, the setting of the bit depends on the mode that we want to. If we are setting the mode analog, then we are going to set a part of the 2 bits to 11. But if we are setting as input is 00. So this part depends on the mode, okay? And the mode has only 2 bits. These are all the modes. So when we end whatever mode we have with 3, we will get the mode that we want. Then we will shift this according to the pin that was given. So when we come here, we can do mode and 3. So let's assume that we are going to set that pin to input mode, and input mode is just 00. So it means here we pass 0 to it. So when we do 0 and 3, we are going to get 0. So once we have the 0, then we can shift it to the particular bit range that we want, and it's just the same as what we've done above. This should be Easy. Now what it means is that whenever we want to set the mode of a GPIO, we just call this function. For example, we can do GPIO set mode. The first one is a pointer to the GPIO struct. So if we are interested in GPIO A, we call GPIO A over here. The next one is the pin. Let's say we are dealing with pin 3, and the next one is the mode. Here are all the modes, so we can pass GPIO input mode. And it's just like magic. So now we don't have to do all of this. We have just put everything inside a function right here, and we can call it. And actually this is the beginning of hardware abstraction layer. We are abstracting some of the hardware. Okay, so you are not going to write the registers yourself. We put everything inside the function, then we will call the function right here. There is a little problem. When you look here, we have to define each instance of GPIO. So if I need GPIO F, I have to physically write it here. So I'll define it, then I need to calculate the offset, right? When you look at when you go back to the reference manual, IO port, right here. So we have GPIO A, B, C, D. So if I want GPIO F, then I'll have to copy this address, right? But maybe there is an easy way that we can just write a generic function by looking at the offset here. The starting address, this is starting from 0, then the size is 1 kilobyte. So the offset is 1 kilobyte, 1 kilobyte, right? So we can just write the base address and we multiply each by a number. Okay, so if we give this the base address, then here this part we call bank because there's an increment and the increment is 1 kilobyte. If we pick the base address for GPIO A, the bank for GPIO A will just be 1 kilobyte times 0 to give us this 0. Okay, and the bank for GPIO B will be 1 kilobyte. Now 1 kilobyte in hex will be what? 0x400. So we have 0x400 times 1 for GPIO B. For GPIO C, it will be 0x400 times 2, 0x400 times 3. You see where this is going? Yeah, so with that we can just write a generic GPIO macro. So whenever we call that macro, we pass in the bank. So if the bank is 0, then it means that it is going to return GPIO A peripheral. If the bank that we pass into the GPIO macro is 1, then it's going to return the base address plus 0x400 times 1. So whatever bank we pass into this generic macro, it will return the corresponding GPIO instance that we want, right? So let's do that. Right under here, leave some space and let's define. It will be GPIO, and this one is going to take, let's say, this variable called bank. We want this to return the GPIO instance depending on the bank that we pass to it. So we call the struct here and we'll cast it to GPIO pointer. We get the base address. We are going to add that to the offset times whatever value the bank is, right? We can do this right here. As we said, if we pass 0 here, then it means here we are going to get 0x400 times 0. So this entire thing will be 0, which means that this GPIO is going to return GPIO A. If you pass 1, then this part will be 0x400 times 1, the same 1 kilobyte. So when we come here, we will get 0x500000400. If we pass 2, get 800. This macro will return whatever instance of GPIO that we want. Now, I think instead of calling GPIO set mode here and we pass the specific GPIO instance, right? It will be nice if we can do something like this: GPIO set mode, and we just pass a pin to it, then we pass the mode. So somehow let's find a way and combine the GPIO instance that we want. Let's say we want A or B, and we'll combine it with the pin number. Now when you look here, the pin is just 1 byte containing the pin number. So we can make this pin number 2 bytes so that the higher bytes will contain the bank. Now when I say bank, I mean A, B, C, D, alright? The higher byte can contain the bank number, that is the pin bank, and the lower byte will contain the pin number. Example, we have this pin GPIO A pin 7, right? This is GPIO B pin 9. So when we call this, we will do something like this: set mode and here we got the pin and we want to set it to output. We can do something like this. Let us create a macro that the macro will take the bank and also the pin number and combine them, okay, and it will return pin. Go right beneath this one. Let's define this macro and we call it pin. Okay, so this macro will take the bank, as I said, and it will also take the pin number, and we want it to combine them, put the bank inside the higher byte and put the number inside the lower byte, right? To do that, let's say we have the first bracket here for the higher byte, and we will do OR with the lower byte, that is the num. So whatever we get, we will OR it with the num. We want to put whatever value that we get into the higher byte, right? So whatever we get here, we have to shift it to the higher byte before we OR it with the number, so that the pin number will occupy the lower byte and whatever we get here will occupy the higher byte. So inside here, we want to get the bank and we will subtract A from it, so that, for example, if we are dealing with GPIO A, then the bank will be 0. If the bank is 0, for example, we call the GPIO, we pass 0 in, it will return GPIO A peripheral. We will create two macros that when you pass, let's say you have a pin, right? A pin that consists of the bank and the pin number. When you pass that pin to it, the pin number macro can subtract the pin from it, and also a pin bank macro that will subtract the bank from whatever pin you pass to it. You should find a way to separate the pin number from the pin bank. Let's call this pin number, and pin number is going to take pin, and we know that pin is occupying the lower byte, right? So when we end it with 255, you can do this, okay, or you can also end it with this and it should give you the same thing. Then we will make the macro for the pin bank. The same thing, you pass pin to it and this pin bank is going to get the higher byte, right? So you shift it 8 bits. Once we have these macros, we can create a more sophisticated form of the GPIO set mode. In the new function, instead of passing a pointer to the GPIO struct and giving it a pin number and the mode, we can just give it a pin and mode. So when we go inside, we can use our macros to get the pin number and the pin bank from the pin that we will pass to it, and we can do the same thing, right? Let's write it and see how it will work. I'll just copy and paste this. All right, let's call this mode X, more like a superior mode X. We don't have this anymore, and now we are using 2 for this all that we have. So here we will call the struct GPIO, a pointer to GPIO struct, and we are calling the GPIO macro to return the GPIO instance that we want. Now this requires a bank, right? Now we have a macro that will give us the bank, so let's call the pin bank here. The pin bank requires a pin that is 2 bytes, and it will shift it right 8 bits, and it will return the bank that we want. All right, we will pass the pin to it just like that. Once we do that, we are good. Now the new pin that we form, we put the pin number inside the lower byte. All right, so we will get the pin number. Let's just name this N to avoid confusion. So this one we will call the pin number here, and the pin number requires a pin that is 2 bytes, and it will get the first byte. So we pass the pin to it, and easy, uint 8. Now if you are wondering how we are going to use this and how you create this, to create this pin is very easy. So when we come here, we can do uint 16, right? Let's say we want to create pin A7. All right, how are we going to do it? Our macro is here. We pass the bank and we pass the number. We said we are interested in pin A7, that is GPIO A pin 7. So we pass our bank here and we pass the pin number here. Now you see how easy it is, and this is why using hardware abstraction layers is very important in embedded system, because you don't want to be calling the registers at every point. Right? What if you want to create, let's say, GPIO B pin 13? Okay, so we do this as usual, 2 bytes, pin B pin 13. So all that we have to do is we pass B to it and number 13. Okay, So once we have our pin like this and we want to set the mode for this pin, we need to call this function. This is how we are going to do it. We call GPIO set mode X here, right? We pass pin A7 to it and whatever mode that we want. GPIO analog mode. Now you see the mistake that we made here. We are calling this pin A7 and we are passing AN7, but we forgot to call the macro that is supposed to create it. This is the macro, right? Put the macro right here and put the macro right here. Yes, we need a here. Now this is giving us red because we are calling it outside main function. You know, to run C program you need to call it inside main, and we are calling it here, so I don't really worry about it. Now this is a very good foundation for what we are going to do next. We are going to look at how the boot system works. We will write everything, how we are going to compile this. Hello everybody, let us look at interrupts and how the MCU boot. Interrupts are signals that temporarily pause the normal execution of a program, diverting the CPU to execute a specific function called interrupt service routine or interrupt handler. They allow the microcontroller to respond to events that require immediate attention, such as hardware triggers. If you look at the diagram that we have here, there is a button. When the button is pressed, the person pressing the button is expecting the CPU to execute something, right? So during hardware triggers or even software generated events, interrupts play a crucial role in ensuring responsive system behavior, especially in embedded systems. In this diagram, we have CPU here representing our microcontroller unit. Inside the microcontroller unit, it has a program counter. The program counter is responsible for moving to specific instruction to be executed. Now, when this button is pressed, the corresponding interrupt service handler from the vector table is loaded and executed. So a vector table is nothing but a structure that contains interrupt handlers. So you can see them as addresses to specific interrupt routines that we need to be executed. The MCU boot process and the vector table are very simple. When an ARM microcontroller powers on, and typically most microcontrollers, it reads a structure called the vector table located at the beginning of the flash memory. When we look at the CPU, we said that the CPU contains flash and RAM and other stuff. This table holds 32-bit addresses that corresponds to interrupt handlers. 1, 2, 3, 4. They are 32-bit addresses. Why? Because we are dealing with a 32-bit architecture. Now, the vector table begins with 16 standard entries defined by ARM, and this is common across all ARM-based microcontroller units. These entries handle core exceptions like reset, fault handling, and system interrupts. The remaining entries are specific to the microcontroller and correspond to peripheral interrupts, such as timers, communication interfaces, and GPIO interrupts, right? So let's say if you get Atmega or you get STM32, all these are built on ARM, but they support different peripherals. Some might have 5 GPIO instances, some have 3 UART instances. Yes, but across all ARM MCUs, there are 16 standards. STM32 F429, it has 91 peripheral interrupt handlers in addition to the 16 ARM standard entries. Each entry in the vector table points to a function that is executed when corresponding interrupt occurs. All these interrupts, they are addresses that are pointing to a function that needs to be executed. However, the first 2 entries are very essential to the boot process. So in respect to our diagram, it will be interrupt service routine 1 and interrupt service routine 2. The first interrupt service routine that is placed on top of the vector table is the initial stack pointer. This defines the address that initializes the stack pointer. And the second interrupt service routine is the reset handler. This one contains the address of the firmware entry point, the function executed when the MCU boots or resets. So we have to be careful here. To ensure correct operation, the firmware must correctly populate these entries, particularly the second entry. What is the second entry? We said the second entry is supposed to be a reset handler. It needs to be there as the microcontroller jumps to this address to begin execution during the boot process. We are going to write firmware that will load all these interrupt service routine into their proper place in the flash. I want you to go back to your VS Code. We will start with a reset function. Now inside here, infinite loop. The next function I will write will be pointer stack. This will be defined from the linker script. We will create this file later. The next, we will define the 16 standard and the 91 specific interrupt service routine handlers. I'll call session. Inside the session, vectors contain 16 plus 91. So inside this, we call the e-stack and the reset function that we created above. Okay, so this is constant, make it S. This code snippet represents the minimal startup code for an STM32 microcontroller. It defines the initial entry point of the program and it set up the interrupt vector table. As you can see something here, vector. The reset function. Inside here, naked and no return. They are keywords from the GCC compiler. It specifies that this function does not return and does not use the usual function prologue epilogue. Inside this reset function is an infinite loop. It prevents the program from continuing execution as no actual initialization or logic is present yet. We've not done that. When we go to the next code fragment, it declares the external symbol e-stack, which is defined in the linker script. We are going to write a linker script soon and we will define that. Now, this typically points to the top of the stack memory. The next code fragment, which you can guess, it is creating a session in the memory and calling it what? Vectors. It places the table in a special memory session called vectors. What table? The vector table, as we already discussed. The tab is an array of function pointers that represents the interrupt vector table. The first 16 are standard, the rest depends on the MCU that you are using. Inside here, we are calling the e-stack and the reset. It means that the first entry e-stack, it defines the initial stack pointer address. The second entry reset, it specifies the reset handler, the function executed when the microcontroller boots or reset. There will be other entries, okay, but the remaining entries can be filled with pointers to standard exception handlers and STM specific interrupt service routines. This forms the foundation for initializing the system that we are building right now. I hope you guys are ready, because in the next video we are going to write the linker script. We are going deep as we can, very low level. If you're afraid, maybe this is the point that you stop. If you are brave, why not? Come with me. Hello everybody. A linker script tells the linker how to map your program's sections like the test, the data, and the BSS to the memory layout of your microcontroller. Think of it as a blueprint that helps your code live in the correct places in the flash and RAM. Breaking down the linker script, there are four main parts. We have the entry, we have the memory block, the stack initialization, and the last part is the sections block. So this is what we are going to do. I want you to go to where your program was created and create a file and call it link.ld. Now in this file, we are going to write the linker script for our simple program. The first part is the entry, write entry, and inside entry, we will write our reset. And right beneath that, we will declare our memory block. Now, before we write the memory block, I want you to open your reference manual. I'm using the STM32 J0B1 RE board. From the reference manual, the starting address of the flash 0x08000000. That is a long number. Now, on the left right here, the RAM, which starts at 0x2000, then 4 zeros. In the linker script for the memory block, we are going to declare the starting address of our flash and RAM and also the size of each. When we scroll down, the starting address of the RAM was this, and it has a size of 144 kilobytes. On top of that, we have another section, but it's reserved. We will also look for the main memory flash that starts at an address of 0x08. It's right here. It has a size of 512 kilobytes. this is what we need to write the memory block of our linker script. Come back here. So we just write memory, just like that. You open your bracket and we can start with the flash. Inside here put IREX. I will explain in a bit, but more importantly we want to write the address. That is the starting point. Okay, go back here. This is the flash and this is the starting address. Let me just copy it. Let's paste it right here. Make sure you close the space. We will bring comma and we will write the size. Okay, instead of using size we will use length. Okay, so let's just write length, and the length was 512 kilobytes. On the next line we can declare the SRAM. Now inside the SRAM I will put RWX. Let's do the same, right? Origin, and let us copy the origin for the SRAM, the starting address. Copy it and let's paste it, remove space, and also the length is 144 kilobytes. Now if you are using a different microcontroller, just look at your reference manual and write these dimensions accordingly. The explanation is really simple. Okay, the first part is entry. All that we are saying is that we are specifying the entry point of the program, which is typically the reset handler. You remember when we were talking about the interrupt service routine, we said the second interrupt service handler in the vector table is reserved for the reset function. Exactly. Okay, so we are specifying the entry point, and we are also telling the linker where execution should start after the microcontroller powers on or reset. Now with the memory session right here, we are giving the starting address of the flash. Inside the flash we have RX. So the RX indicates that the flash is readable and executable. So whatever we put inside the flash can be read and it can be executed. Things like text and read-only data are stored inside the flash. What we are doing with the second line is that we are indicating the starting address of our RAM, and we are allocating amount of data storage for the stack. The RWX permissions allow for reading, writing, and execution. The next section is the stack initialization, and as we said, the RAM is for data storage and stack. So we are just going to point our stack to the last part of the RAM, so that when values are added, the RAM will keep on coming down, and when values are removed, the RAM goes back up. So right here is stack, and the origin will be our SRAM. We want to point to the last part and we bring a comma. Very easy. The E stack, as you can see here, is set to the top of the SRAM, which is the end of the defined memory region. The stack will grow downward from this address during program execution. So whenever you call a function will be placed on the stack. You call another one, it will be placed on the stack, and the stack keeps on growing downward. And when you remove item, it goes back to the highest point of the RAM. The next block is the sections block, and this is where we map specific code and data session to their respective memory regions. So quickly, I want you to create that block. Let's call it session and open a big curly bracket like this, and on top of it we will write vectors. You remember the vector table? Yes, we will write it here, and inside we will do this keep. Let's add two more parts here, and the last part will be the read-only data. Now what we mean by this is right here, the vector table, which holds the interrupt and the exception handlers, is placed on top of the flash right here. The keep directive ensures that the vector session is not discarded by the linker, even if it seems unused. So we are making sure that it keeps the vector table right on top. The dot test section, it holds the executable code, and the dot arrow data right here, it contains read-only data. For example, the constants that we are going to use, they are read-only. You can change them. Both of these are stored in flash memory since they do not change during runtime. Leave some space and let us write the data section. The data begins, it ends, come after the curly bracket, and SRAM flash This section, that is the data section, it contains initialized variables. During startup, they are copied from the flash where they are stored initially to the SRAM. Now, the SData, start data, it marks the start of the data in SRAM, and the end data, it marks its end. The add flash you see here, it ensures that the initial values are stored in flash. SI data here, it holds the flash address of the initial data used during the startup process to perform the copy. So when you are starting, the data is in the flash and load the data from the flash into the RAM. What about the values that you don't initialize straight away? Well, they will go to the BSS session. So let's write that. .bss. At the end of the curly bracket, we are putting this in the RAM. The BSS section, it contains uninitialized variables. These are placed in SRAM and are cleared to 0 during startup. Whenever you write a code and you just declare a variable like int age and you do not initialize it, you leave it like that, it will be set to 0. Underscore SBSS and the EBSS, they mark the start and the end of the BSS section. The last part of our linker script will be alignment. We will do .equal and we write align into bracket, we write 8. After that, we can bring this and we will end our linker script. The align ensures memory alignment for performance and compliance with the microcontrollers architecture. Now, if you go to the first video in the series, maybe you can see it right here. We said that microcontrollers come in different architectures. So basically, the linker script will organize your program in a way that matches the memory layout of your microcontroller. It places the code and constant data in flash. It initializes the variables in the SRAM, and it will set up the stack at the top of the SRAM. By understanding this, you can customize your linker script to fit your specific application needs, such as adding custom sessions or optimizing memory usage. If you found this explanation helpful, don't forget to like, share, and subscribe for more videos in our bare metal programming series. See you in the next video where we will load the linker script into our projects and test it out. A makefile is a script that automates the build process of your project. It defines rules for compiling source files, linking object files, and generating the final firmware binary, because we need the binary to flash onto our microcontroller. In your project directory, create a file and call it makefile. Make the M capital. Makefile has few parts to it. First, we will define some flags for the compiler. The compiler flags variables contains options for the compiler. See flags. The first part right here is targeting the ARM Cortex M0 processor. If you are using, let's say, M7, then you need to define it as such. The mTAM is just enabling TAM instruction set for better code density. The WAR enables compiler warnings, and the W extra enables additional warnings as well. So you might ask, what are the purpose of the flags? These flags catch potential issues early in the development process. The second part of the makefile, we are going to define flags for the linker. LD flags. tlink.ld, it specifies the linker script for memory layout as we have defined in our linker script. Now the last part, no std library, it prevents linking with the standard C library. After we have defined our compiler flags and the flags for the linker, we will include some libraries in our firmware. Define libraries. We are only adding 3 libraries here. The first one, LC, it is linking the standard C library. The second one, it is linking the math library, and the LGCC is linking the GCC support library. The essence of writing a makefile is to be able to generate a binary file that you would then flash onto your microcontroller. So these are the steps that we are going to go through to generate our binary file. We are going to build a target, that is the binary file that we want. Okay, firmware.binary. In order to get the binary file, we need a file that we call elf. Okay, elf file is when you have an object file and you link all the necessary libraries to it. And before we can create the object file, we need to compile the source code. The source code is this file, the main.c. So inside your main.c, make sure you've cleared everything with only this remaining. All right, go back to your makefile. we do build and we call this firmware.bin. Now this depends on an L file. Let's deal with the source file because we have it. We compile our source code into object file. The object file depends on the source code and small c here. This is the command from the ARM-GCC library, and this will enable us to compile the source code here into an object file. Now this sign represents our dependence and this $@ is representing our object file. The next stage here is that we'll add our links, right? The linker script and everything to this object right here. We are going to do that to create the elf file. At this point we need the elf file, right? So we do elf and the elf file depends on the object. The C flags already defined on top here, so that is no problem. The ARM command, and this is where we add all the external libraries and our linker script. That is, we define the memory segment, everything we add to the object file. Now we can generate the binary file. We can do firmware.bin and this depends on the elf. Okay, so with this command we are compiling the elf file right into the binary file that we want. We go to the terminal and we run make. Is going to give us the binary file, but before we do that we will just add a command to clean in case we want to reset, and also we add a simple command to flash the binary to the microcontroller that we are using. All the objects and the bin files that we created will be removed. The last line of code is to enable us to flash the binary that we create onto the microcontroller that we have. We are just calling the st32 and we first need to call the reset and we'll write it to this is the address of the flash. We want to know the details behind everything. We are not going to use IDEs, and because of that you need to install the st32. This is provided by ST company for flashing binaries onto the microcontroller. I have included the instruction for installing the st32 in the description, so whether you are using Mac or Windows or Linux, go ahead and install it. Once you are done, go to the terminal where your projects are, and at this point you can just call the make. Is going to compile everything. It will give us the object file right here, and more importantly it will also provide the firmware.bin. okay, so with this firmware.bin we can just call make stm flash. Once we run this command it will flash our bin program to the microcontroller that we are using. You can go ahead and do that. One thing I can also do, once you have the st2 installed, you can use the terminal to check the properties of the st that you have by using the st info probe command. So I have the STM32 F74 connected to my machine right now. This is the RAM and this is the flash. Once you flash the program, it will just show the bytes that were read into the flash, and there you have it. In the next video we are going to use all the knowledge that we have acquired and build our first Blinky project. Hello everybody, in this video we will bring together everything that we have learned so far to build our very first Blinky project. Now we will start by first defining macros for extracting the pin bank and other necessary configurations. Okay, the first macro bit allows us to write to any bit that we want. The second macro is allowing us to combine a bank and the number to form one variable. Now in that variable, the highest 8-bit contains the bank number right here, and the lowest 8-bit will accommodate the number, which means that if we have an LED that is connected to, let's say, GPIO A pin 4, the bank will be A and the number will be 4, right? Now once this macro is called, it will give us only one variable. When we have that variable and we want to extract the pin number, because the pin number is occupying the lowest 8-bit, we can end it with 255 to get the pin number. And when we want the pin bank, we can shift it right 8 bits to get the pin bank. Once we are done with defining the macros, we will define a structure to represent our GPIO peripheral. Now this will interact with the microcontroller's GPIO registers more effectively. As we have done throughout this series, look at your reference manual, the structure of your GPIO peripherals and your RCC peripherals, and define accordingly. Now once we are done with defining the structure, we define a macro of GPIO, right? So if you want to work with GPIO A, here is going to be 0, GPIO B here is going to be 1, right? And since the GPIO registers, they are at offset from each other, as we have already talked about in this series, we just multiply the offset by the bank and it will increase accordingly. So depending on what you want the GPIO to be, we need to define the mode. So once we have already defined the states that our GPIO can take, then we will write a function that will allow us to set the pin to that particular state. It will be a static inline function. You will pass the pin and the mode. The GPIO set mode function will take as inputs the pin and the mode. The pin, as we defined in this particular macro, contains the bank and the num. We can use the GPIO macro and the GPIO bank to extract the particular GPIO peripheral that we are dealing with, right? So the first one will return the bank, and when we pass the bank to the GPIO macro, it will return the peripheral. Also, we can use the pin number to get the particular pin number that we are dealing with. Now once we are done, we can go ahead and first clear the area that we want to set, then we will set with this line. One thing that we have to note is that some microcontrollers automatically power and enable all the peripherals, that is from startup, but the STM32 is different. In order to preserve or save power, it doesn't power all the peripherals automatically, which means that to enable a peripheral, you need to allow clock to it. We have to create the clock peripheral, and according to my microcontroller, the clock, as we discussed earlier on, is the RCC peripheral. So let's define that. Now to define the clock peripheral, let us take a look at the reference manual. I will search for RCC. Now these are all the registers for the RCC, starting from the control register to configuration register up to this part, clock configuration register, right? So we are going to define all these registers and look at your particular MCU and define the same. I'll close this and we'll write strat RCC. Don't forget to always use the volatile because you're accessing memory. The first one is the CR. Okay, that is for the struct, and we will define the macro RCC. Now we are going to cast the address to this peripheral. Let's check the memory map. Okay, so this is our RCC and it has this address. So go ahead and copy and just put it in here. Okay, now we can use the RCC to enable the GPIO or any other peripheral that we are interested in. Since we are going to blink an LED, we need a function that is going to write to a particular GPIO pin, right? So this function will allow us to toggle the LED on and off. This is going to be static inline function, GPIO write. You pass the pin and also a bool. So first we will get the GPIO that we want to write to. Now once we have the GPIO peripheral that we are dealing with, we can call the bit set reset. Depending on the boolean that we pass, we either write to the first half of the register or we shift it left 16 so that we go and write to the second half, which means that we are going to reset the particular pin that we are dealing with. stdbool right here, yes, and we are good to go. Inside the main function, that is where we are going to call all these functions that we have defined above, whether we want to set a particular pin as output or input. And also we go inside the loop and we will switch on or off the particular pin that we are dealing with. So come here and let's write the main function. Now we come here and we define our main loop. This is where we will write to the GPIO that we want. So we write LED true. In this code, we are putting the LED on and we are putting it off. But we can see there is no delay in between here. So the switch will be too fast that we will not be able to see. Let us define our own delay up here. So come here and write static inline delay. We just pass a counter to it. So we are not doing anything particular with this function. Whatever value we put up here, it will loop until the value gets to 0, okay, providing us a delay. So in between this, we can call delay and we can put in, let's say, 100,000. Now before running this code, we need to modify the startup code. Since we have added new data to our program, as you can see, we must ensure it gets copied to the correct place in the RAM region for execution. So come down here and inside the startup code, let us go ahead and define the BSS and the data section. So if you have not watched that one, take a quick look. It's part of the series. Start BSS session here. Okay, so with this code we can see we are defining the start BSS session and BSS session, the start and the ending sections of the data, and we are making sure that we are moving the BSS to the RAM. Once you have this, that will be all for our Blinky project. You can go ahead and run makefile in your terminal. Thank you so much for watching this long series with me, and I really hope that you guys learned a lot. Bye. See you in the next video. The flowchart of the program is going to be very simple. When the program starts, it will first read the state. Once the state is off, it will turn the red LED on. If the state is on, it will turn the blue LED on. After that, the program will sample ADC signals depending on what we want, and it will put it into a buffer. After the buffer is filled, we will transmit the signals via UART, and we can read the UART maybe using our terminal, and the program will keep on looping forever. On the other side, we can write a simple Python script to read the UART values, that is the sent ADC signals, and put them into a CSV file, or we can just open the terminal and read the UART values. Now go ahead and open your STM32 CubeIDE. We go to File, we are going to create a new STM32 project. Okay, the project has loaded. I'll be using the STM32 Nucleo G0B1RE board. So right in this test board, I will search for Nucleo G0B1. That is my board. Select here, then it appears down. You click it and next. Project name, new project. Now on this part, make sure you select empty because we are going to start everything from scratch. C, executable, we click finish. When a new project is created, it gives you these directories. First, the includes directory, and now we have this include source and startup. The source contains the main file. Let's open it. It presents us with this as the main file. So mostly I will go ahead and clear all these just to make it a little bit neater. Now because we'll be using 3 peripherals, I like to organize my files as such. So in the source file, first go to new. You want to create a new source file. And this will be the source file for the GPIO. So I'll call it gpio.c. Finish to complete. Let's create another source file for the usart. Let's call it usart.c. Finish. And the last source file we will create is adc.c. Once we have the source file, go to the include directory and let's create the header files for the source file we just created. So now new header file. We use the exact same name. So now we create gpio.h. Finish to create. We create for the others as well. Header file for the adc.h. Finish. And also for usr.h. This is going to be how our project will be structured. So within the main file, where we call our main functions, then the registers for the ADC will go into the adc.h. The registers for the GPIO will go here, and the registers for the usr will go into the usr.h header files. Then in the source files, we will implement the respective functions. Now open your datasheet and search for block diagram. The block diagram shows all the peripherals of the specific board you are connected to. As I said earlier, in this project, we'll be using the GPIO peripheral, ADC, and UART peripheral. Because of that, let's pay a closer attention. The center of this block diagram is the RCC, which is the source of clock. All the peripherals are connected to the RCC. When you go to the GPIO peripherals, it houses the port A, port B, port C, port D, port E, and port F. Each port has 15 pins. So depending on which port you use, if you want to use a pin in port A, then you need to allow clock access to port A peripheral. Likewise, you do for the others. In order to use a particular peripheral, first you need to allow clock access to it. Then you get the address of the peripheral. From the address, you use the offset to get the specific register you need to read and write. Most of the time, when you are dealing with bare metal programming, all that you are doing is you are writing or reading from specific registers of a particular peripheral. If we are dealing with ADC peripheral, then we go ahead and get the registers necessary to modify. So if we are reading and writing from ADC peripheral, then we have to get the reading register or the writing register. From this diagram, we have the RCC, which is also the source of clock. We'll be dealing with the GPIO peripheral. Now, when we move a little downward, we can see the ADC peripheral right here. Now, the ADC peripheral is connected to the APB bus, and the APB bus connected to the clock control. Also, we will work with the UART. You can see right here, we have all our UART peripheral. Now it is written USART, which is not different. UART is Universal Asynchronous Receiver Transmitter, and the USART is Universal Synchronous Asynchronous Receiver and Transmitter. So that is what we are going to use. Now one thing that we also need to take a look at is that all the peripherals are connected to the clock source by means of buses. The ADC is connected to the clock source by means of this APB bus. Also, the USART peripheral is connected to the clock source by means of this bus. The GPIO, on the other hand, are connected to the clock source by means of the IO port bus. Now the reason this is important is when we want to get the address, it will be easier for us to look at the specific buses. So now I want you to open your reference manual. Now in the reference manual, you can go ahead and search for memory map. This is the diagram you are looking for. To get the address of any peripheral, you need to take a look at the memory map. From this diagram, we can figure out the address of any peripheral we want to work with. First of all, we are more interested in this section of the diagram, the peripherals. Now it is extended here on the right. The base address of the peripheral is this UX4000000. Now we can see the peripheral is divided into these sections, and if we remember from the block diagram, these sections are also the buses, right? So APB here, this part showing brown, it means it is reserved. No peripheral is used over there. Now APB bus, AHB, and IO port. If we go back to the data sheet, we could see the GPIO peripherals are connected to the clock source by means of the IO ports, right? So when we look at the memory address, let's scroll down and let's see the IO port bus, how we can figure out the GPIO peripherals. So we scroll down. Now on this side we have bus and we see the IO port. From the IO port section, it starts with the GPIOA, now GPIOB, GPIOC, GPIOD to F. If we want to address, for example, GPIOA, this is the address that we are going to use, right? Now, what about the ADC? The ADC is connected to the APB bus. So we go back to the reference manual. Let's look for the APB bus. The APB bus starts from here. We should find the address of the ADC peripheral. Okay, this is it. The ADC peripheral, and the starting address of the ADC peripheral is this, which means that if we want to get the address of the ADC, this is it. Once we have this address, we can go ahead and find all the registers within this ADC peripheral. When we go back to the data sheet, the USART peripheral is also connected to the clock source by means of the APB bus. So back to the reference manual, let's look for the USART. Okay. Now we have USART 5432. You can use any of them. We will be using USART 2, and this is the starting address. It is important that you understand the block diagram because we are going to use it a lot. It gives you an overview of the connections of the particular board or MCU you are using, and it shows all the peripherals available. So let's say you need to work with SPI. The SPI is connected to the clock source by means of the APB bus. If you need to work with I2C, you can see the I2C is here. Once you know where the peripheral is connected, you can go to the reference manual, you search for memory map, and you get the specific address. I'll go to include directory. Let's create a new header file. We call it base.h. This header file will contain the base address of our peripheral. Open your reference manual and go back to the memory map. We can see the peripheral and the base address. Copy the base address of the peripheral. Go back to the IDE and we define here the peripheral base. Make sure you remove the space. Now we have the first address of the peripheral base. When we take a look at the diagram, we see the buses are for the sections of the peripherals. We have the APB, we have the AHB, and the IO port. Let's define these three sections, starting with the APB peripheral. Now, what we are going to do is, instead of defining directly the addresses of the peripheral, we will find offset of each peripheral relative to the base address. We start with the APB peripheral. We can see the APB occupies the base of the peripheral, which means the offset is going to be 0. Now we come here and we define APB peripheral offset. Because it's occupying the base, it's just going to be 0. Once we have the peripheral, we can just write APB peripheral. You have the offset. We will add peripheral base to the APB peripheral offset. We will do this for the rest. Back to the reference manual. Now we have the APB address. We can get the AHB. AHB address starts from here. Copy it. Go to the IDE. First, let's define the offset. AHB peripheral offset. First, we paste it, and when we look at the address and this one, we can see the offset is this 20000. So delete the 4 and write 0 instead, and make sure you close the space. We have the offset, so we can go ahead and write AHB peripheral and peripheral base plus AHB peripheral offset. Let's also define for the IO port peripheral offset. Take a look at the reference manual. This is the IO port and this is the address. Copy it. We go to the IDE. Now we paste it. If we want the offset, that is the difference between this and the base, you can see the difference will be 100. So we delete the 5 and we put 1 here and we close the space. IO port peripheral, and it will be peripheral base plus IO port peripheral offset. We are done with the 3 main buses, that is the APB, AHB and IO port. Now let's go ahead and get the peripherals. Open your data sheet and back to the block diagram. We said we are going to use the GPIO peripherals, ADC peripherals and the USART peripheral, which is right here. Let's get the address. Let's start with ADC. The ADC we said is connected to the APB bus. So we hide the data sheet and the reference manual. Let's scroll down to get the address of the ADC. We know the ADC is connected to the APB. Let's find APB. This is okay. APB start from here. So now this is ADC and the starting address of ADC is this. We copied this one so that we can find the offset. We come here and we define the offset for ADC peripheral. We want to know the offset of ADC from the APB, and we know that this is the address of the APB bus because it is also at the base of the peripheral. So we want the difference between this and this, and clearly the difference should be this part. We delete the 4 and put 0 instead, and we close the bracket. This is the offset of the ADC from the APB peripheral. Once we have it, we can go ahead and define the ADC peripheral address as this. APB peripheral plus ADC peripheral offset. Let's do the same for the USART. We said we are going to use the USART2, and the USART2 according to the data sheet is connected to the APB. Let's find it. Okay, we see USART5432. This is the address of USART2. Go ahead and copy it. Go to the IDE. Let's define USART2 peripheral offset. Let's paste the address. Now we want the offset, the difference between the USART2 and the APB. So looking at the USART2, which is 0x4 and the rest is 0, and this one, clearly the offset will be 4400. Delete the 4 and put 0 there and close the space. So now let's define USART2 peripheral so that this will give us APB peripheral plus USART2 peripheral offset. Now the next peripheral should be the GPIO. We know that the GPIO is connected to the IO port according to the data sheet right here. Now in this project we are going to use port A, port B, port C. Let's get the addresses of port A, B and C. IO port. Let's scroll down to find the addresses of the GPIO peripheral. This is IO port and we have A, B, C. We start with A. This is the starting address of GPIO A. We copy it, we go to the IDE, we define the offset for GPIO A. Now let's paste the address. GPIO A is also the same address as the IO port, which means that the offset is 0 right here. So we can close the gap and make it 000, or we can just keep 4 of them, right? Define GPIO A peripheral. So as usual, this is going to be IO port peripheral plus GPIO-A peripheral offset. The next one will be GPIO-B peripheral. This is the address. So we copy, go back to the IDE, we define the offset, GPIO-B peripheral offset. We paste what we have. So clearly the offset is going to be this 400, right? Make sure you delete the 5 and make it 0. You close the space. Now, just as with any hexadecimal numbers, the 0 zeros after a number is important, so that if you delete these zeros, the numbers will be different. So make sure you don't delete it. But the zeros before any number is not important. You can even delete this or let them be. Define GPIOB peripheral, and this should be IO port peripheral plus GPIOB peripheral offset. Then our last peripheral of the GPIO should be this, the GPIOC. Copy the address. And clearly we can see the offset is 800. We define GPIOC peripheral offset. We paste the address, we close the gap and just delete the 5, make it 0. Now we define GPIOC peripheral. So it should be IO port peripheral plus GPIOC peripheral offset. Now we have all the 3 peripherals we need. The next peripheral that we need to address, if you take a look at the data sheet, is the clock itself, which sits right here in the center. In order to allow clock access to all the peripherals, we need to address the clock itself. So now let's scroll to see the address of the clock. So the RCC is actually connected to the AHB bus, and this is the address. We can copy it. Now when we look at the base address of the AHB is 0x40020000, and this is the address of the RCC. So clearly the offset between the RCC and the base of the AHB is 1000. Go to the IDE and we define RCC peripheral offset. We paste what we have. Now this is the RCC and it's connected to the AHB. Clearly this is the offset. So make sure you delete the 2 and put 0. You delete the 4 and put 0. Once you have this, you can go ahead and define the RCC peripheral, which should be AHB peripheral plus RCC peripheral offset. These are our base peripheral, and the reason we put them in a separate file is that we will need to add this base file to all the other header files. Now let's run it and see everything is correct. So you go to this sign debug and we press it. You can see it built, finished, 0 errors, 0 warnings. Now that we have the base header file completed, let's go ahead with the GPIO header file. We start by including the base header file here. This is where we will get the registers for all the GPIO peripherals that we are going to use. Now let's take a look at the Nucleo 64 user manual. You will search for connector pinout. We want to see the pinout of the Nucleo board. This is the pinout of the Nucleo board that I have, and on top here you can see there is a blue button, that is the user button, and it's connected to PC13, that is port C pin 13. We will take a look at the schematic. Now in this project we will use one red LED light, one blue LED light, and the user button. The red LED light will be connected to D7. D7 is here, and D7 is actually pin 8 of port A. So GPIO A8, port A pin 8. We will connect the blue LED to D4, which is port B pin 5. The user button is already connected to PC13. Let's hide this. Let's look at the reference manual. Go ahead and search for the GPIO registers. It has a couple of registers. It starts with the mode register, and this register lets you define what a pin is supposed to do. For example, in our case, the red LED and the blue LED, they will all be output, right? So in the mode register, we will define the pin of that port A that we want to use for red LED, that is the D7. You will define that as output, and also we will define GPIO B5, that is D4 pin, as output. But the user button, which is connected to PC13, we will define that mode as input, because we'll be reading the input of the user button. Let's start with the mode register. Then again, once we define the mode of every pin, the user button, because we'll be reading the state of the button, we need to also get the input data register right here. So we need the input data register, and for the LEDs we also need to read the output data register. Apart from that, there are a few registers here. For example, bit reset and set we can use to write high or low to a particular pin, and we will also be using the control register. Okay, let's put this aside. Let's define GPIO A mode R, the mode R register, which is here. Let's search for it here. Okay, mode R register is a 32-bit register. So it starts from mode 0 to mode 15. Depending on the pin you want to use, you address the specific mode respectively. It has an offset of 0x00. First of all, we copy the offset, which is 00. Mode R offset is just 0x00. Define GPIO mode register. Now this is where we define the register, and we do it like volatile unsigned int pointer. Then we get the GPIOA peripheral, the peripheral that we defined in the base header file. Then we add the GPIOA mode R offset. Now we said we'll be connecting the red LED to GPIO A8, which is going to be an output pin. So because it's going to be an output pin, we need to get the output data register of GPIOA. Let's go back to the reference manual. Let's find the output data register. Input data register. This is the output data register, and it has an offset of 0x14. So we come here and we define GPIOA ODR offset 0x14, GPIOA ODR, GPIOA peripheral plus GPIOA offset. Now we can go ahead and also do the same for GPIOB, because we'll be connecting the blue LED to pin 5 of GPIOB, which according to the user manual is also labeled as default. Now we define GPIOB mode R offset. Now we shouldn't forget that the registers occupies relatively the same space inside the peripheral. Okay, so the offset is just going to be the same as the GPIOA mode R register. GPIOB mode R, the GPIOB peripheral offset. We can also go ahead and define the GPIOB ODR offset, which also 0x14, because they are the same registers, different peripheral. GPIOB ODR, GPIOB peripheral plus GPIOB ODR offset. We have 2 registers for the GPIOA and 2 registers for the GPIOB. We'll be reading the user button, which comes with the nucleo board, and that is connected to PC13. Because of that, we need to get the necessary registers for port C. Obviously, we will need GPIOC mode R peripheral plus offset. Because the GPIOC is an input button, we don't need to get the output data register. Rather, we need to get the input data register. Let's go back to the reference. The input data register is right here, and it has an offset of 0x10. Define GPIOC input data register offset, that is 0x10. GPIOC input data register GPIOC peripheral plus offset. Basically, we have all the registers that we need. For now, this is what we have for the peripherals. Later on, when we go to the UART, we'll come back here and add the alternate function registers, but we talk about it. The last register that we need to get is the RCC register. We go to the reference manual, and here we will search for RCC registers. Let's scroll down. This is the RCC register. We need a particular register from this RCC peripheral, a register that corresponds to the bus of the GPIO peripherals. And according to our block diagram, the GPIO peripherals are connected to the clock through the IO port. This is the IO port clock enable register. So we need this register. Let's go ahead and search for it. It is a 32-bit. If we take a closer look at bit 0 to bit 5, you can see to enable GPIO A peripheral, we need to write 1 to bit 0, and to enable clock access to port B of the GPIO, then we need to write high to bit 1, and likewise we do for the others. First of all, let's get this register. The offset is 0x34. We come here and define RCC IO port enabler, an offset of 0x34 enable register RCC peripheral plus RCC offset. When we go to the source file for the various header files, we will define all the enable pins. When I say enable pin, this is what I mean. For example, if we want to enable clock access to GPIOA, we will define a variable called GPIOA. We will store this bit in a variable so that we can use to set or unset this bit. We define our function prototypes here in the header file. Then we will write our functions inside the source files. A function to initialize our GPIO pins. A function to put on our red LED. Another function to put off red LED. A function to put on blue LED. Put off blue LED. LED toggle. Program state set, and we have to pass a pointer to the program state display, and we will pass the program state. That will be all for now for the GPIO header file. Go ahead and save it. We go straight into the GPIO source file. Open, include the header file we just created, gpio.h. Go and copy our functions. Let's copy them, bring them to GPIO here, paste all the functions and give the functions bodies, put some space between. So at this point, I expect you to have all these functions. First thing first, we start with a GPIO init function. Enable clock access to GPIO ports. Enable clock access to GPIO port A. Now, to allow clock access, bring back the reference manual and search for RCC registers. The RCC registers start from here. We need RCC IOP NER. To copy it, and let's search for that instead. Okay, let's see. This is the register that we want. We are going to define macro for these three values. And don't forget, the register is RCC IOP NER, which we defined in the GPIO header file. Right here, we define that register. Go back to GPIOC, and on top here, define GPIOA enable bit 0. Go ahead and define for the others. Once we have it, then we allow clock access GPIOA enable. This is how we enable clock access to GPIOA. Let's do for the others too. First, we allow clock access to the GPIO ports that we want to use. After doing it, the next thing that we need to do in initializing a GPIO port is to set mode of the pins. We are going to look at the GPIO mode register and set the particular pins that we want to use. Go back to the reference manual and search for GPIO mode R. It starts from mode 0, mode 1 up to mode 15. Bit 0 and bit 1 is for mode 0. Depending on the pin that you are using, you choose one of these modes. We are connecting the LED to D7, which is pin 8 of port A, which means that we will look at mode 8. If you want to set a pin as analog mode, you need to set the bits 1 1. If you want to use the pin as output, you set it as 1 0, and input you make it 0 0. We will connect our red LED to pin 8 of port A, and it's an LED, so it's going to be output, which means that mode 8, which represent bit 16 and 17, we are going to set bit 16 as 1 and we will set bit 17 at 0. Let's go back here. Mode R. To set a bit as 1, we use the OR operator. Bit 16. This time we are setting it at 0, so we have to use the AND operator. Bit 17. Let's write a comment. The next pin that we will use for the blue LED is the D4, and the D4 is connected to GPIO B5, port B, pin 5. If we look at the reference manual, pin 5 means that we are dealing with mode 5. We are going to use bit 10 and bit 11. Blue LED is also output, so we are going to set bit 10 to 1 and bit 11 to 0. Go back to the IDE, bit 10 to 1, and we set bit 11 to 0. Let's leave a comment. The last pin that we need to configure is for the input button. Port C, pin 13. We go back to the reference manual. Pin 13, which means we are dealing with mode 13. And mode 13, we are looking at the bits 26 and 27. We set it to 0 0. Let's come here. GPIOC mode R, bit 26, bit 27. This will be the basic configuration of our pins. Now if you like to see why the input button is on PC13, you can open the schematic of the Nucleo board, and when you scroll down here, this is the blue input button as I showed you right here. It's connected to PC13. Now that we are done with the GPIO initialization function, let us write the program to turn on the LEDs. Now to turn on an LED, you need to look at the output data register. Let's go back to our reference manual and we will find the output data register. This is the output data register which we have already declared in the GPIO header file. Now the red LED is connected to port A pin 8. Pin 8 is right here. We are going to do with this bit. So what we can do is we can define a name here, and I will call it GPIO-A8 bit 8, as we can see from the reference manual, bit 8. We can also define the blue LED port B pin 5, a bit for the input button. According to our diagram, we said the input button will be connected to PC13, pin 13. So let's define this. Define GPIOC13. So we go to red LED, and this time we are going to call the output data register as we defined here. To put on the LED light, we call GPIOA output data register, and we put on GPIOA8. We can do this, or one thing that we can also do is we can define red LED, and we set red LED to GPIOA8, blue LED GPIOB5, and we can also define user button, and we set that to GPIOC13. When we come here, instead of writing this, we can write red LED. This will switch on this bit, meaning our LED will go high. Now to put the red LED off, we just write GPIOA ODR, and we use the AND operator, inverted red LED. We go ahead and we do the same for the blue LED. GPIOB output data register. To switch it on, we use the OR operator, blue LED, and to switch it off, AND operator, blue LED. The LED toggle is for the onboard LED. The Nucleo board has an LED attached to port A pin 5, so we can define GPIO A bit 5. Then when we come here, we can define that as user LED. Okay, then we set it to the GPIO A5. We can use it here to toggle. We just write GPIO A output data register user LED. We need to simulate a delay. Other than that, the toggling will be too fast for us to notice. Yes, so once we do this, okay, we'll be able to see the toggle. It's an empty for loop. We want to simulate a delay. At this point, let us go ahead and write the code to set the program state and also display the program state. But before that, go back to the base header file and let us define the program state. An enumerator enum, let's call it state, and this enum will contain only 2 values. Let's set off to 48 and we will set on to 49. Now move back to the GPIOC, that is the source file. We are going to first of all read the input button, but I want you to open the schematic. Now according to the schematic of the Nucleo board that I'm using, the user button, which is connected to PC13, it is a pull high button, which means that if you've not pressed the button, that connection is always high. Once you press it, it goes slow, right? So we will know the button is pressed if it goes slow. Let us write an if statement here. We will check for GPIOCIDR, because already, as you can see from the header file of the GPIO, we have defined the input data register of port C. Go back to the source file and let's do end with the GPIO13. We can do it like this, or we can use user button as we define on top here. We define it here. We will dereference it, and if the program is off, if it is off, we will do something else. If on, we will do something. if the program state is off and we press the button, we want to change it back to on. And if the state is already on and we press the button, it means we want to change it. Program state, we set it to on, and likewise we set it to off. Don't forget, we are dealing with pointer here. That is why we need to dereference it here. Because this is running very fast, let us add a delay, LED delay, right? Let's write a simple function. So we have delay here. Let's copy it and add it to the header file. So go to the GPIO header file. Let's forward declare the LED delay. Now go back right here. After setting the program state to on, we call LED delay, and we also call LED delay. We can also decide to get rid of this and put the LED delay. Let's write the function to display the program state. State is off, red LED. State is on, blue LED. The program state is off, red LED on, blue LED off. Alright. Now, else if program state is equal to on, if the state is on, then we want red LED off, blue LED on. The next thing that we are going to do is to go to the main file and first call the GPIO init. Then we will probably call the LED toggle to see if the onboard LED on our Nucleo board is actually toggling. Before we run the program, let us add the onboard LED since we'll be using it to test. Now the onboard LED is connected to pin 5 of GPIO-A, which means that we need to set bit 5 to 10. So we are dealing with bit 10 and bit 11. So we set bit 10 to 1 and bit 11 to 0, the onboard LED. So we come here and set onboard LED, and it's going to be output GPIO-A, just like the others, mode R, bit 10 to 1, bit 11 to 0. Okay, so basically that is what we have for the GPIO pins. Okay, now come to your main file, and on top let's include the GPIO header file. Once we are done that, we come back to the main function outside the for loop. Then we call the function to initialize the GPIO pins, and we can begin by toggling the onboard LED as we defined in the GPIOC file. That is it. Let's change this to toggle instead. When we toggle the onboard LED, then it will call delay. Go back to main file. Let's build the program. Yeah, so the program built successfully without any errors. At this point, we can either click here to debug and it will open a debug interface, or we can just click here to run. After running the code, you can see the onboard LED blinking. Great. Now that we have been able to get the onboard LED to blink, we can go ahead and implement the rest of the program. First, we are going to read the program state, and we can comment this out. Before we do that, let us create a variable for program state, and let us set it to off. Created a state in the base, right here in the base file. We created a state for our program on and off, right? So we create a program state, and initially we are setting it off. First we call program state set, and so we will pass it a pointer of our program state. Then we also call program state display. We pass it the program state. We build with no errors. So after running the program, So from our LED board, when we press the user button, it changes the state. So now the program state is on, and when you press again, it changes to red. On, off. Now that we are done with the GPIO header file and source file, let us go directly into the USART program. So we will open the includes directory and go to the USART header file that we created. The first thing that we want to do here is to include the base header file, and the reason is that the base header file contains the USART2 peripheral. You can check it out. When we look at, you can see the USART2 peripheral here. So out of the USART2 peripheral, we will get all the registers, all the USART registers. Okay, go back to the USART header file. We are going to select few registers that we will need. We will need a couple of them. We will need the USART control register. We will need the baud rate register. We will need the ISR register, that is the interrupt state. We will need the receiver data register and the transmit data register, few of them. Let's start. Let us start by opening up our reference manual and search for USART registers. Okay, now when we search for USART registers, these are the USART registers. There's a couple of them. First, we are interested in this one. Okay, so let's copy this and search for the control register. Let's see. It is a 32-bit register, and from here we are mostly interested in this one. You can see this bit 0. Let's look at what bit 0 is. Okay, USART enable. Yeah, so we need to get this bit if we want to enable the USART. Also, because we will be transmitting and receiving data, we need to get bit 2 and bit 3. So bit 2 is receiver enable and bit 3 is the transmitter enable. So once we set these bits, it means that we'll be able to read or transmit register. Alright, just like we did for the GPIO registers, let us do the same for this. So the control register has an offset of 0x00 USART CR1. So go back to the IDE and let us define USART2 CR1. We will define the offset first, and this one has an offset of 0x00. Oops, let's make it small. Okay, once we have the offset, we can go ahead and define the register USART2 CR1. As with all registers, you reference it, you bring your bracket, then we write volatile unsigned int because we are addressing a memory location. Then inside here, what we need is the USART2 peripheral. We can go ahead and we go to the base header file instead, and we copy this USART2 peripheral. Copy it and go back to USART header file. Okay, so we can paste it here. Then we will add it to USART2 CR1 offset. Great job, we have our first register. The next register that we are interested in is the baud rate register. So we go back to the reference manual and let's find the baud rate. Yeah, this is our baud rate register right here. So we will copy it and search for that baud rate. Let's see, go through. All right, this is the baud rate register. It has an offset of 0x0c, so we can copy the offset and go back to the IDE. In here we will define user2 BRR offset, and the offset we've copied, so we can paste it. Now we go ahead and define the register itself. User2 peripheral plus user2 BRR offset. The next register that we will need is the ISR, interrupt state. Now the interrupt state will help us to know if let's say a data is ready in the receive data register, or even when we are transmitting, we will check if the TDR, that is transmit data register, is empty to transmit. Okay, so go back to the reference manual. Okay, all right, so we have the user interrupt and status register. We will copy this and search for it. Okay, and the ISR is a 32-bit register. Now the ISR is of two types. This is not what we need. Let's look at the other one. Okay, now this is what we need. We need this one. They have the same offset, so depending on the bits you want to address, you choose a particular one. Now here we are interested in the bit 5 and bit 7. Let's look at it. Okay, now bit 7 is transmit data register empty. So as I was saying, before we can transmit data, we need to do a while loop and see if this is empty. And the bit 5 is bit 5 is here, is the read data register, not empty. Okay, so before we can read, we need to make sure. So we are interested in bit 5 and bit 7, but first of all, let's get the register. We will copy the offset. Define user2 ISR offset. Okay, and we paste it. Now we define user2 ISR and user2 peripheral plus user2 ISR offset. The other two registers that we need is the receive data register and the transmit data register. Since we said from the ISR we need bit 5 and bit 7, let's define it straight away. So we can call it ISR, so RXNE, and also let's define ISR TXE, that's bit 7. Okay, we can put U here to make sure it's unsigned, that is a positive integer. Now before we get the next registers, let's go back to the control register and find the bits that, let's define the bits that we need. Okay, so let's see. Okay, this is control register 1, the one we've gotten, and we are interested in bit 0 bit 2 and bit 3. Let's go ahead and define those. So we CR1 UE, and that is the bit 0, right? That is bit 0. We define also CR1 RE bit 2, and we will define CR1 TE, and that is bit 3. All right, so we need this for the CR, that is the control register. We need it for the interstate register. All right, now the next two registers that we will need is the receive data register. So go back to the reference manual, find the receive data register. All right, right here. So we have the USART RDR. Okay, so we copy the offset as usual. Go back to the IDE and let us define USART2 RDR offset, and just paste the offset. Then we define the register USART peripheral plus offset. The next register, which is the last that we need, is the transmit data register. So quickly go back to the reference manual, and it's right beneath the RDR. It has an offset of 0x28. We copied that and go back to IDE and let's do justice to it. USART2 TDR offset. We paste our offset and we create the register. TDR offset. All right, we have 5 registers. So the next thing that we will do, as we did for the GPIO, is to define or forward declare our functions. So I'll just say function prototypes, right? Okay, now to the function prototypes. The first function that we want to declare will be void USART2 write. Okay, we are going to write and it will be void. The next one, your guess is as right as mine. USART2 read. Easy. Read. The next function that we need to also declare will be setting the baud rate. Set baud rate, and the set baud rate we need to pass the peripheral clock, right? Peripheral clock, we need to pass it a peripheral clock, and also we need to pass baud rate variable. Now they are all supposed to be ESP32 type baud rate, but most importantly we have to declare the function to initialize the USART, right? So we can go USART2 init, okay, and this will always be void. Inside the USART header file, we have these registers and these functions that we have declared. Before we leave here, let us go ahead and include, because we are using some numbers, we can go ahead and include stdint.h, right? Yes, it wouldn't hurt anyone. Once we are done here, we can move to the usart.c source file and write the definitions of all our functions and use the enables. Let's call this enable bits. Okay, we are done with the usart header file. So normally I will do as we did for the GPIO, is to copy the function prototypes, right? Copy them into the usart source file. We paste them before we give it body. I also prefer to cut the enables, that is the bit from here. Normally I don't like to keep them in the header file because I will be using them in the source file. So I cut them and just paste them here. All right, so the function prototype you only copy, but the enable bits we cut them and paste them here because we don't want them to be duplicated. Okay, now let's give them a body. Remove all the semicolon and give the functions bodies. All right, the first thing first, we are going to write the usart init function. But before we do that, I want us to first declare some macros that we will need for the baud rate. As you can see, the baud rate function here, we will be passing these two parameters, the peripheral clock and also the baud rate. Okay, so why don't we go ahead and define, first of all, we can define the clock. Let's call it peripheral clock. Okay, and the baud I'm using, it is 16 megahertz. So 1 2 3 1 2 3. All right, and we can also define the baud rate 5200. Yeah, so basically this is all that we need. We need the peripheral clock and also the baud rate. Now, one thing that we should notice is that I'm setting the peripheral clock to the system frequency, right? The board that I'm using, it has 16 megahertz for the frequency, so I'm setting the peripheral clock to it. Other than that, we can also do this instead. We can do this system frequency. Okay, maybe if you don't understand where we are getting this from, then we can put the 60 megahertz there. Then we will set the peripheral clock to the system frequency. I think this is more intuitive. Let's align them properly. Now we are here. How do we initialize the UART peripheral? Few things that we need to do. The first thing, as the GPIO, we need to allow clock access to the peripheral. So let's write allow clock access to usart2 peripheral. We also, after allowing clock access, we need to set the alternate function. UART uses GPIO pins. It will use one pin as a transmitter pin and one pin as a receiver pin. Because of that, we will need to set UART alternate function for the respective GPIO pins that we need to use. We get UART TX and UART RS. That's right, set usart2 alternate functions. Okay, and we will do this in the GPIO.c. Let's indicate it so that we don't forget. Now, after setting the alternate function, the next thing that we need to do is to configure the baud rate. Configure the baud rate and enable TS and RS transfer function in CR1. So when we got the enable bit, this is the bit that we are talking about. Okay, we can see the receiver and the transmitter. Okay, so we have to enable it in the control register. After doing everything, then we can go ahead and enable usart2 module. Right, let's begin with the first one. How do we allow clock access to the usart peripheral? The same way we did for the GPIO peripheral. But to refresh your memory, we open up our data sheet and search for block diagram. Okay, Now this is the block diagram for my development board. Yours might be a little bit different depending on the STM32 board that you are using. But for this one, this is where the USART peripherals are connected to the clock source. They are connected to the APB bus, right? And this is the RCC. So what we need to do is, let's open our reference manual. And in the reference manual, we will search for RCC registers. We want to get the register that is responsible for the APB, starting from here. But we are interested in the APB, this. If you remember, for the GPIO pins, we use the clock enable register. That was the RCC IOP enable register. But this time, because the USART module is connected to the APB register, this is what we need. So we have 1 and 2, but let's go there and see. We will search for that. Alright, we have this, and let us go through the peripherals here. So bit 0 is time 2. What we want is USART 2. We have USART2 right here. Now let us get this register, APB enable register 1, and this is the offset. So I'll copy the offset, go to the IDE. Once we have copied the offset of this register, okay, this register is responsible for allowing clock access to the USART peripheral. So go back to your IDE and go to the USART header file. We need to add that register. We define RCC APENR1 offset, and we can paste our offset. Then we will define the register. Define RCC APBENR. This time we will call the RCC peripheral that we defined in the base header file, RCC APBENR1 offset. Okay, we've already defined the RCC peripheral in the base header file. So when we go to the base header file, you can see we defined it here. All right, so we will leverage on that in the USART header file, and we create this register. Once we have it, you can come here and enable USART2. Once again, USART2 is bit 17, USART2 enable. Okay, so on top here, we can make some space and create that enable macro, RCC USART2 EN. Okay, and that is bit 2. All right, so here we can do RCC APB ENR1, then we enable the bit. So RCC USART2 EN. With this, we have allowed clock access to the USART peripheral. The next thing to do is to check out the USART alternate function. To do that, open your data sheet and search for alternate function mapping. It provides a table. Let's look for that table. All right, so this is the table. It goes down, but let's start from the top. So what happens is that USART is an alternate function stuff, and because of that, you need to assign some GPIO pins to it. When you look at this table, depending on the USART module that you are using, for example, we are using USART2. You can see USART2. It means that USART2 TX will be connected to GPIO port A pin 2. All right, and this is USART2 RS. So USART2 RS will be connected to port A pin 3, and you can see their alternate function is AF1, TS is PA2, and RS is PA3. First of all, go back to your IDE, and beneath it, let's make a comment. Once we've gotten this information, we will go to the reference manual. Now in the reference manual, search for GPIO registers. Now the GPIO has a particular register. These are my GPIO registers, but what I need is alternate function. You can see we have GPIO alternate function low register, alternate function high register. They are all the same, just that they are divided. Okay, for example, if you have a byte, we have least significant byte and most significant byte. So I will copy this one and search here. Is that phrase 2? It brings us here. This is the alternate function low register. If we look here, we can see it starts with AF SEL0, it goes up to 7. That is why we call it low. When we go to the next alternate function, it will start from AFSL8 to 15, so it's more like the most significant bit. Alright, now because we need pin 2 and pin 3 of port A, we fall within AFSL2 and AFSL3. So GPIO-A2, that is the TX pin 2 port A, we will configure it according to this, and our alternate function is AF1 as we've indicated here. So to set that pin to AF1, this is AF1, okay? Yes, so for pin 2 port A, we will set these bits from bits 8 to bit 11. We will set it to this, alright, which means that we will set bit 8 to 1 and the rest to 0. Alright, but first thing first, we need this register. It's a GPIO register and it has an offset of 0x20. So let's copy this and go to GPIO header file. I'm not sure we created this register, so we find GPIO header file right here. We don't have the register, so let's create it. Let's define offset. Go ahead and paste your offset value, then we can define the register itself. GPIOA peripheral that we have already declared in the base header file. GPIOA peripheral plus offset. Now go back to USART source file, and we've already looked at the alternate function, right? So we need to configure this in the GPIOC, not in the UART. We can choose to bring it here, but we don't have to. So now let's go to the GPIOC, right? And right here, let's make a comment, AF1. Now when we come here, alternate function for PA2, which is also TX. Alright, now let's go back here. We are setting bit 8 to 1, bit 8. We are done. The rest up to bit 12 we are setting to 0. We do for bit 11. We set bit 12 to 0. Now how did we know that this alternate function is AF1? Well, we looked at our data sheet. We searched for alternate function mapping, and in the data sheet it says that USART2TX is connected to pin 2 port A right here. So that is why we've configured it that way. Now let's do the same for this USART2RS, which is connected to pin 3 port A. Okay, so pin 3 port A, which means that now we are dealing with this AFSL3, alright, and we are setting it to this. Now we are dealing with which pins? Yeah, I think we made a mistake here. You can see it has only 4 bits. Yeah, I think it's a big mistake. You should notice. AFSL2, it spans from 8, 9, 10, and 11. Okay, we can't make that mistake. So let's delete this. You are not supposed to be here. Great. Only 4 bits. We are setting 4 bits. So now pin 3 port A, we are dealing with 12, 13, 14, 15. So we will set 12 to 1 and the rest we will set to 0. Okay. This time I'll just copy this and paste it, right? So we change 8 to 12. We change this to 13, 14, 15, right? So bit 12, 13, 14, 15. It corresponds to alternate function of GPIO pin 3. Let's leave a comment here. We've set the alternate functions of PA2 and PA3. Now go back to your USART. Okay, so basically we are done with this part. The next on the list that we need to do is to enable TX and RX transfer function in the control register. Now we already defined the control register in the USART header file. We have over here the control register, and when we looked at the reference manual, we said we needed bit 0, bit 2, and bit 3. We need to enable those bits in the control register. So let's do this first. Later on we will configure the baud rate. Okay, let's set the control register first. USART 2 CR1. We just do CR1 TE, then we will enable CR1 RE. We do this to enable receiving through UART, and we do this to enable transmitting. We can go ahead enable the UART module CR1 UE. Alright, we are done. Now what is remaining is configuration of the baud rate. We have already defined the parameters that we need for the baud rate, right? We've defined the peripheral clock which is picking from the system frequency. My board is using a 60 MHz internal crystal, and the baud rate we are choosing 115.200. Come down here and let's start with the baud rate. To define the baud rate, we need the USART2 baud rate. When we go back to the USART header file, we have the baud rate. Go back to the USART, and within here we want to set the baud rate. First of all, we need to get this peripheral clock plus our baud rate over 2u. The u is just unsigned int, and you divide everything by baud rate. Okay, all right. When we come here, we'll call this function. Okay, we call it here. Then we pass in the peripheral clock, which we have defined here, the macro, and the next parameter that we pass is the baud rate, which we have also defined. We have successfully initialized the UART peripheral. We started by allowing clock access to it, then we configured the alternate function, but we did the alternate function in GPIOC source file. Then we set the transfer function in the control register, we enabled user module, and finally we have set the baud rate right here. To write to UART, what we need to do is to perform a while loop on the UART interrupt state register. We can take a look at the UART header file, the interrupt state register. We can go ahead and write a comment. We want to write something, so we have to make sure something is written there. Once we are sure something is written, we can set that byte we've written to the USART transmit data register. Data transmit register. That is funny. All right, so let's perform while, and we can use while is not null, right? Now, if we take a look at our UART, we define it at USART2 ISR. So you can copy it and write USART2 ISR. Then we perform end operation with the enable macro that we defined. Okay, TXC ISR TXC bit 7. So we perform end operation with USART2 ISR. So ISR TXE. While this is not true, then we will keep on looping. Once we are sure it is true, then we set USART2 TDR. Once again, if you take a look at, we define the transmission data register right here. So once we are sure that this register is not empty, once we write something to it, this will evaluate to 1. Once this evaluates to 1, this will flip it 0, and the while loop will not run. We can come here and we will set this to what we've written. Because we are writing, we made a mistake in the write function. We are writing a character, okay? It cannot be void. Maybe we can make it a character or an int. Let's make it ch. Okay, there's a mistake. So let's go back to the header file of USART-H. Let's correct this, the USART write function. Obviously, we are writing something, so we need to give it a byte, okay, ch. Then we can get the first byte. We write 1 byte. So that is pretty easy when writing to the UART. Reading is no different. If you are receiving something, we have to make sure there is a value before we read. So we flip this, and once again we will use the USART to interrupt state register. Now this time we will perform end operation with the ISR, RX, and E. If you don't know what that means, we took a look at it, but you can check the data register. You look at the USART registers and you check interrupt state register, and you see TSC bit 7, RS, and E bit 5. We perform end operations here, R, X, and E. Okay, so it will only exit this loop when we have received something. Immediately we receive something, this will evaluate to 1, and this not will flip it. Then the loop will not run, then we can run the next code. Because we are reading something, we would like to return read data register, and I'm pretty sure we defined it here, right here. read data register. Okay, that was easy. So basically we have our USART source file ready. We defined the initialization process. We've written to UART, we've read, and we set the baud rate. All right, now the next thing that we will need to do, obviously we'll be reading analog data, right? So let's dive right into that. Hello, before we go ahead and write the ADC header file and source file, let us run our program. Okay, it looks like the program is compiling, but there is a mistake here. We are reading something, right? And we want to return at least a character. That is a bad mistake. So make sure you correct this and go to the USART header file and also change the return of this, the read. Okay, make it a character. Perfect. At this point, go ahead and open the adc.h. Just like with the other peripherals, with the GPIO peripherals and also with the USART peripheral, we are going to get some registers. I always say in a normal program, you will put all the registers of a particular peripheral into a struct, but we are not doing that. We want to get the individual registers that we need. And one thing, make sure that the USART, you include the header file. I realize it. Make sure you include it. And also in the GPIO source file, make sure you include the header file. Else when you run it, you might get a mistake. Now ADC header file, the first thing that we will do is to include the base header file. Once we are done with it, we can take a look at the data sheet. But already we've taken a look at it and we know that the ADC peripheral is connected to the APB bus. Alright, it's connected to the APB bus. Let's look for the ADC okay, let's see. ADC registers. Okay, ADC, the register should be here. Okay, yes, right here, ADC registers. The first one is the interrupt status register. Let's go there. So copy it and I'll search for, all right, okay, ADC interrupt and status register, and it's a 32 bits. Most of the bits are reserved. More importantly, we need this bit 2, and we can take a look at bit 2 is the end of conversion. So for ADC, before you can read the value and it has to be converted, this bit is set by hardware at the end of each conversion of a channel when a new data result is available in the ADC-DR register. So when you want to read ADC value, you have to first of all check this register and see if the conversion is completed before you can read. So we will create enable bit for this bit 2, but before we do that, let us get this register. It is at an offset of 0x00 ADC ISR. So come back here and let us define ADC ISR. First we define offset, okay, and the offset is at 00. Then we define the register ISR. We will call the ADC peripheral that we defined in the base header file. So if you go to the base header file, we define the ADC peripheral, ADC header file. So ADC peripheral plus offset. Now we have the register. Let's define the bit ISR EOC, end of conversion. And the end of conversion was at bit 2. We will read this bit. Let's call this enable bits. When we are done, we will cut it into the source file. End of conversion EOC. That is the first register. The next register that we are interested in is the control register. The control register is always important because we will need to start the ADC module and also we need to enable it, and we do all of that in the control register. Okay, this is the ADC control register. It is at an offset of 0x08, and when we take a look at the register, it's 32 bits from 0 to 31. Most of the bits are reserved. But right here we are interested in the ADEN, enabling ADC, and also ADC start. Let's take a look at it. Bit 0 ADEN, that is ADC enable command. This bit is set by software to enable the ADC. So for this to work effectively, we need to write high to that bit. The ADC is effectively ready to operate once the ADRDY flag is set. So now let's get this, and also the ADC start conversion command. It's also set by software to start the ADC conversion. So we can see it flows. First of all, you need to enable ADC, right? You have to start it to allow conversion, and before you read the ADC value, you have to check end of conversion using the interrupt state register. So most of the time, the interrupt state register either is ADC or USART or any GPIO is there for you to check it when something is done. So you get these 2 bits, but for now the register is at this offset. We can copy it, go to the IDE and CR offset 0x08. Then we define the register ADC peripheral offset. Perfect. Now I said the 2 bits that we will need at least for the start is bit 0 and bit 2. Later on, for example, if we need to calibrate the ADC, we could even use this. But for now, we will use the default calibration. So let's create a macro for ADEN and AD start. We define ADEN bit 0. We also define CR AD start, and that is at bit 2 registers. We will also need the configuration register, and we will need the channel selector and the data register itself. Let's take a look at the configuration register. Go back to your reference manual and okay, so we have the configuration register here, and what we need from the configuration register is bit 13, and sometimes you can choose to align the values, and also we can choose to set the scanning direction. For example, if we are using multiple ADC, so about 3 pins, they are all ADC values which are being connected by different sensor modules, and we want to scan them in a particular direction. Okay, let's say we have a thermometer, we have heart rate monitor, and we have a variable resistor value, and we want to read the values in a particular order. We could use the scan direction. But for now, let's take a look at bit 13. Okay, this is continuous or single conversion mode. If you set it to continuous conversion, it means the ADC keeps on converting. If you set it to single, then it converts to a particular point and it stops. So as we can see, this bit is set and declared by software. If it is set, conversion takes place continuously until it is cleared. All right, let's get this register. ADC CF, let's copy it. Offset 0x0C. So we define the offset A. Okay, let's paste what we have. 0x0C, and we define the register, then ADC peripheral plus offset. Now that we have the register, let us look at the bits that we will need. We said we would take bit 13. Bit 13 is this. Let's create a macro for it. Define cont bit 13. The next bit that we need is the channel selector. A quick look at my dev board, can see it has analog and digital pins. So right here we have A0, A1, A2, A3 and A4. Now those pins, you can set the pin mode to analog. We are going to do that in a minute. We will do it in the source file. So once again, we will need the register to select which pin we want to use, whether we are using A0 or A1 or A2, and that register is the channel selector register. So we have ADC channel selection register. It is at an offset of 0x28. We copied this register. It is at an offset of 0x28, offset 28. Now from this register, we will need channel 0, which means that we will connect our ADC sensor to A0. That will be GPIO A0. We can just define channel select get bit 0. The next register that we need is the data register. So once the ADC has completed the conversion, the value can be found in the data register. So let's quickly go to the reference manual and look for the data register. Yeah, this is the data register. It is at an offset of 0x40. We get the offset. Go back to your IDE offset and we define the register itself, dr ADC peripheral plus offset. Now we need our last register. We need the RCC register that is responsible for enabling clock access to the ADC peripheral. Okay, let's look at the block diagram. Okay, so this is the block diagram. ADC is connected to the APB. Then let's go ahead and search for the RCC registers. RCC, it brings me to the RCC, but I need the APB. Okay, APB enable register 1. So let's see if we can find our ADC peripheral here. I don't see it. I don't see ADC. So if there is 1, then there is 2. APB peripheral clock enable register 2 and bit 20. Yes, so bit 20 is for enabling ADC clock. We'll get this register. It's RCC register. Let's copy it, come here, offset 0x40. Then we define the register itself, RCC peripheral plus offset. So more or less, these are all the registers that we will need for this particular project. You could use other registers. Once we have all the registers, let us forward declare our functions. With the ADC, we will need to initialize the ADC peripheral. We will need to do conversion. It reads the ADC value, it needs to convert it first. We will need to sample the ADC and we want to transmit the ADC. So we read the ADC from whatever sensor is connected to it, then we will transmit it via UART to the computer we are using. So let's write the functions. First we will need void ADC init, ADC conversion, right? The next will be ADC read. The next function will be sample ADC signal. So in this function we would like to pass a buffer to it, and also we will give it a pointer to our program state. The next function is to transmit signals. Just pass the pointer to the buffer. This is pretty much the end of the ADC header file, but as usual I like to cut the enable from the header file. I like to take it from here and move it to the ADC source file. I paste it, and in the ADC source file we should include the ADC header file. Then I go back to the ADC header file. Let's copy the function prototypes here, ADC, and paste them. Now we can give them bodies. This is where we are going to define them. Let us start with the initialization. Now we have our ADC header file set and ADC source file. So when we created the RCC APB ENR2 register, the register that is responsible for enabling clock access to the ADC module, we said we needed bit 20 as is indicated over here. So let us create the macro to store this. Let's define RCC ADC enable, and that is bit 20. A few steps are required to initialize ADC module. First, we need to allow clock to ADC module. After allowing clock access to the ADC module, what we can do is, and because we will connect the ADC module to A0 as I showed you guys. I mean, you can choose A1, whatever it is. Because of that, we need to set GPIO A0 mode to analog. Okay, at this point we will go to the GPIO source file and do that configuration. After setting that, we can go ahead and set data resolution. Now once we go into the configuration register, we will see that the ADC can convert values in different resolutions. With this particular board, it can give you values in 12-bit, 10-bit, or 8-bit. The lower the data resolution you are picking, the faster the sampling rate. So after setting the data resolution, you select the channel in the channel select register. After selecting the channel, we can go ahead and enable the ADC module, which most of the time we do in the configuration register. Now, to allow clock access to the ADC module, we will use the RCC register responsible for the ADC module, and we have declared it over here, right? This register. Go ahead and copy it back to ADC source file. We can paste it, and as we always do, we enable that bit, and that should be RCC ADC enable. Now the next point, that is configuring pin 0 port A to be analog pin. All right, let's go to the GPIO source file here, and let's give a comment. Set GPIO as analog mode, right? Go and get your reference manual, and here we will go for the GPIO registers. With the mode register, depending on the pin you are using, you have to choose one of these. Because we are setting pin 0 port A as analog pin, we are dealing with mode 0, and mode 0 occupies bits 0 and 1, and to set it as analog, we need to set both bits to 11 GPIO mode R register. And since we have already defined the GPIO mode register, and if you want to know, we define that in the GPIO header file. Go to the GPIO source file, and let's set mode 0 to analog. We are setting both bit 0 and bit 1 to 11. So we can write GPIO bit 0 to 1, and also mode R bit 1 to 1. All right, the pin mode is set. We go back to the ADC source file. This is set in the GPIOC. Now we need to configure the data resolution, and with the data resolution, we are going to use the configuration register that we have set. Let us go back to the ADC header file. We already have the register. We are going to use this. Before we do that, why don't we look at the ADC registers and see ADC registers. Let's check the configuration. Scroll to the configuration. Okay, this is the configuration register, and as we can see, bit 3 and 4 represent the data resolution. Let us scroll to bit 4 and 3 and see how we can configure data resolution. These bits are written by software to select the resolution of the conversion. Let us set both bit 3 and 4 to 10 bits. Go back to ADC source file, and let's call the ADC configuration to set bit 3 to 1, and then bit 4 we set to 0. All right, the next thing that we need to do is to select the channel that we want to use, and definitely with this we are going to use the channel selector register right here, ADC channel selector. Let's go ahead and copy this, and let's paste it. But how do we set the channel? We looked at the channel selector register, and actually you can see here we already selected channel 0. But still, if you do not understand, what we did is that we went to the ADC, we were in the ADC, and we looked at the channel selector. Okay, this is the channel selector, and you can see the channels ranges from 0 to 18. This lines up with the number of pins in each port, right? We are choosing channel 0. We have defined it right here, channel 0. We copy it, and let's just leave it like this. Now, to enable ADC module, we are going to use the ADC control register, which we have already defined here, ADCCR. And the ADCCR, we have gotten the enable bit here, ADCCR EN. This is all that we need to do to configure ADC peripheral. Now, how do we perform ADC conversion? The ADC module is reading a value, and it needs to convert it before we can use it. To do conversion, we are going to use the configuration register, set continuous conversion, and start ADC module. This is the configuration register, and we are interested in setting the continuous conversion to ensure that the microcontroller keeps on converting the values. So that was bit 13 right here, and we set it to 1 because we want it to do it continuously. We copied this, we go back to the ADC source file, and we already defined the conversion mode, which is here. Okay, we've already set it. We will paste the register. We've set it to continuous conversion. Once we are done, then we will call the ADC control register and set the ADC start. This is the ADC control register. You can see bit 0 is for enabling the ADC module, right? And bit 2 is for starting. Bit 0 to enable command write and to start. Go back to the ADC source file, and with the conversion we need to start ADC CR, and this time we will do the ADC start, which we have defined here, AD start. The ADC conversion function is done very easy. So let's go to the ADC read function, and with the ADC read function, always we look at the interrupt status register and see if, let's say, a value is available. Once a value is available, we return the ADC data register. Now, when we look at the ADC header file, we already defined the interrupt status register. And in the interrupt status register, we need to read a particular bit that will tell us if a value is available in the data register. And that value was the ISR EOC, that is end of conversion. We need to check whether the conversion is ready or not. I think we can use a while loop here. ADC ISR, we use and compare with the ISR end of conversion. As long as this evaluates to true, then we are stuck in the while loop, because if there is a value in the data register, then this will evaluate to 0 and the while loop will not run. It will go to the next line. Once there is value in the data register, then we can go ahead and return the data register. We are going to write the ADC sample function in a way that when the blue LED is on, then we go ahead and sample signals. Sampling signals means that we read ADC into the buffer that we have provided. When we are done with sampling, we will call the transmit signal and we pass a pointer to the buffer to it. Let's define few variables. Let's check the state of the program. If the program state is equal to on, let's create a pointer to the starting address of the buffer that we have passed. So I'll use the UART byte to read the ADC, and I'll use this byte 1 to get the first byte of the UART byte. Once our program state is on, we can do a simple for loop. Then we will use this UART byte and we will set it to ADC read. So once it returns this value, we will take the first UART byte. Let's do AND with 0xFF. So I'll take the first byte and put it into the buffer, byte 1. Alright, once the sampling is complete, we will call the ADC transmit signal and we pass the pointer. With the transmission, definitely we have sampled 64 signals, so we will transmit 64 signals. We will do a simple for loop here. We will call USART write, okay, and we will pass in buffer. We will do this. Since we are calling UART here, we need to include the UART header file, usart.h. Alright, this is what we have in the main function. We will just go ahead and read the analog signals. Inside the main loop, we will start by adding the header file. You add the adc.h and also we will add the UART. Okay, we will add these two header files. Then we will initialize. So we start with initializing the GPIO pins. Then we can initialize USART, USART2 init. After initializing USART2, we can also initialize the ADC init, ADC conversion. Alright, so when we come here, we can call the ADC sample signal, and this signal will take a pointer. So let us define a buffer of 64, and let's also just declare ADC value. We will use this value to observe the live expression when we are debugging. So we pass a pointer to the buffer and also the program state. Okay, then when we come here, we can just set ADC value. We can just set it to the first ADC value in the buffer. All right, let's just run this program and see what we will get. So click run. Okay, now I've connected the MCU, so let's click on debug. Okay, we have a live expression. So in the live expression, type the ADC value there. Type this ADC value so that we can observe it once it change. So now we are expecting the ADC value to change when we change the program state to blue. Let's go ahead and press this. So the initial state of our program is off. Okay, now when we press the button, it means we are sampling the ADC signals and we transmit to UART. So this is a live feedback. If we open the terminal, we can observe the UART being transmitted to the terminal. Once we press the button, our state goes back to off and you can see the ADC stops reading value. So it means that it is not sampling any value. Now let's press the button again. We press the button and the blue LED is on and you can see the ADC keeps on sampling signals. This will be the last session of the project, and I realized that the program was running. If we click run, it will compile with no errors and you can deploy the program onto the MCU. But I noticed that the UART wasn't working. So, and I mean this part, after we set the program state and also display the state with the LEDs, the program is supposed to sample the ACD and transmit them via UART. But whenever I checked the UART, I wasn't getting the necessary response. I went into the program and I saw in the GPIO, let's go to the GPIO source file here. So I noticed that although we set the alternate function in the GPIO AFR register, we also need to set the pin mode. We didn't set the pin mode. So let's pick our reference manual and go find the GPIO registers. We need to set the mode, and when I say the mode, I mean the mode for the UART TS and URRS. We need to set the mode to alternate function. GPIO registers. Okay, we need this. Now you can see alternate function mode because we are using GPIO2 for UART TX. According to our program, so we are using pin 2 port A as UART TX pin and pin 3 port A as UART RX, which means that we need to set them to this, right? Let's start with the first one, GPIO A2. So that is mode 2 and we will set the bits to 0 and 1. Let's set them to alternate function. So mode 2, the bits are 4 and 5. We set 4 to 0 and 5 to 1. 4. Then we set 5 to 1. Alright. As alternate function. Then let us set the pin 3 port A as alternate function. Pin 3 corresponds to mode 3, that is bit 6 and bit 7. So we do the same. You can just copy them, paste bit 6 and 7. So we change this to 6 and this to 7. Let's align them properly. So at this point you have this. A link to the project file is in the description. You can get all the code. Okay, let's go back to the main file and let's compile it. The program compiled successfully, no errors. Now I've connected the MCU right here, so I will go ahead and click the debug. Now we click on live expression. I've already input this ADC value. I want to observe how the ADC sampling will change. ADC value will just get the first number of the buffer. So anytime the program sample the 64 ADC values, this ADC value will correspond to the value of the first value in the buffer. So go ahead and click this one, resume, and immediately we click resume. You know, according to our program, the red LED is on. I hope you guys can see this, but you know, the red LED is on. If we press the button, the red LED is supposed to change to the blue LED, and the program is supposed to sample 64 ADC signals and transmit them to UART. Let's press this. Okay, and it has changed to blue, and as you can see from this side, the ADC values is constantly changing. So now what we want to do is open your terminal, and I'll use the screen command to open the UART of my device. This is the name of my device, and I'll put in the baud rate. Okay, yes, and this is exactly what we are expecting. As long as the state of the program is on, this will sample 64 and it will send it via UART according to when we go to the ADC. Yeah, so this is what we are doing right here. We sample and we transmit as long as this if statement remains true. Okay, so the terminal keeps on reading the characters. But if we press this and change the program state, it turns to red and it stops sampling. So now nothing is being sampled, right? Once we click again, it samples 64, send it via UART. Hopefully this project gives you an introduction to writing bare metal program on the STM32. Hello everybody, my name is Ebenezer Asabre. You can call me Asabre. Currently, I am a grad student at University of Massachusetts, Amherst, and my field of study is in electrical, electronics, and computer engineering. In this video, we will build an IoT home automation system using ESP32 MCU and a Raspberry Pi to track real-time data from temperature to pressure to air quality and light sensors. We will simulate the sensor values and send them over to the server. A Raspberry Pi acts as both an MQTT broker and also Node.js backend server, handling the data with PostgreSQL database and socket I/O. Every 5 seconds, the sensor data updates a live web dashboard displaying real-time plots. From the web client, you can easily switch sensors on or off. We have connected 4 LEDs and a servo to the ESP32 client. For example, turning the air quality sensor on or off will move the servo motor. The other sensors control the LEDs. Since all sensor data is saved in the PostgreSQL database, you can also query historical data with just a few clicks. For example, if you want to know the sensor data that was saved within a particular time, let's say between the last 1 hour and 5 hours. Now, before we dive into the demo, let's take a look at the hardware. As you can see from the screen, the hardware is pretty straightforward. We will use ESP32 MCU right here as the MQTT client. We will be connecting 4 LEDs to the ESP32 clients, and right here I have defined the pins, but of course you can feel free to use any pin that you want. I will be using the Raspberry Pi 3B model, but feel free to use any Raspberry Pi, it should work perfectly. I'm showing a laptop here for a reason, which is representing PC, because we will first build the NodeJS app on a PC. In my case, I'll build it on my MacBook, then copy it over to the Raspberry Pi. So you can just SSH into your Raspberry Pi to run the server. Alternatively, you can push the project to GitHub and clone it to the Raspberry Pi. Any way that you do it is fine. Now let us take a quick look at the demo. Now to the flowchart of the program. Right here, at the center of the project is a Raspberry Pi 3 Model B. It will function as the MQTT broker and also host the Node.js server. The ESP32 will be the client that publishes and also receives data from the broker. Now on the back end, we have a Node.js server that is running with a PostgreSQL database. Because we want real-time communication between the server and the web client, we are going to use Socket.io. If you don't know Socket.io, that is fine. It allows bi-directional communication between the server and the client so that they can communicate in real time, just as you would do with instant messaging applications. Now, how does this entire project work? Starting from the ESP32 microcontroller unit, it will read the sensor values and publish the sensor values via a specific topic to the MQTT broker, that is the Raspberry Pi. The broker in turn will take those values and publish them to other devices. Any device that is connected on that topic will receive that data. So MQTT protocol is very easy and efficient. That is why it's kind of popular in IoT frameworks. Now, when the MQTT broker gets the data, it will publish it and also it will save the data in the database. Once the data is saved, we can retrieve it later time either via the web client, or even if we build a mobile application, we can just send HTTP request and retrieve the data that has been saved. By the end of this tutorial, you guys are going to learn a couple of things. First, you will learn how to set up MQTT communication among devices. You will learn how to create a Node.js server and incorporate Socket.io for real-time communication. You will also learn to set up and manage a PostgreSQL database. If this is your first time of hearing about MQTT protocol, you shouldn't worry. The MQTT, as we simply call it, is a message queuing telemetry transport, right? It is a lightweight messaging protocol designed for small sensors and mobile devices in low bandwidth and high latency. So mostly it is used in remote places where the networks mostly are not reliable, and particularly is very important in IoT applications. MQTT follows publish subscribe model, where a client communicates through a central broker rather than directly with each other. So we have a broker which serves as a central point, and all the clients will be connected to the broker. So a client is the device that can, let's say, send message to the broker. For example, in our case, our client is the ESP32 right here. A client can also subscribe to a particular topic. Whenever messages comes in through that topic, the broker will send that message to those clients that are subscribed to it. A web application could subscribe to temperature topic to receive and display data in real time. In our case, we have MQTT client and also we have the web client. So the MQTT client will be subscribed to a particular topic. Let's say the topic is home/living room/temperature, and it will periodically publish data to that topic, right? The web client over here can also subscribe to that topic. So whenever the client, this one, publish the temperature data from the sensors, it goes to the broker and the broker will transmit it to the web client. Very easy. I've included materials in the description if you want to learn more about MQTT protocol and WebSocket. Let's go on. Let us write the program for the ESP32. Open your Arduino IDE and create a new sketch. We need to add the ESP32 board to the IDE. Go to Tools right here and go to Boss Manager. Search for ESP32 and you add it to the library. Once you are done, we need a pop sub client that is used for the MQTT protocol. Go to Tools, Manage Libraries. So in the Manage Libraries, type pop sub client. Can also install this. This will be the two installation that we will add. Leave some space and let's begin writing the code. Include wifi.h. We will also include the PubSub client, include HTTP client. We start by setting up the credentials for the Wi-Fi and the MQTT. For the Wi-Fi, we will need the Wi-Fi name, the password, and also for the MQTT, we will need the server. Now the server is whatever network your broker is connected to. For the broker, I'm using a Raspberry Pi, and the Raspberry Pi is connected to my own local network. Now if you have a Raspberry Pi and you SSH into it, you can do ifconfig to review the IP address. The next thing to do is to define the pins that we are going to use for the sensors. As we said, we have 4 sensors in this project: for temperature, for pressure, for light control, and also for air quality. This will be the pins for the sensors. We will set up the Wi-Fi so that the ESP32 can connect to the Wi-Fi network. Let's write a function here and call it setup Wi-Fi. It will return void delay for 10 milliseconds, and let's say we can print something connecting to something, the name of the network, and we will not leave this while loop until we are connected. We will call the inbuilt Wi-Fi while status is not equal to wl.connected. We will delay for about 500 milliseconds. If we are connected, then we can say Wi-Fi connected. Now we know that wireless connections can sometimes be unstable. We need to define a function whenever we are disconnected. The ESP32 will once again connect to the Wi-Fi. So let's just define something like reconnect. Loop until we are connected. In here we can do a while loop, and we call the Wi-Fi client. It's part of the library. Whilst we are not connected, we always attempt to connect. We need to call the ESP32 client. You pass this to it. We can print something. So once we get in here, we are connected. Other than that, we'll keep on looping. Once we are connected to the network, because we are dealing with MQTT communication, this is where we try to subscribe to a topic. In here, we can call the client.subscribe, and we will use this ESP-CMD. So that is the topic, which means that the broker also has to create this topic and publish it for the client to be able to subscribe. If we get to this stage, it means still we are not connected. So fail to reconnect. Maybe we can print the state of the network. We will wait for a few seconds. We want to wait, so we call the delay function for 5000. That is exactly 5 seconds. If connection fails, it will reconnect again. Now we are going to write a callback function, and it's responsible for receiving messages from the broker to the client. We know that the client can transmit and also it can receive. So we call this function callback. We will pass the topic, the payload, the message that is coming, and we will also get the length of the message. Whatever message is coming, we can get it inside a string. We can do for loop here, length. We can add everything to the string, whatever the payload is. So let's say if the broker sends something like put off the fan, we will get that and we will turn it into a string. Then we can print the message. So now we have the message. We need to handle the message. First, we need to make sure that the message is coming from the topic that we are subscribed to. We will check the topic if it is equal to what we have subscribed to, right? And top here we said we are subscribing to this topic, so in here we will do ESP/CMD. That is the beautiful aspect of the MQTT protocol. You subscribe to something and you are waiting for messages through that topic. Once this if statement is true, this is a string pointer. Let's convert it to a string. Okay, this is accurate. Okay, so once this if statement is true, it means that we've gotten a message from what we've subscribed to. We can print receive message. Now when we receive message, we need to call function to pass the message, right? We need to decode the message that is coming. Do this and we pass in the message. So let's come here and define the function. It will take a string as passed by the reference. Now the string that will come in will contain the name of the sensor and also the command. So let us find where the comma is, and we separate between the sensor name and the command. We call this comma index, and whatever string we get, we try to find where the comma is. So once we know where the comma is, we can use to extract both the name and the command. We create a string to hold the name of the sensor name, and we can use this Arduino command substring. We already have the index of the comma right here. So the first part of the string will be the name of the sensor, and as you are right, the second part is going to be the state of the pin, right? That is the command that we want. We will call this pin state, because basically all that we are doing is we are going to write a high or low to the pin that the sensor is connected to. So pin state is equal to string.substring, and this will be the command that comes after the comma. You will do this +1, and we convert it to integer. Once we have everything, we can print the sensor name and also the pin state. We have decoded the incoming string from the broker into the sensor name and the pin state. So we can go the next step and actually issue the command, right? We have 4 sensors, so we can make a switch statement, and we say that, for example, if the sensor name is temperature, then write the pin state to the temperature pin. This should be very easy. If sensor name is equal to temperature, digital, right, whatever value that comes in to the temperature pin. So we go the temp pin and you write the pin state. This should be easy. We will do it for the rest. We can also leave a space to handle unknown names that are passed, but we will leave that empty for now. That should be all for passing the string. So now we can come into the setup function of the Arduino code, setting up the serial.begin and 115200, and we can call the setup Wi-Fi function that we declared right here above, setup Wi-Fi. Now we can also set up the client for the MQTT set server inbuilt function. We call the MQTT server that we declare above, and it contains the IP address of the broker, and this is the default port that we use for MQTT communications. And we call the set callback. So in the set callback function, we pass in the callback function that we defined, which is this, receiving messages from the broker. Once we are done, we can also set up the pin modes. We will do pin mode. We set all the pin modes, and they are all outputs. That is all for the setup function. In the main loop, we try to maintain connection, or when we have a disturbance in the Wi-Fi connection, we will need to reconnect. So this is where we call the reconnect function we defined earlier. Inside here, we will check if the client is connected to the network or not. If he is not, then we call the reconnect function. Okay, and we will loop it. After making sure that our connection is intact, we can read the pins that the sensors are connected to, right? We could use analog in or digital in, but this time let us simulate sensor readings. So we are going to provide random values, right? So float temperature, let's give the temperature a value between 0 and 100, and we want it to be float, so let's do this divided by 100.0. We do similar things for the other sensors. This should work for simulating the values. Once we have the values like this, we will put the values inside a string, then we will publish it onto the topic. So the broker is already subscribed to that topic, and the broker is going to receive that. We call the payload, and we will use the inbuilt string function to turn the float values into a string. Once we are done, we can publish it. So we can do client.publish, and we need to indicate the topic on which we want to publish this. So we can call this sensors, and we call the payload. We use the inbuilt function str. We can also print to the serial. We call in the payload. Let's delay for about 5 seconds. So this means that we are going to send the sensor values every 5 seconds. If you watch closely, you can see something that we are publishing on this topic, right? But we are also receiving some values from the broker on a different topic. If you remember this, Okay, so in this instance, the ESP32 client is publishing and it is also receiving, because it is also subscribed to a topic from the broker. That will be all for the program on the ESP32 MQTT client. Let us move to the next. Let's make a few modifications to add the server code to the client. Go to Tools, Manage Libraries. Now I want you to search for ESP32 server. This will pop up. Then I want you to install it. Once you are done, so include ESP32 server.h. Let's instantiate it to my server and also declare a pin and call it server pin 13, just like that. Scroll quickly to the setup code and let us attach the pin to the server. Just call the my server object that I created, call attach, and into that function pass the server pin. Once you've done that, we want to create a function and call it run server. So this is a very simple function. It will return nothing, and the parameter, it will take int value. When the value is 0, we will write 0 to the server motor, but otherwise we will write 180, which means that whatever pin that we will attach to the server, if we turn it off on the web client, server will move to 0. You know, the server deals with angles, and when we switch the sensor that is connected to the server, then the server will go to an angle of 180 degrees. So once you are done defining this function, I want you to go to the pass string method that we defined here, and in the else if statement where the sensor name is equal to air. Now previously we had this code, digital write air pin state. Now this is supposed to toggle the LED that is connected on the air pin. Comment that and instead call the server and pass in the pin state. Whenever from the web client we turn the air sensor on or off, the servo motor will move to 0 or move to 180. Open your terminal. I'll be writing this on the Mac OS, but all the installations that we are going to do today, I will provide a link in the description where you can get the command for Linux terminal. But those on Windows, I think you can find a way to install PostgreSQL and also Mosquito. I'm going to use Homebrew. If you don't have it, I think you can install Homebrew on your Mac OS. So first, I will make sure that everything is updated. We will install the Mosquito, and the command is brew install Mosquito. Now the Mosquito is for the MQTT. So we will do this. We need to wait for a while for it to finish installing. Okay, our installation is complete. All right, it has given us the command to start this service. We can do that, but for now we need to edit something in the configuration so that it will allow us to have access to the server. If not, the server will not allow you to have access via the IP address. So let us do this. Mosquito. Okay. Password. Okay, so first we need to allow anonymous. We can remove this. Okay, and also we need to add a listener so that other devices can have access to it. So let's see, right above this, let us add listener 1883. This is the default port for MQTT 0.0.0.0, so that this will allow anybody on the network, the home network, to have access to the Mosquito. Once we are done, we can save it, and you can choose to edit with anything, but I prefer to use Vim. Maybe you can use Nano or something. At this point, we can start the service or restart it. Mosquito. We are done with this. The next installation that we need to do is to set up PostgreSQL on our system. Now, if you don't have Postgres installed, once again we can choose to update, brew update. Then we can do brew install PostgreSQL. Okay, so just like this, PostgreSQL, enter. Okay, we wait for a few minutes. It looks like our Postgres is already started. All right, these are the two main installations that we need to. The next thing is to create our Node.js application and do some small npm package installation. I have just created a folder called developer, and inside that there is a directory called server. This is where I'm going to write my code. As usual, to start a Node.js application, we can do npm init. We can press enter to accept the default. We will add get later, keywords nothing. Then maybe you can type in your name. Okay, so let's see. Okay, we need to make some few package installation. When you look at our diagram, you can see we are going to use socket IO, we use MQTT, we are going to use Express for the Node.js application, and also we are going to use a PostgreSQL. So go back to the terminal and let's do npm and install few packages. So we will install Express, HTTP, PG, and socket.io. These are the main packages that we are going to use. So we press enter and wait for the installation to be done. Perfect. Now to be sure, let us look into the package.json file. Okay, so Express is here, HTTP, PG, and socket.io. Okay, we need to also install a package for the MQTT. Alright, it looks like we have all the dependencies. Once we are done, we can open code from the terminal with this. So this is our VS Code, and these are what we have in the directory. Go back to the terminal and let us create some few files. We set in the npm installation that the index.js is going to be our entry file. So let us create a file called index.js. Now we need to make some few directories. First, we will create a directory called public. This directory will contain all the static files, that is the static web files that we want to show on the client side. We'll also make a directory called source. Yes, and let's press enter. Let's see. Do cd and go into the source file. In the source file, we are going to create a few directories. First, we'll create modules, space, services, controllers, and config directory. We also need to add route for the HTTP routing. So type enter. Let's see. Yeah, the files are created. Now cd into the config file, and inside the config file we will put the configuration for our database. So inside there, I want you to create a file and call it db.config. Okay, now leave that file, go back into the source file, and now let's go into the models. Inside the model, we want to create db.js, and also we want to create a file and call it census.model.js. Now go back. Now let us go into the controllers. Inside there, we will create a file and we will call it census.controller.js. That will be all. Now go back. Let's go into the route. Inside the route, we create a file and call it index.js, and also a file we call it census.routes.js. Now leave the route and let's go into the services. Let's create a file and call it census.services.js. So basically this will be the file structure for this program. As you can see, I will include a link into the description for you to see the structure more clearly. Once we are done with creating our file structure, we will proceed and create the API for accessing the database. This is how our directory looks like. Inside the server, we have the node modules, public, source, and these files. Go into the source and into the configuration. We created this file db.config, but we need to rename it. It has to be db.config.js. So you can do the renaming here. We are going to set up for the PostgreSQL. We need to first give the credentials of our database and export it. Module.export, and inside this object we will give a few credentials. The user will be Postgres. We will add a host, give the name of the database. We will call it home. The next thing is to add a password. Just create any random password that you want for your database. I'll use this, and the port is always 54. STM32. Once you are done, go to the modules, and inside the modules, the db.js. So this is where we are going to create an object that will help us to connect to the database. We are going to require the PG, that is for Postgres. And also we will get the db config that we just created. So let's try to access that config/db config. Constant pool, and we are going to create a new instance of this pool that we got from the Postgres. So you do this and you leave space. Inside here we call user, and the user that we created in the db config, we call host dbconfig.host database, call the password, and we call the port. You bring a semicolon. When the database is connected, we can print something. So on connect, we can write something to the console. Now in case there's an error, we can also print something to the console. Error on the client, you can print the error and exit. After everything, Node.js application, we always need to export, and this export will be the pool object that we created. This is a concise program here that will allow us to have access to the database. From this, in the same directory, I want you to go to the sensors.module.js. A module is going to describe the fields in our database and the operations that we would like to do in the database. So for example, we would like to insert something into the database, we would like to find something by an ID, we would like to delete, we would like to update. All those things we are going to describe in the module, so that later on we can reference the API and we don't need to rewrite the queries manually. We will call the pool that we created here. So on top, let's call constant pool. They are in the same directory, right? So db. The first function is we have to create the table that we want to have access to. When you go inside the database, we have tables. In case the table is not created, then you have to create it, and we call it create sensor data table. We have to make it asynchronous in case it has to wait for a response. Inside here, we will write a query to create table, and so we can do constant query like this. As a convention, we have to write in capital letters, but you can also write in small letters. We do create table, and the name of the table will be sensor data. We need to bring this. Let us define the fields in the table. So first, this sensor data table will have an ID, primary key, so that it will keep on increasing, and it has to be unique. We will have a field for timestamp, so that anytime that we send data, it will get the timestamp of that particular moment and save it in the table. We will call an inbuilt function called timestamp default now. Now the next field will be for recording the temperatures, and this will be numeric. We will create the field for the pressure, the field for air quality, and also for the light intensity, which will also be numeric. We will just call this function here. So this function will be called automatically in case the table does not exist. So we say create table sensor. Let's add if not exist. If we already have the table, then we want to create it again. The next function that we want to create is a function that will go into the database and query all the data that we have. So we can do const get all sensor data. Now we are going to do a try and catch. Let's put an error. If there is an error, we will throw that error. Throw new error. Now inside the try block here, we can do constant result. We call the pool object and we pass in the query. We want to select everything. To do that, we write select star from sensor data, and we will return all the rows. The next function will be to get a specific row of sensor values by the ID. Get sensor data by ID. It means that we have to pass an ID to this. Make sure you bring your semicolon. Inside here, we will do try and catch. So now constant result, we will do await pool.query, and this time the query to select a row of data by an ID, we write select star from sensor data, where ID is equal to the ID that we want to add, right? We will do *1. We go outside here and we put this in bracket ID. Once we have this, we can do return. This time we only need one value, so we get the first row, and we have to do the catch the error. Now, something that we would like to do with this project is that we want to enable the user who is accessing the web client to input a time range in which he wants to see the sensor data. So you go to the website and you type, let's say 1,5. It means that you want to see the sensor values that has been recorded between the past 1 hour and 5 hours. So let us write the query for that. We can say constant.get sensor data within range async. So this time we need to give it the time range that we want to query the data. Bring your semicolon. Let's do a try block here. We're going to do select star from sensor data. This time we will use the where clause. Now if we look at our database, you can see we have a timestamp field, so we are going to use that. So where the timestamp, we want to find the timestamp between certain period of time, right? Let's go to the next line and do timestamp between now, and we need to subtract. Let's get the time that we passed here. This time we get time end. So this is going to be an object. So that object will have a field that we call time end. It will be in hours. Okay, let's continue the query. Let's go to next line. Now we will get the time start. So now minus interval. We do the same thing. This time is going to be time start, also in hours, and we will bring a semicolon. This query will do that for us. It will get the sensor data within a specific range. So now we can get the result like we did for the previous. Await pull.query, and we pass in the query. Once we get it, we can return the result, and this time it's going to be a lot of rows. We will return everything. Now let's catch the error. The next function will help us to insert sensor data into the table, right? And also we will create a function that will delete a row from the table. So the function to insert, we will call it create sensor data. This will be async. And when we are creating a sensor data, we need to pass the data that we want to create, right? So this is going to be a post request. You send a post request with the key value pairs. We will do this. Make sure you bring your semicolon. So inside here, we will try and catch. So we're trying, we need to get the query. We're going to insert into the sensor data table. We'll get the field that we want to insert to. We get the temperature field, pressure field, the air quality, and the light intensity. Now come to the next line and the values that we want to insert. The values we want to insert will be coming from this. So this is going to be an object. So we are going to call this object, and we will get all the fields that we want to insert here. In PostgreSQL, you can just represent them with numbers. We have 4 values to insert. After creating it, we want to return the object that we created. So we will add this. Once you are done here, let us get the objects that we want to insert. That is the fields that we want to insert. Let's put them into like an array. We can do constant values, right? Going to be an array, and we will pass the field from it. So this is temperature here, data dot. The next one is pressure, air quality, and light intensity. Now this, as I said, is going to be a post request, so make sure that the fields they match this exactly. Other than that, it will return an error. And we can do constant result, the same as the above. Await pull.query, and this time we will pass in the query that we just created above, and also the values. So we get the results and we can return it. We are creating one object, so we get the first index and we throw it. The last function that we create is a function to delete a field in the database. So as usual, let's say delete sensor data. Sync. Now when we are deleting sensor data, it means we are going to delete a specific ID. So let us pass the ID here, except you want to delete everything inside the sensor data table. This is not what we want to do. Bring your semicolon. We do try and catch any error. The query is delete from sensor data, where the ID is equal to, we will return the row that we deleted. So bring comma inside and also outside, bring comma, right? So once we have this, we can do results. Once again, we call the pull object query, and we pass in the query, and also we need to pass the ID that we want to delete. Okay, then we return it. We are only deleting one, so we get the first index. Then we can catch any error. So we can do module .export. So first we export the get all sensor data, get sensor data within the range, literally all of them except creating the sensor table, and also delete, comma. Now that is it for the sensors.module.js. From here we will go inside the services and we will write the code for the sensors.services. So the sensors.services is going to require the functions that we created in the module. That is why we exported it. We create all these abstractions and it makes it easy for us to manage the database. Go to the sensors.services.js, which is inside the services directory. Now that we are done with the sensors.module.js, go to the services directory that we created and let's write the code for the sensors.service. The first thing that we do is to import the module that we defined. So we will do constant sensor module. We go to the module class, then we select sensors.module. We will define a service function for each of the modules that we defined. What I mean is when you go back to service.module.js, all these functions, we need to create service functions for them. Starting with the first one, we begin by saying export. Now when we do the export, it means that we are exporting directly. The previous one, after defining the functions, we exported. But one way is that we can also do it directly. Export.get or sensor data. This is also going to be asynchronous, and we do our try block. Basically, we are going to call the similar function in the module. So we will return sensor module. We will call the get all sensor data. If there is an error, we will throw that error. So seeing that this is very easy, you can go ahead and do the same for the rest of the functions in the module. You can do get sensor by ID. Now because we are getting sensor by ID, we need to pass the ID whenever we call it so that we can give it to the module. Next function could be the get sensor within range, and that one we would give it the time just as we did here. It is this function that we are calling inside the service. Within range, we pass the time. The next function create sensor data. We can paste it, and when we create sensor data, we pass the data to it. Now we need to do the same for the delete sensor data. You can choose to write. The delete will take the ID. We have created the service functions for the modules. So what happens is that we are not going to call the module directly. We can choose to call the services. Once we are done with the services, go to the controllers directory and let's write it. So just as we did for the service, we will now import the service. We can do constant sensor service. We will import from the service / sensor service. Now once again, we are going to write the controller for all the services. The controller is the functions that we use for routing. When somebody, for example, wants to access a specific API, get all the sensor data, then the routing file that we will write after this will route the request to this controller. The controller will call the service, and the service will call the module, which will execute the query. We use this abstraction in Node.js application. It makes it very easy. So we will do export get all sensor data, going to be async, but this time because it will be receiving the HTTP request, we will pass in the request and the response. So this time we are going to get something from the service, something that has to return. So we can say sensor data, and we will await, and we will call the sensor service dot get all sensor data. Once we have this, we can return the HTTP response that the request was successful. So we can do response dot status. Status 200 means that it was successful. We will send the sensor data in a JSON format. We can pass the sensor data just like that. Then we will catch get any error. So we can use a response of 500. The request failed, and this time and do a message. Then we will get the error.message. Now we are going to write functions for the rest of the services. So the next one could be get sensor data by ID, request response. We will try. We will get the sensor data that we want. We call the await, then we need to pass the ID. If this is a request, then we will retrieve the ID from the parameters. You can do request.params.id, and that should be it. We can return the response 200, meaning it was successful. Then .json, then we pass in the data. If the request was not successful, we print the error and use 500, and we can do the same. The next function, we can get the sensor data within range. We try the data that we retrieve, we put inside a variable, this one. And if we look at the function, when we come here, the get sensor within range, pass the time, right? It's the function that was called here with time. So if we are calling it in the controller, then we need to pass the time, and this could be a post request. So we will get the body of the request. Can do request.body, then we can return it. HTTP status as successful. If not, error occurred. We catch it. We can create the create sensor data. We call the function from the service, create function. So the create is going to be a post, so we pass in the body and we return the request status. So after creating an object, whatever it is, it will return it. If not, then there is an error and we get the error like that. Need to remove this one. What is left for us to define will be the delete sensor data, and this one, it takes the ID of the row that we want to delete, and after deleting, it will return the row or the entity or the sensor data. Same process. We call the delete sensor data and we pass the ID, so we get it from the parameters. That is, we pass it in the get request. If not, an error occurred. Okay, so we have defined the controllers for this application. The next thing is for us to route everything. So if we look at how it works, the service calls the module, the controller calls the service. Now we will go and route the request so that when the request comes in, we can route it to a particular controller. So first, let us get Express, and we will also get the router, express.router. We will get the controller, so sensor controller. We go to the controller directory, we select this. We are going to route each request to the functions that we have created. So first we can do post. When the post comes in like this, then we will route it to sensor controller dot create sensor data. We can do a get request on this slash to sensor controller get all sensor data. Now what this means is, for example, if we have a domain name, right, and slash, and it's a get request, then the request will be routed to this, right? We can do router dot, if we want to search, we can call the get sensor data within the range, so that will be a post request. If we want to get a request by the ID, so if a request comes in by this path, then we can get sensor by ID. The next is to route the delete. So if the delete comes in, the ID, we can map this to delete. When we are done, we need to export the router. This is very easy. So in the same directory, go to the index.js. Now, before we begin to write the entry point of our program, that is the index.js, we need to install something. When you look at our package, you can see all the dependencies that we have: Express, HTTP, MQTT, Postgres, and Socket.io. We need to make a last installment for EJS. EJS, embedded JavaScript. It allows us to embed data into HTML file. For example, if we query our database and we get rows of data, we can decide to embed it inside HTML. So go to your terminal and move back to the main application, that is the server, and we will do npm install EJS. Now the package is installed. It looked like it required root access. Open your index.js with VS Code or whatever editor you are using. First, we will get Express. We will get MQTT. We will make app out of the Express. If you know how Express works, then we will get the port. As I said, we are going to run it on localhost, so we could make it port 3000, and this is the Node.js server, so that when you go into your browser you can type http:// your IP address :3000, then we can get the HTTP to require HTTP. Next, we can get a server out of the HTTP that we created, the http.create server, and inside the server we will add the app, this app that we got from the Express. We will get a path object because we will be serving static files on the web client. The next one, we will do this server and we will require socket IO. We are going to use socket IO and we need a server to do that. So once we have this, we can do IO is equal to, then we call the server that we have already defined up here. So we create a new instance out of that server and we pass in the HTTP server, right? So we need to create a server for the socket IO. Whenever a request comes in, it needs to be routed. Can define constant routes. We go back into the source, and source we get routes, and you get the index.js. And the last thing, we can get sensor module, source modules, and sensors.module. We will set up the embedded JavaScript. We call the app.set. We call view engine, that is the default name for this, and we will use EJS. Now we also want to specify a directory which will contain the static files, that is our web pages. So we can do app.set. We need to specify from which directory we are serving our static files. So we will do views like that. Then we call the path object that we created, then join directory name, and we want to be serving from the public directory. We are not going to save every sensor data or row of sensor data that comes in. So we create a buffer, and for example, we will save about 5 minutes of data inside this buffer. After the buffer is completed, we will find the average and we will save the average inside the database. Let sensor buffer. We will set it to empty array, middleware to parse JSON data. We are going to use express.json. We call it like that. Now we will add routing here so that when an HTTP request comes in, it will route it to the appropriate API. So we can do app.use. We will say like API, which means that whenever a request comes in and it has this after the domain name, right, then it will be routed to this. Now it's time to set up the MQTT. So we can just create a constant and call it MQTT client. And this one, we are going to call the MQTT that we created up here, this. So we do MQTT and connect. Now inside this connect, we are going to add this, and also we will add our IP address. Now the IP address that my Raspberry Pi has is this. Look at yours. You can go to your Linux terminal and type ifconfig. It will show you the IP address. So we type in the IP address and we type in the default for. Once we have our MQTT object, we are going to define two main functions. That is when the MQTT is connected and also when message comes in. We will do MQTT client that we just defined above on connect. We are going to call this JavaScript function. For debugging purposes, you can print something to the console connected to MQTT broker. So when connection is made, what we can do is we can subscribe to a particular topic. So we can do MQTT client.subscribe, and when we looked at the code that we wrote for the ESP32 client, we created this subscription home.census/data in case we catch any error. Okay, make sure you bring the semicolon here. We can print it to the console. You say failed to subscribe, we can put in the error. In case you have another topic, subscribe to a different topic. Now we will leave this entirely just as we've done for MQTT client.onConnect. That is when we are connected. We can also do that when message comes in, right? And we decide what to do with the message. We can decide to save the message, or also we can decide to send the message to update the web client, right? We will do MQTT client.get this time on message, right? So when we have a message, we want this to be async, right? So that it can work in the background. We pass in the topic and also the message. We need to make sure that this is the topic that we are expecting. For example, we might be publishing a couple of topics. So once we know the topic, then we can route it properly. If topic is equal to what we are expecting, this time we are expecting home/census/data constant get payload string, and we will call the message and we will convert it to string. Payload string received. Once we are done, we can convert the string into appropriate format that we need. We'll be passing it as JavaScript object, an object that has the fields of temperature, pressure, air quality, and light intensity. We will say sensor data. We will create a function and call it convert payload string to object. We will pass the string inside it. You can do console.log sensor data, right? When this is complete, we can update the web client, right? And we said we will be using the socket IO for real-time communication for the web client. So the object that we created for the socket IO is here, IO. So inside here, we will call this emit, and we give a name for it, sensor data. The working principle of the socket IO is easy. All that you need to do is that you need to emit data and you go to where you want to get that data. For example, when we start writing the HTML, we will call socket IO object and we will do, for example, socket.on. Whenever we receive this on sensor.data, then we can retrieve this object. Okay, then we can decide to save the sensor data that we have received. That is the average. Save average sensor data. This function we've not created yet, but we will create. So we have two main functions that we will create. We have this to convert the incoming string to object, and also this function that will save the average of the sensor data that we have recorded over a period of 5 minutes. Move down and we need to define few endpoints. We will do a get request. When somebody visits the home like this, we want to see if the page is working, right? So request response console.log, we will say hello world, then we can return response, then we can just pass a message like data received. Do app.get/graph, the request comes in, the response showing graph. After that, we are going to serve the request with the static HTML file. So we can do res.send file. We add the directory where the files are, and the files are located in the public/graph.html. I mean, when you go inside the public, we are going to create two HTML files. One will be graph.html and the other will be detail.html. In here, we will do app.get detail request response. We will do try because we will be accessing the database. So we say constant data, and this is why we define the sensor model. We imported it here. If you go up, you see the sensor model. We want to access the database directly. Sensor model, then we get all sensor data and we will send the response. Now we will be using the EJS embedded JavaScript. So with that, you call res.render, we give the file name, the data that we queried from the database, we want to embed it inside the HTML. So we do it like this, and that is all. Here we are assuming that you are using a template engine. After this try, in case we get an error, we will catch the error like that. Error retrieving data. We have to make this also async. The next thing that we will do is that we will create the connection for the socket IO. So IO.on, this time on connection, we will create an object and call it socket, and we will say that a user connected to socket IO. On the web client, the user will have the opportunity to either turn on or turn off a sensor, and we are going to use checkbox for that. We will do socket.on, and this time we will call it checkbox data. When such data comes in, we will get the data like this. Once we have the data that we want to send to the client, we need to call the MQTT. Python 3 main.py. The test-based RPG adventure. Main menu. Alright, I'll start a new game. The character's name will be Titan. Choose your class. Let's say I want to be a warrior. Now we are in the main game loop with 5 options. Let me check inventory. 2. This is what I have in my inventory. 2 items. Okay, 3. Let me view the quest. Item not found. Okay, explore this time. You meet an old man. Welcome to our village, we need your help. Yes. Our main game loop. On explore, nothing happens. Okay, let me explore again. Now something happened. Scroll to the top. I explored one and an enemy appeared, so there was a battle between me and the enemy, and it looks like I won and I leveled up. Okay, explore again. An enemy appeared. This time I was defeated. Now it took me back to the main game loop. Let me view the quest 3. I have these items inside my quest. My mission in this game will be to find a lost sword, save a village from goblins, and retrieve the magic amulet. Okay, so I will explore one. I found a treasure. Then it means the treasure was added to my inventory. So let me check my inventory with 2. Yes, right here. Gold was added. Gold was the treasure that I found and it's being added to my inventory. I'll go back. Alright, so I will save the state of this game by pressing 4 and 5 to quit. I'm out of the main game loop and it took me to the main menu. So start new game, load game, or quit, and I will decide to quit with 3. So now when we do ls, we can see that our game state was saved in save game.json, and we can look at what is inside there by using cat. So it's saved the entire state of our game, the player, his name, everything, his movement, and the quest. Let us look at the flowchart of this program. When we start the program, the main menu is displayed. Now the main menu of this game offers 3 options. You can choose to start a new game, you can choose to load previously saved game, or you can choose exit. Now when you exit, it means you're out of the game, but when you decide to play a new game, the program will go ahead and start with creating your character class, whether you want to be a warrior, a mage, or an archer. It will ask you a few questions about your name and other stuff. When you are done, it will initialize some preliminary game elements, and after that it goes into the main game loop. Now if you had previously played this game, it means that you already have a character name, the type of the character, and probably you've won some trophies, or maybe you have acquired some weapons. So when you choose this option, it will load all those data and use that to initialize the game element. Now in the main game loop, about 5 options are provided. You can choose to save the current game you are playing. You can choose to view quest. Quest file is provided as part of the game. Whatever you can do in this game, the treasure hunting that you can go on, the villagers that you can help, everything has to be provided by the quest. So the quest is provided as part of the game. Now there's an option to check your inventory. Every item that you can ever acquire or take in this game, it will be saved in the inventory, and you can choose to explore. There is also an option here to exit. Now if you choose to explore, first your player is going to move, because in this game we have the map function that allows the player to move either north, south, east, or west. When the player moves, there are 3 activities that can happen. He can move to encounter a treasure. For example, you can take coins or gold, right? And when such items are encountered, you put them into your inventory. Also, you can have a dialogue with the game intelligence, right? Sometimes you are playing a game, you reach a certain point and you'll be having a dialogue with the game. Let's say, do you want to go on this quest or not? You have the options to either accept it or decline it, right? And also you can move and encounter an enemy. When you encounter an enemy, it means there's a battle. If you kill the enemy, it means you've won the game. If the enemy kills you, unfortunately you have been defeated, and it will take you back to the main game loop. After this encounter, the program always checks that the character is alive, right? Once you are alive, you can see it goes back to the main game menu and the options are provided. If you are not alive, then probably we are exiting this game and it will take you to this menu where you can start a new one, you can load previously, or you can totally exit the game. So the flowchart of this program is very simple and intuitive. Let us start writing it. Go to any directory where you want the program to run and create a Python file. I have created mine and called it main.py. We will start by importing some modules that we will need. First, we will import JSON, and we will import random. That will be all. One of the most important things in game development is building a player. We make the character class that will be the basis of any player that we create. Out of a character class, we can create unique players with different abilities. So let us start by creating a class and call it character. Now we will define a constructor in itself. Constructor of this class is going to take name, health point, attack, defense, and level as parameters. And the level we will give it 1, which means that every player will start at level 1. We set name to name. We will give it an experience 0. Now this is going to be the main attributes of any player at all. The HP is the health points of a character, and it will decrease whenever the player takes damage, right? When he gets hit by an enemy. Now the defense power of the character will reduce any damage that the player gets. The level refers to the level of the player in that specific game. So whenever the player wins any battle, his level will increase. And also as the player wins stuff and gain items and win battles, his experience will increase. A character, which is a player, will take damage. So we can define take damage function and we will pass the damage. Let's say that you are fighting with an enemy. The enemy can hurt the player. When a player takes damage, then we are going to subtract it from his HP, that is health point. But we do not want any negative value. We make sure that we subtract the character's defense from the damage that he is incurring. We can define a function that will tell us whether our character is alive or not. We can do is alive, and it will not contain any parameter, and this will return health point of the player is greater than 0. If it is greater than 0, the player is alive. If it is not greater than 0, then probably he is dead. We can do define gain experience, and this method can take experience as a parameter. So whenever we get an experience, we will add it to our experience like that, and if the experience exceed a certain amount, we will level up. We can say if self.experience is greater than or equal to self.hp times 10, we will call a function to level up. So this level up obviously will increase the level of the player. Define this function, we can do level up, and it will not take any parameter, and whenever a player levels up, he gets some values increase. The level will increase by 1. We can also increase the health point by 10. We give the player more attacking power. We can give him more defense by 2. We will set the experience to 0. Okay. Whenever the player's experience reaches 10, his level will increase by 1. Whenever we call the level up function, we can print an information to the console. The name of the player, level up 2, then we can. This will be the character class. Out of this character class, we are going to create specific players with unique abilities. Let's give a comment and say warrior. We can create our class warrior, and this class is going to inherit from the character class. We bring our bracket and we call the character class here. Now we define constructor for this self. Whenever we create an instance of the character class, we will pass the name to it. Then also we need to call the constructor of the class we are inheriting from. Init. Then according to our character class, the constructor contains name, health point, attack, defense, and level. So we do name. The name we've already passed here, right? But the others we need to give them some default values. Now let us create another unique player, and we will call this mage. So we can create a class mage, and this class as well will inherit from the character class. We define the constructor for this class, and we'll pass self and name. Once we are done with that, we also need to define the constructor of the class that it inherits from, and that was the last special player will be the archer. The archer is also a combat specialist, and he excels when he attacks from a distance. Okay, so we create a class archer. It will inherit from the character class as usual. We call the constructor in itself. Whenever we create it, we need to pass the name and super. So this will be the 3 main unique players that we are going to use in our game, which means that when you decide to play this game, you get the chance to select the player that you want to be, whether you want to be a warrior or a mage or an archer. If you have ever played a game before, you realize that the player can pick up certain items. It could be a sword to fight, it could be stars, it could be coins to earn more money. Now all those items are classified in the inventory system. So an inventory system will give us an environment to create and save all the items that a user can ever use in the game. We can define class an item. As usual, we define the constructor, we put in self. Whenever we want to initialize an item, we have to give it a name, we have to define the item type and also the effect. Because some items are, to make the player fight more. Some items like potions are used to heal the player when he is hurt. Once we define that, we can go ahead and set the values. Effect is equal to effect. Now we have this attribute for an item class. We need to define how we will use the items. Define usage of items. So we can write this method as, let's say, use. This method could take the character as a parameter, right? So whenever the character wants to use a certain item, I think it is obvious that we need to check the type of item. Once we know the type of item, we can define how the user is using it. The 2 main items that we will have will be a weapon and also potion. Potion is for medication and weapon is for fighting. So we can do an if statement here and say if self.itemType is equal to potion. Then we can call the character which we have defined above, and potion is for healing, right? So healing, we are going to look at the health points of the character. So we will call the minimum internal function and we do character.hp. Then we will add it to the effects of the specific item. So we will say self.effect, and also we call character.level times 10 plus 90. So we will pick the minimum out of this, which is going to be like the character plus the self effect, obviously. Once the user is using the potion, we can write a message. We can do character.name, use something, right? What did he use? He used the name of the item and healed. So we can show the effects of the item HP. Once we are done with this, we can check if the item the user selected was like a weapon. We are going to add the effect of that item to the attack power of the character. If correct this character.attack, we can add the effect of the item to the attack, just like that. Then we can print a message. So the user has gained a certain amount of attacking power. So we can say this character is equipped with something, name of the item, and he gained, we show the effect of the item that he picked. So let's say that he picked a sword that has a power of 10, then we can say that of effect of that attack. Now this should be enough for defining an item. Any item that the user can ever pick will have a name, item type, and effect. Now we can create an inventory. So the inventory will be like a container that will contain all the items that the user can ever pick. So we can define class inventory. We will define a constructor self, and the constructor will not contain anything. Immediately you instantiate an inventory class, it will just create an array of items. Because this is an inventory and we said that all the items of a player can be managed by the inventory system, it means that there should be a method that will allow the player to save the item that he picked. Also, there should be a method that will allow the user to remove an item from the inventory. Let's add a comment like we can add an item. So we define a method and we call it add item. It can take the item as a parameter, and we call the set of items, and we are going to add this item to it. So because it's a list or an array, we just append it to it. Now we can add item, so let us be able to remove item. Define remove item, Now if we want to remove an item, then we need to pass the item that we want to remove. So we do the self.items remove. We pass the item that we want to remove. A method in the inventory, let's say use an item. So we can define a method and call it use item, right? If we want to use any item, then we can pass the item name and also the character, that is the player who wants to use the item. Now this inventory class will contain all the items of a player, which means that we have to loop through his items and get the specific item that he wants to use. So we can do for item in self.items. Now if we find the item the user is looking for, item.name is equal to item name. If this is true, then we can use the item. We can do item.use, and according to the item.use method that we define here, we pass the character. So item.use, then we pass the character. Once an item has been used, we need to remove it from it. It could also happen that we are looking for an item which is not available in our inventory. In that case, we have to tell the player that item is not found, and we can return false. That is method for using item. Now correct this, use item, not user item. So now let's define the method that will save our inventory and also the method that will load the inventory. Define save inventory. This method can take the file name. We want to save the inventory, so we have to compile all the inventory into, let's say, a JSON file. So we will use the with Python command. With this we pass the file name. Because we are saving it, we want to write as file, and we call the json.dump function. And because it's an array, we need to loop our entire array and write them into the file. So we will do item dot, we call the dictionary function, or date for item in self.items, and we pass the file. This will allow us to write all the items in the inventory array into a JSON file and save it in our system. The last method that we can create is to load inventory. So we do define load inventory, and to take a file name if we want to reload a previously played game. So we do with open Python function, we pass in the file name, and this time we are going to read as file. Now we need to create a list or an array that will get the files. So we pass the files right here. Now we set items to the JSON file that we want to read, and we will loop through the file and write them to the items list in the inventory class. So we will do self.items, right? And we are going to loop through. So we call the items class right here, and then we will do item. We get the specific names, we get the name, we get the item type as we define in the item class. Then we also get the item effect. And because we are looping through the Python file, we can do for item in items. That should be all for the inventory class. In this game, a player is going to fight with an enemy. So we will define a battle system that will allow that to happen. First, we will check whether the player and the enemy is alive. While that is true, they will take turn in attacking each other. So first, the player can attack the enemy, and if the enemy is alive, he will take turn and attack the player. At the end of this while loop, whoever is alive wins the game. So we can create a battle system for that. We will define battle, and obviously we have to pass a player and an enemy to it. So as I said, we will do a while loop while player is alive and the enemy is also alive. While this is true, first we will let the player attack the enemy. The player will use his attacking power, attack. After the player attacks the enemy, we'll check if the enemy is alive. Then he will also take turn and attack the player. So we will do player take damage. Inside will be the attacking power of the enemy. Once we go through this while loop, whoever remains, as I said, is the winner. So you check if player is still alive. If that is the case, we say you won the battle. If that is not the case, we will tell the player that you were defeated. Now, an important aspect of every game is the ability of a player to move. Sometimes when the player moves and touches an item, it triggers an event. For example, when the player touches a star, some rain might fall, or maybe he might end up increasing his lifespan. So now that we are done with defining the battle system, we can go ahead and define a map that will be responsible for movement of the player. In this game, the player will be able to move north, south, east, or west. We will create the map class. For the constructor of this, we can just give it the size of the area that we want the user to be able to move. Self.size is equal to the size. Then we will create another variable and call it map. This map is going to contain a grid of the movement of the user. So we can create a grid using this for loop. We don't need to give it a name. We can do this in range. Then we pass the size. Then we do for this in the range size. We are going to get a grid of s by x, but it will be dots of the size. So let's say that if we have a size of 7, then we are going to get a row of 7 dots and a column of 7 dots. So once we've defined the map, we can define the player position. This player position is going to just be an array of only x and y coordinate. We can divide x by 2 and y by 2 so that we get x and y coordinates. Once we are done with the constructor, we can define a function that will allow the player to move. Okay, so we can say dev move player, and because we are moving the player, we need to pass the direction in which we want the player to move. And as we said, we'll be able to move north, south, east, and west. We can say that if the direction is equal to north and the self.player.position, that is the s coordinate, is greater than 0. If we want to move to north and the s coordinate is greater than 0, then we are going to subtract 1 from the user's position to allow him to move to. So we will do self.player position minus 1. In the same way, if the player wants to move out and his x coordinate is less than the size that we pass minus 1, then we have to add 1 to the player's position to allow him to move right. So we can do if direction is equal to south and self.player position still on the s coordinate. If this time it is less than the size of the grid minus 1, then we can just do self.player position, and this time we add 1 to it to allow him to move right. What if the player wants to move, let's say east, and this time we will take the y coordinates. So we say if self.player position y coordinates, if the y coordinate this time 1 here is less than the size, then once again size minus 1, then we can do self.player position add 1 to it. So we can also do for the west, right? This time equals to west. If this time is greater than 0, then minus 1. As I said, movement can create an event. So whenever we call this class or whenever we make an instance of this class, it should return an event. So this event, we can just get a random choice of what we might encounter. The user might encounter a treasure or an enemy or nothing, or maybe he will just interact with the NPC function, which we will define very soon. So the NPC allows the game to communicate with the player. We can list some of the things that the player can encounter when he moves. So the NPCs, the non-player characters, that is the things that are not under the player's control, like a dialogue. Do you want to go home? Yes or no? That kind of stuff. Basically, this will be enough for movement of the player. After defining the movement of our player, we can go ahead and provide the storyline. Now, every game runs on a particular storyline. Sometimes it could be a quest. So in this instance, we need to provide a quest for the player. Now, this quest could be specific objectives for the player to accomplish within the game world. So after the player have accomplished that quest, he might get a reward. So we will create a class and call it quest and define a constructor for it. So we do self. Now in this game, we will provide a file for the quest. This file will contain all the quests that the user can ever do. So we pass description and we can add the reward. Self.reward equals reward. We can add whether this quest has been completed or not, and this one we can give it a default value of false. We can write define complete quest, pass the self and also player. if the player actually completes this quest, then we need to set the completed attribute to true. The gain experience method we define in the character class, and we pass the reward. So the reward of the quest will be the experience that the user gets. Then we can print something and let the player know that he has completed a particular quest. You have earned this experience. Now we will define a function that will load the quest. As we said, the quest file will be provided by the developer. We just define load quest. We are going to load the file. First, let us create a list that will contain the files that we will load. Then we will do with open. We pass the file name here and we will read as file. We can do for every line in the file. Now every line is a quest, and every quest contains description and also the reward of that particular quest. So we will break each line into their respective description and reward by using the strip command. The description and reward, they are separated by a comma. We can use the strip command to split it. We want to split where there is a comma. After splitting it, we need to make sure that the length of the line is 2. Description and reward, we can do if length part. If it is not equal to 2, then probably the line is invalid. We can say skipping invalid line in quest file. To be able to do that, we need to put F here. So now we split it, then we continue to the next line. But if the length is 2, then actually is correct. So we are going to get description and reward. Then we will set these 2 parts, right? Once we have done that, we can append this quest to the list of quests that we created above here. We will do try reward is equal to int reward. Then we append it to the quest list. So we call the quest class, and the quest class takes description and reward. We just pass it description and reward. And since we are doing a try, let's write exception here. If there is a value error, we can do print here, and we can say that invalid reward in line. After doing this, all that we need to do is to return the quest. So now the list will contain quests. After creating the quest and storyline of this game, we can go ahead and create the non-player character class. Now it will be responsible for quest management and also dialogue, which are not under the player's control. It represents character control by the game's intelligence. We will create a class. We call it NPC. We define the constructor as we did for the others. It will contain a self and the name, the dialogue that we want the game intelligence to have with the user, and also the quest. So this time we will set the quest to none. Now after doing this, we can set the values for the variable. Now after defining the constructor, we will add a method here that will enable the game to interact with the user. We can simply call this method interact. This method will take the player as a parameter, so it's going to interact with the player. Whenever we call this method, we can print the name and also the dialogue that we want the game to have with the user. Print self.name then self.dialog. So after doing this, we can make sure that the user has completed the particular quest or not. So if self.quest and not self.quest completed, then we can print something quest available, because the player has not completed this quest yet. Now we are telling the user this is the quest you have to do next. Do you accept this quest or not? So let's create a variable here and ask the user for his input. Do you accept this quest? Yes/no. Now we will check his answer. At first, let's convert his answer to lower, and if it is yes, then we can return the particular quest. If the user wants to take up this quest, we will return this. If not, then we just return none. Now that we are done with creating the NPC class, we can define the main flow of the game. We will start by providing the player with some options to choose from, which means that when the game starts, we welcome the user to the particular game, which is a text-based RPG adventure. So let's leave some space here. So we will define like the main function here. We call it function main, and it starts by welcoming the player to the game adventure. Once we've welcomed the player, we can give him an option to either start a new game, load the previously saved game, or if he wants to quit, we can show him the menu, main menu. First, we will say that 1 is to start a new game, 2 will be load previous game, and 3 is to quit. When we provide him with the options, then we can get his choice. Choose an option. So now, depending on the option that the player wants to choose, we can do an if statement. If choice is equal to 1, then we will call the start new game function. Now, we've not created this function yet, but we will soon right after this. If choice is equals to 2, then obviously we are going to load game. We will create this function. If choice is equal to 3, he can decide to quit, so we will just return. Anything beyond this, we let him know that it's invalid. We can say that invalid choice, please try again. With this loop, the user can decide to play the game over and over again. He plays one game, he can save it and reload it again. Now that we have the main flow of the program defined here, we can start by writing the exciting part of the program. We have 3 main functions to define. We need to define this start new game function. We need to define a load game function, and also we need to define a function that will save the game. We start with the first one, and we can write a comment playing a new game, and we define the function start new game. Now this is when the user wants to play a new game. Immediately we start, the user is going to choose the type of character that he wants and also provide the name of the character that he wants. First, we ask for the name. We can do an input here and we say that enter your character's name. We will give him options to choose which type of character he wants to build. Choose your character class. Maybe 1 means warrior, choice 2 means a mage, and choice 3 is an archer. Now that we have given him 3 options to choose from, we need to accept his choice. We can create a variable and call it class choice, and this is going to be an input, and we will say choose a class. So depending on the input that he gives, whether 1, 2 or 3, we will create the class by calling either warrior, mage or an archer. We can do that by using an if statement. If class choice is equal to 1, we are going to create a player of class warrior. So we say player is equal to warrior. When we scroll back to the classes, scroll to the very top, right down here, whenever we create the character class. Now don't forget, the character class is over here, and these 3 special characters are inheriting from that. So a character class always requires you to input the name, and the other values are given as default. So scroll back, let's give it the name that he inputted at this point. So we put in the name. Now we can do the same for the others. If class choice is equal to 2, then we are going to create a mage. Player this time will be a mage. Give it the name. If the choice is equal to 3, then it's going to be an archer. We will tell him his choice is invalid, and we give him a default character. We pass the name. The first part is done. The next thing is to give him an inventory, and according to our inventory class, the player can use a potion or a weapon. We can do inventory, then we call the inventory class. And according to the inventory class, we can scroll to the top. We don't have to pass anything to the constructor. So the inventory class is created, then we can add certain items. So inventory.add item, and according to the add item function, we add it and it will append it to the list of items the player has. And we shouldn't forget that this is the item class, and an item should have a name, item type, and effect. We need to add an item, so we call the item class, and the constructor of the item class, we pass the name of the item, the type, and also the effect. So this item could be health potion. This is going to be like a medicine that the player can use. The item type we say is potion, and the effect is going to be 20. If you remember, we say that whenever the user gets an item, that item is added to either his attack power or health power. And we can also add another item. The item type, this time the item name, let's say iron sword. The type will be weapon, and the effect will be, let's say, 10. Now that we have given the user some items, we need to define the movement of the user by calling the map function that we define above. So we can say game map and we call the map. Now according to the map class, whenever we call it, we pass the size into the constructor. So let's say we give it 5. So the player will be able to move on a 5x5 grid. Now after giving him movement, we also need to load the quest. So we will create a list and call it quest, and we call the load quest function. We pass the name of our file. Now when we scroll here, you can see that this is the load quest. We pass the file name and it will read the file into a list and return the list, which means that this is going to contain all the lists of the quest that has been provided. But we need to make sure that there is something in the quest. Other than that, we cannot continue with the game. So we say if not quest, we can't play at all. Then we will return. After loading the quest, we also need to give some non-player character according to the NPC function, which we define here. Let's scroll on top. When we call the NPC class, we pass the name, the dialogue, and also the quest. Right, so at this time we've already loaded the quest, so we can pass the quest to it. So right here, NPCs, right, call the NPC class, and inside it we give it something. For the name, we say old man, welcome to our village, we need your help. Once we do this, we will pass the quest that we want the user to do. So we can do quest, let's pass the first line to it. Now that we have defined the player and given him the inventory, that is the item that he can use, giving him his map, the grid that he can move on, as we defined above, he can move north, south, east, and west, and we've given him a quest, and also we have loaded some interactions that the game will have with the player. We will go straight into the main loop of the game, and we just need to check if the player is alive. So once the player is alive, we can give him an options to do. Let's say he wants to explore, or he wants to check inventory, or he wants to view all the requests, he wants to save the game, or he wants to quit. Let's do that. We will do while player is alive. We print game menu, and we give him an option to first, let's say if he wants to explore. 2 will be if he wants to check his inventory to see the item that he has. 3, maybe he wants to view the quest that he needs to embark on. Option 4 could be if he wants to save the game. And 5, if he wants to quit the game, he can do that. This will be the main options. Then after that, we can get his choice. We can say choice is equal to input, then we say choose an option. Now whenever we have an options like this, we use an if statement and we go through all the options. So we will do if choice is equal to 1. He wants to explore. Now if the user wants to explore, what it means is that he wants to walk around, so we need to get the game map that we already provided for him. This is the game map. He wants to move around, so we are going to call this game map, and according to how we define the map class, the map class always returns an event. If we look at the map class here, call to move the player, and we give the player some direction, it will return an event, right? If he chooses to explore, then we are going to move, right? So we will get the event and we call the game map and we call the move player function. We can do random.choice here, and inside it we will pass the options that the player can move: north, south, east, and west. So if the event is an enemy, we need to fight with the enemy. If the event is a treasure, then the user found the treasure, we will keep it in the inventory. If it is NPC, we interact with the game, and if it is a quest, we look at, let's start with the first one. If event is equal to enemy, then we are going to call the battle, if we remember. So first we can print something, an enemy appears, right? We create an enemy and we pass any name, let's say goblin, and now we call battle. Now according to the battle function that we created, whenever we call battle, we pass the player and the enemy. So we can pass player here and enemy. And if the event is equal to, let's say treasure, we can say he found a treasure, right, which he can keep in his inventory. So once we tell him that, we can call the inventory instance that we created up here, right here, and we add item, and according to the add item class, we pass in the item, and an item needs the name, item type, and effect. So let's say he found gold, the type is treasure. Let's say that the effect of gold, let's say 0. The next option, if the event was just NPC, as we've already defined the NPC here, we can just select a random instance from the NPC. It is an array there, so we can say NPC will be equal to random.choice, right? And we will pass the NPC start. So the NPC is an array that contains multiple of these, so we will choose randomly from the NPC. And after doing that, we can just say unit, so NPC.name, right? Then we get the quest. This time the quest will be the NPC, then we get interact player. So when we look at the NPC class, it has a function called interact. We scroll to the top and we pass the player. When we pass the player, it will print the name of the NPC and also the dialog and the quest, whether the user wants to go on that quest or not. So as we can see, this will always return a quest or nothing. So scroll back and we are getting that quest that is returned from the NPC. Once we get it, let us make sure that the quest is right. If that is the case, then we can append this quest to the quest list that we already defined. This is the quest that we defined. We can append it to it. So under this we will say quest.append and we will pass the quest to it. Now what we have left is nothing. We've looked at enemy treasure NPC. So now what we have is we can do our else statement here and we will say print nothing happens. Now all these are under choice 1 when the user chooses to explore right here. So now we can take a look at choice 2, that is when he decides to check the inventory. Correct this, check inventory. So we go down, make sure you get the indentation right. So right here we say if this time choice is equal to 2, he decides to check the inventory. So what we'll do is that we will print all the items in the inventory to him and ask him if he wants to use any of those items. So what we can do here is that we can print all the items in the inventory to the player and ask him to maybe choose one. We can do printf inventory and we will show the items in the inventory. Because this is an array, we can just loop through and we will do item.name for item in inventory.items. This is the inventory. It contains this list items and it will return all the items in the inventory. Then we will get his choice, right? We will ask him to enter item name, or maybe he should return if he doesn't want to use it. So now we will get the choice, and if he doesn't want to go back, he wants to use the particular item. So we call the inventory and the use item function, and according to the use item function, you pass in the item name and also the character item choice here, and also we will pass the player. Our third choice is view quest. He wants to look at the item in the quest. Now when we scroll a little bit upward, we define the quest here and we loaded the quest from the file which was provided as part of the game. So all that we need to do is just to loop through this quest and show the player which quest he has completed or not. This time if choice is equal to 3, then we can just print like showing quest. Then we will look through the quest that I said. So for quest in quest, first we will check whether the quest is completed or not. Let's get the status of that quest. So we can say completed if quest.completed, else incomplete. Now we can show the description of the quest and also the status of that particular quest. So we can do quest.description and we show the state. Now if he chooses option 4, what we need to do is obviously call a save game function and we'll pass some argument to it. We have not created the same game function yet, but when we do, the save game will take the character, it will it will take the inventory, the game map. Literally, it is saving the entire state of the player's game so that when he comes later on, he can load the game. You save the game map and also the quest of the player. And the next choice, if he doesn't, and the next choice, if choice is equal to 5. If he wants to quit, we just break from the loop. That should be it. Else, probably the choice is invalid and you can say that invalid choice. Please try again. That should be all for the start new game. As long as the player is alive, he can decide to choose any of these options, either to explore, check inventory, view quest, save game, or quit. The next function that we are going to define will be the save game function. In defining the save game function here, first let's write a comment. We go ahead and write save game. Now we'll be getting all the items that we can save. For example, we'll get the player and everything about the player. We'll get the inventory, we'll get the player's position and the quest. So this function needs to take some parameters. We'll pass in the player, we'll pass in inventory, we'll pass in the game map, and also we will give it the quest. We can use the Python with open and we pass the file name. We want to call it save game.json. We are writing, so we pass w as file. Now we create an object called game state, and inside this object we will get our key value pairs for our JSON file. So the first key value pair will be player and all the attributes of a player. So player will be an object. Inside the player, you will get his player's name. We get it from player.name. Then we can get health point, player.hp. The next attribute, we can get the attack, player.attack. Then we will get the defense, player.defense. We add the level and also we will get the experience, player.experience. So this is the first key value pair, player and his values. And after saving the state of the player, we can also get the state of the inventory. Now this inventory, as we said, it is a list that contains all the items that the user picked along the way. It's going to be an array and we will use the dictionary to list all the items in there. So we will do for item in inventory dot items, right? That should list all the items in the array. The next one, we can get the player position, which is supposed to be the game map, right? So we can do game map dot player position. After this, we can get the quest. So we pass in the quest. Now the quest is also a list. We can look through the quest, get the description, whether the quest was completed or not, and also the reward for that specific quest. We can start by getting the key value pair description here, and description we get quest.description. The completed, we can do quest.completed. Then the next one could be reward, quest.reward, and that is it. So for quest, in quest. So this should be it. This should be the state of the game. Once we have these, we can use json.dump to write all these value pairs into the JSON file that we created above. Don't forget, we created a JSON file and we call it save game. So here we can write a comment like to serialize a Python object into JSON format. We will use the json.dump method and we will pass in the game state and the file. That should be it. So doing that, we can get out of the while loop and write game is saved. And that should be all for the save game function. The next function that we are going to write will be the load game function. We can go ahead and write load game just as we called it inside the code, and we are going to read a JSON file that we saved from the save game function right here. So we will do a try and catch errors. Can do try, and we use with open command to read the file. We know the name of the file. We call it savegame.json, and we want to read as file. So we can create the same object and load it json.load. Then we pass the file into it. Once we have the file like this, looking at how we save our data, we will go into our game state. Then we get the player, we get inventory, we get player position, and we get the quest. We shouldn't forget quest is an array of items. Inventory is also an array of items, and the player is an object. Come down here. First, let us get the player data. With the player data, we will do game state. Because it's JSON, we use the key player just as we saved it here, this key value pair. So with this, we get the player data, and out of the player data, we can create a character. If we've forgotten, these are all the attributes of the character class. It has name, HP, attack, and defense level, and experience. So when we come here, we can create the player data, and we call the character as usual, and we pass in the argument. When we look at the character class, it takes a couple of arguments. It takes the name, it takes the HP, it takes the attack, defense level. The first one is the name. We can do player data and we get the name just as we saved it. The next one is the attack. So we do player data and we get the attack. From attack we get defense. Player data, you get the defense, then we get the level, and that should be it. Now that we have the player data, we can add the experience to it because we also save the experience. But when we are instantiating the character class, we don't have to pass the experience. So player data, then we get the experience. Now we have retrieved the player character from the JSON file that we saved. The next is to get the inventory. So we can create a variable here called inventory. So this will be an instantiated object of this inventory. We will loop through and write all the saved inventory items into this variable. So we can do for, let's say, item data in game state. Now in the game state, we saved our inventory as this. We saved as inventory. We get the list right there, and we will add them to this variable that we created. So dot add item. The parameter was an item object. So we need to create an item object. The item class takes name, item type, and effect as parameters, which means that we will call the item data. We get the name as we saved it, we get the item type, and we get the effect. Yeah, so it will look through the items, make an item object, and add it to the inventory list that we have. When we are done with getting the inventory, the next thing is to get the player position as we saved it here. We saved all the map and the movement of the player as player position. So we create a variable player map, instantiate the map class, we give it a size of 5. Then we get the positions that we saved from the JSON file. Player position, we will just set it to game state, and we will retrieve player position. Once we have the player position, we can retrieve the quest and storyline. We create an empty list. We will loop through the quest that we saved. We saved it as quest here. It was an array, so we loop through all of this and we get the quest. We create quest object and we add them to the list. We can do for quest data in game state quest. This will retrieve everything. We will create a quest object. And quest class, as we define it, requires description and reward as parameters. So when we instantiate this object, we need to pass the description. So we do quest data and we get description, and also we pass in the reward. You can do quest.completed, and this should be equal to quest data into bracket completed. Okay, so once we get this, we can append everything to the list. With this, we have retrieved all the quest and storyline. The next thing to do is to get the NPC, that is the non-player characters, which include all the dialogues that the game intelligence will have with the player. So we can create an array like this. We call the NPC. We instantiate the NPC class, and the NPC class takes the name, it takes dialogue and quest as parameters. So go here and we can say old man welcome to our village. We need your help. We pass in the quest and we get the first item of the quest. Now at this point we have retrieved everything that we need to enter the main loop, and when I say the main game loop, I'm talking about just as we did for starting a new game right here. So I'll quickly write everything here. You can go ahead and copy. It's the same thing. 3 is to view quests, 4 is to save game. The same thing, we get the choice. Event will be equal to game map. We use random to get a choice, south, east and west. So now if event, and whenever the player moves, he meets a couple of things as we defined earlier on. He could meet an enemy, he could find a treasure NPC, or he could meet nothing. Now we check for the next thing that he might meet. Treasure. You will say you found a treasure. We add it to his inventory called item class, and we pass in the name, type and effect. Event is equal to NPC. That is a dialog with the game intelligence. Then we do the same thing. Random.choice. We pass the NPCs into it and we get the quest. NPC.interact. We put in the player. If quest is valid, we can add it to the list, else he met nothing. So that was for choice 1. And for choice 2, in case he wants to check up his inventory, then we do the same thing. Item the name for item in inventory.items. We show him all the items. That if his choice is not equal to bank, then he wants to use item function, the item name that he picked and the player. If the choice was 3, then we will look through the quest, show the user the description and also the status. Now if his choice is equal to 4, then he wants to save the game map and the quest, else it's an invalid choice. The next thing to do is, when we go back to the definition of this function, we started everything with a try because we were reading for a JSON file. So we need to add the exception here. So we can add the except not found. No saved game was found, right? That is all the functions for this game. As with all Python scripts, we will run the main file. If name is equal to main equal main. The next thing is for us to run it and debug any errors. Now that we are done with the program, we'll go to wherever you created the Python file and let's run it. First, do ls. So we call Python 3 and the file name. So when we run the program, the main menu comes and it asks either we want to start a new game or load the previous game or quit. If I select option 1, enter character's name Titan, and it's saying choose your character class, so I choose warrior. Oops, and now we have an error. So let us look at the error. You say the start new game class, load quest and file. Okay, now as I said, the quest.txt file is part of the game, so we need to add it to it. So let us create a file, call it quest.txt. So we will write something into there. Let's give the player some quest too. So the first quest, we will say find the lost sword, and the reward for this will be 10. We'll add 2 more quests. Save the village from goblins. So goblins are the enemies, and we will also say retrieve the magic amulet. The reward is 20. So once we are done, I will save this file and let's run the game again. So we do Python 3 main.python. Okay, so 1, we start a new game. Okay, so character name Titan, we choose warrior, and now we have entered the main game loop with the 5 options: to explore, check inventory, view quest, save game or quit. So if we choose to explore, I click 1. Perfect. Now we are getting another error. Let's fix this one. Start new game, game.move player, self.position. Yes, the error is in how we are implementing this, because the player.position is an array of 2 coordinates, x and y, but we didn't indicate the index of the array that we are looking at. So let's go to, so when we scroll to When we scroll to this part, now when you come to the map, you can see that player.position is an array of 2 coordinates, right? So we will get the first coordinate. Let's fix that. This one to the first coordinate, that will be the X, and the other ones will take the second coordinate, that is the Y element. This is what we need to. Now once we are done with this, go back. I'm going back to the terminal, but however you want to run it. So I will do Python 3 again. Now we have this, so let's start a new game. Character name will be Titan. We want to be warrior. Main game loop. Now if I choose one to explore, it's saying you meet an old man, and the old man is saying, welcome to our village, we need your help. Do you want to accept this quest or not? So I will say yes. Let me check my inventory. So in my inventory I have health potion and iron sword. I'll type back to go back. Main loop again. Let me view the quests that I have. If I type 3, okay, so these are the quests that I have. So we have find the lost sword, it's incomplete. Save the village, incomplete. Retrieve the magic amulet. What if I go to explore again? 1, nothing happens. If you remember, as we said in our program, whenever you want to explore, you can either meet an enemy, you can meet a treasure, and meet NPC that is interacting with the game, or you can meet nothing. So in this case we met nothing. Explore again. So this time an enemy appeared and there was a battle and we won. Now you can choose to also print the incidents of the battle if you want to, but it's not necessary. You can do that here. Yeah, so if you look, these are the options. Whenever you move to explore, you might be able to meet this. Yeah, so this will bring us to the end of this game. I hope you learned something from Python, especially how to manage files and how to create classes and inherit from classes, and also how to manage the control flow of program. See you in the next video.